Good morning, everybody, and a very warm welcome to our first European Hydrogen Week. Without no doubt, these are very challenging times for everyone, and I hope that you, your family, colleagues, and friends are doing well in these times. One of the things that has changed the most is the way we interact with each other, and that is why the entire week will be organized virtual. It has the advantage that we can reach more people, and I'm extremely happy to see that nearly 3,000 people registered themselves for this event. I truly hope that everything will go smoothly this week, and I want to thank already in advance the entire team that did all this huge preparatory work. The European Hydrogen Week is built on the traditional stakeholder forum and program review days. With the recent announcements of the European Hydrogen Strategy and the Clean Hydrogen Alliance, which spells out the huge ambition that Europe has regarding hydrogen, we had no choice than to step up and meet that ambition with the first European Hydrogen Week. The agenda of the week is amazing. We will start with the program review days that, compared to last year's, will feature more fantastic research results and will be more interactive. By the end of the day, we will have a surprise visit by a VIP from the European Commission, as some announcements will be made. So stay tuned until the last session if you don't want to miss anything. At the end of the second day, we will hear who won the FCH JU Awards for the best innovation, the best success story, and the best outreach. This will be followed with the Young Scientist Award given by Hydrogen Europe Research. On Wednesday, we organized, together with the German presidency and NOW, which is the National Hydrogen Association from Germany, an event around regional and international cooperation. Several ministers from inside and outside Europe will come to speak to shine a light on how they envision the cooperation with the EU. Thursday will be really the highlight of the week. We organized the European Hydrogen Forum together with the European Commission DG GROW, and we have managed to gather an amazing lineup of speakers. 4 European commissioners, including the Executive Vice President, Mr. Timmermans, as well as 4 Director Generals and many CEOs and top scientists will take the floor. Friday then is reserved for the Clean Hydrogen Alliance members. During this day, pitching events will be held by project promoters and investors, as well as we will be able to take stock on the different IPCEIs and the Innovation Fund. So as you can hear, we have a full agenda, which consists out of more than 200 speakers. More details and updates can be found, of course, on our website. Ladies and gentlemen, to open officially our first European Hydrogen Week, we have invited really a top speaker. He combines innovation and adventure to go beyond the obvious and achieve really the impossible. He made history by accomplishing 2 aeronautical firsts around the world, non-stop in a balloon, and more recently in a solar plane without fuel. He considers ecology always through the lens of profitability and made him a forward-thinking leader on the themes of innovation and sustainability. He is the founder and chairman of the Solar Impulse Foundation. His mission today is to select 1,000 efficient solutions to protect the environment in a profitable way. He is now the United Nations Goodwill Ambassador for the Environment and Special Advisor to the European Commission. It is my honor to give a warm welcome to Bertrand Piccard. Bertrand, we are looking forward to hear your inspiring talk. Thank you.
Thank you very much, Yannick, for this kind introduction and for your invitation to speak to this very prestigious forum. And good morning, or good evening, or good afternoon, wherever you are, to everyone. Hydrogen today, I think, is the most fashionable theme that we can see in the media. Each time we hear about climate change, mobility, whatever, somebody speaks of hydrogen like if it was the miracle solution. And I think if we speak of hydrogen, we really have to give the arguments that are correct. I believe enormously in hydrogen, but we have to really define what we speak about. Hydrogen is not an energy. It is not a source of energy, because we have to produce hydrogen, which means that we need to take energy in order to fabricate hydrogen, and then we can use it as an energy. So it means it's a vector, or it's a storage for energy. But it's also a product for the industry. Hydrogen is used in steel production, like most of you know, but not a lot of people know in the public what it's really about. Hydrogen has a temperature of combustion that is extremely high, which helps for the steel industry. But it is also a huge market for fuel cells, for example. It is a market for new products. It's a market for a lot of innovations. When we see, for example, and Yannick was speaking about the Solar Impulse Foundation goal of identifying profitable solutions. We have identified solutions like a DCC, which is a heat production unit made by combination of oxygen and hydrogen. You have Atawheel, which is producing and selling a distribution of hydrogen for electric vehicles. Cell 3D. Cell 3D has been made by Air Liquide, and it is a 3D printing for fuel cells. So we see that it starts to be today a very, very promising economical market. But all these economical issues should also be understood through the angle of energy independence. What is the really interesting factor for hydrogen? It's the fact that you can produce it with electricity that comes from renewable sources. So you can produce it everywhere when you have wind, or you have solar, or you have hydroelectricity, or you have biomass, or you have geothermia. So it doesn't limitate the production to countries who have a source of energy like fossil fuels. Today, Europe is consuming a lot of gas coming from Algeria or Russia. So it's clear that on the political level, it's extremely interesting to be able to produce our hydrogen locally. And of course, when we speak of the clean recovery today, it is more than just a recovery. It is the way to use these billions of euros flooding on the market to build something new, something that was not existing before. And in that sense, the hydrogen policy of the European Union, of France, of Germany, is extremely interesting. Because to be clear, when we speak of electricity, Europe has lost the war of batteries. But Europe can win the war of hydrogen in terms of energy production and in terms of fuel cells and in terms of renewable energies. This is something that is really crucial, of course, when we speak of environment. Hydrogen, whatever is the production source, is zero emission when you burn it. So, of course, it's better to make it with renewable energy. But if you cannot make it with renewable energy, and you produce hydrogen in a place where the pollution is not too damageable for the population, then the hydrogen can be used in cars in the cities where pollution is damageable. So it is something that in terms of pollution, not only climate change, has a big advantage. Now, of course, for climate change, this is the perfect solution if the production is made from renewable sources. Here, we have to see that today it is not the case. I believe in the latest numbers, it is 0.1% of hydrogen that is made from clean sources of energy. So it is not yet what we need at all. And a lot of people will tell you it cannot be done with renewable energy. It is too expensive. We will never have enough. So let me stop here to really say that today, renewable sources of energy like solar and wind have done a quarter of the price of nuclear power or fossil fuels. A quarter. The most beautiful example today is what Accio Energy, a French company, has done in Portugal with electricity that is produced at 1.5 cents per kilowatt hour with solar. And solar is intermittent, as you all know, like the wind. So imagine that you have a solar or a wind production that is sometimes enough, sometimes not enough, sometimes too much. Very interesting to see that today the solar production is sometimes excessive, so much that the electricity is lost. Even in Germany, sometimes with solar and wind, consumers have to be paid to use renewable electricity, otherwise it will break the grid. This amount of excessive energy can be stored in hydrogen. And this is a way to produce hydrogen that is extremely cheap. And that's an infinite efficiency, because you go from zero, where the energy would be lost, to whatever, where the energy is used. So we have an extremely interesting market plan here, where renewable energies have to be combined with energy, with hydrogen production, in order to absorb the excess and reduce the cost. If we speak of environment, of emission, of climate, of course, we come to the question of efficiency. Will there be enough hydrogen production in the world to fulfill all the needs? Well, in this case, the case we have today, where we waste 75% of the energy we use, no, we will not be able to have enough. But if we count all the energy efficiency progress and evolution that we can do, yes. And this is why I don't think it is relevant to speak only of hydrogen, only of solar, only of whatever thing individually. It is a systemic approach that we need. It is a network that we need. We have the production that must be clean. We have the hydrogen that is used. But the way we use it has to be combined with a saving of energy and stopping the waste that we have today. Today, houses are so badly insulated that even if you heat with hydrogen, or electricity coming from a fuel cell, it will not be enough. So you need to combine all the plans of energy efficiency in electric engines, in insulation of houses, in mobility, in industry processes. If we want to be able to really put an important fraction of hydrogen into our consumption. Now, of course, mobility. Mobility now includes hydrogen even for airplanes. Is it a dream or not? I think we have to be very careful before believing that something is impossible. The Wright brothers flyer in 1903 was considered to be completely impossible, and people were laughing at the Wright brothers until they succeeded and managed to fly. And 66 years later, there were 2 men on the moon. So when you see Airbus announcing that 2035 will be the year for hydrogen airplanes, don't laugh. They will do it. They will absolutely do it. And what is so fascinating with hydrogen is the fact that it brings pioneers. It brings pioneers. It brings innovators. It brings people who want to change the world. So it's a unique opportunity. When you look at the old economy, people are doing business as usual. They want to break every evolution, every progress to keep the old system as long as possible. With hydrogen, it's exactly the opposite. It's a pioneering spirit that is spreading everywhere, in the industry, in the mobility, in the energy business, in the politics, and hearing as many European commissioners speaking about these hydrogen opportunities is something that is absolutely wonderful. So how is hydrogen going to find its place? You have batteries, you have ammonia, you have different things that can go for the fuel cells. Well, we have to understand something. There is space for everyone. It's clear that if you have a small vehicle making short distances, batteries will be better for a long time, because the battery has almost 100% of efficiency. So all the electricity you put in the battery comes out of it. When you have a fuel cell, you have 50% of efficiency, but you have a much lighter system. So there is an inflection point, depending on the distance you want to drive, depending on the weight of the vehicle, where it will be better to use hydrogen. For long distance vehicles, like trains, like ships, like airplanes. So we see that here, you have a market for everyone. And I would say that more important than that, even more important than anything here, it is the fact that you can include the oil industry. You can include the heavy industry, because until now you heard so many people fighting against the industry, saying we have to eliminate oil. And with that, oil companies will fall down, collapse, with millions of people unemployed. I don't think it's the way to go. I believe we have to include the oil industry, because they represent so much wealth, expertise, and jobs. Batteries cannot include the oil industry so much, but hydrogen can. The oil industries know how to transport and sell a liquid like hydrogen. So we have the possibility to shape a new society by making more winners than losers. So you see that we are now on the edge of something that can change the world if we don't wait for the others to do it. In Switzerland, there was no help, no support for hydrogen on the national level, which means that private people have gone together to put supermarkets together for renting hydrogen trucks, going to all the competitive fuel stations, asking them, if you have supermarkets driving trucks, are you going to put hydrogen distributors? And they said yes, which means that they went to Hyundai in Korea and said, we have gas stations distributing hydrogen, and we have users for hydrogen trucks. Are you bringing trucks? And they said, yes, we can bring 1,000 trucks. And you have hydroelectricity, completely clean, producing hydrogen in Switzerland today. Today. Not in the future, today. And already today you can go across the entire longest distance in Switzerland with hydrogen. And if you have trucks that are fully fueling up with hydrogen, of course you can have cars. So when I drove the Hyundai Nexo for the world record with hydrogen, with 6 kilos of hydrogen, almost 800 kilometers, it's clear that it starts to be now today an opportunity for cars, normal cars, not experimental cars, normal cars from the market to be used with hydrogen and drive in Switzerland. So of course we need a plan, an economic recovery plan. We need subsidies if you want to do it fast at the highest level. But you see that in Switzerland, it already works without subsidies. The only thing that you need is to have no taxes on hydrogen. And at this level, at this moment, the cost of each kilometer with a truck of hydrogen will be the same cost than diesel. very interesting. You see, when, and I will finish by this sentence, when a lot of people are saying hydrogen is the future, I think it's wrong. Hydrogen is the present. It already works. It can already be profitable. It is a fantastic opportunity. The pioneers know it. We know it because we're here in this Hydrogen Week session. But we need everybody to know about it. Hydrogen is not making the miracle of changing everything, but hydrogen brings a lot of little miracles that will contribute to shape the world in terms of economy, in terms of industry, in terms of energy independence, in terms of mobility. And I think it is extremely exciting. And we need to take everyone with us for this excitement. So thank you for allowing me to open this Hydrogen Week. And I wish you a lot of success during this week. And I hope that enough people will understand the opportunities they can take and join this fantastic hydrogen fashion in order to make it the hydrogen reality of today. Thank you very much.
Thank you very much, Mr. Picard, for your such inspiring speech. And I can only agree with you. Hydrogen is present and there is room for every technology. Well, during the next 2 days, you will hear, of course, the results from nearly 100 projects. And I'm sure that we can add a few more inventions to your 1,000 solutions. In fact, Mr. Picard, we are already in talks with your team. And after this event, we agreed to sit down together and look which innovations we can add to your very impressive list. Thank you again for giving the opening speech for the first European Hydrogen Week. And honestly, you put the bar for the other speakers immediately very high. Thank you so much. This brings us now to the next speaker, who will officially open and moderate the program review days. She doesn't really need any introduction because I'm sure that many among you know her. She's my head of unit for operations and communications, and together with her entire team, she is doing really an amazing job, which you will find out during the next 2 days. She's already working for more than 15 years in the European Commission, dealing with hydrogen and fuel cells. She is a scientist and an economist from education. So, honestly, I can say a truly expert in the field. So, let us welcome Mirella Atanasio. I'm really looking forward to your and your officer's presentation and hearing all those fantastic results that you have achieved. The floor is yours, Mirella, and to our audience, stay until the last session because we will have a surprise VIP visit, so don't run away. Thank you very much.
Good morning. Good morning. Good morning, everybody in Europe, I would say. Good afternoon, good evening in other parts of the world. A very warm welcome also from my side to the first Hydrogen Week and to the, I would say, 10th edition of the program review days. Indeed, this year has been extremely challenging for all of us, and I truly hope that you and your families are fine. I really hope for that. Due to these challenges, however, as an optimist, I always look at the positive side of everything in my life. I'm really proud today that we have managed, in fact, to keep the tradition of our program review days. And as an advantage, we could even invite more projects to present. And you will see through the parallel sessions, multiple parallel sessions, that we will go even beyond our projects, and we have invited several other projects from different other EU programs. I will start this wonderful week with a presentation on the program status of the fuel cell and hydrogen joint undertaking status, including not only the overview of our grants or projects that we are supporting over the years, but also some other activities, such as the studies, for example, the initiative of working with regions, or even different activities or different initiatives in feedback to policies. I don't think it's necessary that I remind everybody why we are here today and why are we doing the Hydrogen Week. We have as you well know, from the European Commission, on the 8th of July, we have launched a European hydrogen strategy in which our Vice President, Executive Vice President Franz Timmermans, has wished that the new hydrogen economy can be a growth engine to help overcome even this economic challenge or damage caused by COVID-19. And the hydrogen strategy has set up very ambitious targets. We have very ambitious targets by 2024, the 6 gigawatt electrolyzers, by 2030, even the 40 gigawatt electrolyzer, with a high ambition that by 2050, we have all deployed technologies at large scale, with all of them reaching, of course, maturity. Who are we? For those that do not know us by now, although I would say that for more than 12-year existence, everybody should know us. But I still discover from time to time people who are wondering what is a joint undertaking. It's somehow a complicated word. It's a public-private partnership between the public side, European Commission, representing the EU, and on the private side, Hydrogen Europe, our industry association, and Hydrogen Europe Research, the Research and Academia Association. What are we doing in this public-private partnership? We are pushing the technologies to maturity by 2020, and hopefully in the future by the ambitious of 2030 or 2050. We have very ambitious objectives. We have, in fact, 5 main objectives, and in the future we might get even more than that. And we work on the hydrogen production side on green hydrogen production, mainly through water electrolysis. We also look at feasibility of hydrogen to be used as energy storage medium and also for grid balancing. And then on the uses of hydrogen, we work on the heat and electricity production with use of hydrogen for stationary or with stationary fuel cells. On the mobility, on clean transportation, we work on fuel cell, on durability of fuel cell, but also low-cost fuel cells. And finally, when working on all of that, either electrolysis or fuel cells, we look at minimal use of critical raw materials, for example, platinum. If we talk about the program implementation, I mentioned already we have more than 12 years of program implementation. And of course, in these years, we have supported 262 projects, precisely signed one, and we are currently negotiating or preparing another 23 additional grants, which in terms of coverage are about half and half between the uses, either hydrogen production and use in the energy sector and use in the mobility sector, but with also about 6-7% either in cross-cutting issues like the pre-normative research, safety, regulations, standards, education, or in type of overarching projects or cross-sectorial, sectoral integration type of projects. And I would also invite you, like my director Bart Biebert said, I will invite you to stay and to follow all the parallel sessions to see examples of all these type of projects. When we talk also about the projects, you will see that in supporting this research and innovation type of activities through grants, we have also managed to leverage, at least in the projects, the same amount of private investments. And if you look at additional activities that our private members have invested in addition to our projects, you will notice a leverage of even 1 to 3. For €1 public investment, we have reached €3 private investment. Now, about the event today. The annual program review of this year, like I mentioned, is the 10th edition. We have normally every year reviewed the ongoing projects, gathered even data, done a lot of surveys with these projects, and we have seen and we have analyzed the progress of these projects against the previous year. I would kindly also invite you to look at the report of the previous exercise, the Program Review 2019, which we have just released a week ago. always, by doing this program review, we have also done an exercise of collecting and extracting success stories and innovations. The innovations, normally we have always done it with the innovation radar exercise. And out of these successes, you will see tomorrow evening the awards, the FCH JU Awards ceremony, where we will identify the best success story, the best innovation, and as a privilege, I would say, to us, to the fuel cell and hydrogen joint undertaking, we will also identify the best outreach. So stay tuned, also like Bart said, and tomorrow evening you will find the winners. Now, on the dissemination and exploitation, key results, but also publication in patents, you will see many, many achievements only over the last year. Just if you look at this number, they are impressive. You will see 77 publications, but also many other, one patent already in application, but many other numbers that are very impressive for 77 projects over the last year. Same when you look at the different type of dissemination activities and the different type of exploitation activities. And in terms of key exploitable results, you will see also how our projects have identified, when disseminating and exploiting results, how they have identified the bottlenecks but also, and obstacles during the exploitation. It's not easy, I want to say, to exploit research results. It's not easy to make them appealing for investors, and this is where they have to spend more time and they have to spend a lot of effort. And I have to say here, Horizon 2020 and our program per se is doing a lot of effort to make that possible. Now, as I mentioned, we do not only support grants, we do not only support projects, but we also do a lot of other activities in the joint undertaking by our nature, by our public-private nature. We also have funding and financing support services, and we do, for example, we have talks to look with our projects for combination of fundings. For our flagship projects, for example, we look at what our other sources of funding or financing are possible. We are, as I mentioned already, we are looking at how our results from our projects could be exploited, how this could be brought to the investors level. We advise on complex business models, for example, and finally, we look at any other news concerning funding and financing, of course relevant for our sector, and we try to inform our sector about that. We are doing also studies, for example, in addition to our projects, of course, working hand in hand with our industry association, but also with our European Commission colleagues. We look on how are we going in the different sector. And it was mentioned by Mr. Picard just before about aviation. How do you think that the aviation people came to that conclusion this year? It's just because we have done a fact-based study together with our colleagues in Clean Sky, for example, the other joint undertaking, and we have provided the facts to the aviation sector, and they have indeed came to the conclusion that's feasible by 2035, for example. We have also worked with the member states based on their national energy and climate plans, and we have looked at opportunities for hydrogen in their national plans by 2030. And finally, I just picked a few of the examples. We are currently working and approaching the end in looking at hydrogen trucks. And stay tuned again, tonight you will hear the first results of our hydrogen truck study. We have worked also in mapping, for example, the hydrogen refueling stations in Europe and making them able to send a live signal that at any moment we know which hydrogen refueling station is available, and if it's not available, why. And we are continuously working in that to map it and to have a clear networking station and to give all the data to any provider, to anybody who would like to develop applications for drivers to be able to see which are the hydrogen refueling stations available and where. Another example that we have worked on, and this is more on the way we work with our public partner, European Commission, to provide feedback in any future policies. We have started working for several years already on guarantees of origin of hydrogen. We have put in place 2 definitions. We have tested in 4 different pilot plants with more than 70,000 guarantees of origin on the market. And then now we are moving on the certification scale and at the level of member states to have a common methodology, a common certification scheme for guarantees of hydrogen. We have also just launched on 15th of September our Fuel Cell and Hydrogen Observatory. This is our part of knowledge management, if I could say that, of our office, where we want, and we are, but we want even to keep that role of knowledge hub on fuel cell and hydrogen in Europe. So please go look. This observatory, again, stay tuned. This day in the program review days, they will also launch an additional platform, an additional functionality for the observatory. And finally, I wanted to give the example of working with regions. We have worked also for several years. We have started working with different regions in Europe. We realized they are an important actor in addition to working with the member states. And we have come to the so-called Hydrogen Valley. You may have heard about Hydrogen Valley. This is one of our successes, well recognized even by President of the Commission, von der Leyen. Stemming from that, why not going internationally? And internationally, we are also working to establish an information sharing platform for all hydrogen valleys under the Mission Innovation Challenge 8 on hydrogen, together with the colleagues, Germany and Australia, of course, us on behalf of the European Commission, but also together with all members of this challenge of Mission Innovation. For regions, of course, for less advanced or less knowledgeable, if you want, on hydrogen, we have also put in place our Regions Hub. I wanted also to pick this example today to draw the attention to any region in Europe that we have this hub of knowledge again, where you can go, you can look, you can get yourself aware of the hydrogen technology. You have different business cases, but we can also look for opportunities of funding and financing. With that, I finish my introduction. You can imagine I could go in any single detail, but I don't want also to take or to spoil, how can I say, the interest and the pleasure of my colleagues, the project officers that will follow after me, and will give you even more details on all of this. And I would like just to draw your attention to a bit the rules of the game, if I could call it. Please do not forget that you can put questions. We can take questions live, and we will try to answer them as much as possible during the whole week. We are using the Mentimeter, and you have here several instructions on how to access the Mentimeter and put your questions at any time during this week. We have a professional time behind that will take your questions, will pass them to us, to the different moderators, and we will do our best to answer to your questions. And with that, this is really my last slide. And just to show you the different parallel sessions that will follow from now on till tomorrow evening, you will see that we have 3 different sessions just looking at hydrogen production. On the left side, the green, we have 3 other different sessions on uses of hydrogen in energy, but also for sectoral integration or in production and careers. We have also 3 different other sessions when looking at the transport applications, and we have 3 others on education training, for example, or this type of cross-cutting initiatives, including those like looking at complex financing like hydrogen in the future one. So you can see very heavy, very full of information days, which I kindly ask you to follow. And with that, I thank you very much for your attention. And it will be my pleasure to already move to the next presentation coming from my project officers. And I give the floor to Nikos Limberopoulos, who is our senior project officer on hydrogen production, mainly on hydrogen production. And he will have the pleasure to present to you an analysis of the portfolio of projects in this area. Nikos, the floor is yours.
Thank you, Mirela, and good morning, everyone. It's great to have you again this year in our program review days. My name is Nikos Limberopoulos, Project Officer at the FCH JU on hydrogen production. I will be presenting you an overview of the support we provide in this area on hydrogen production, storage, and distribution, on behalf also of my colleagues Dionysis Timis and Claudio Pavlo. Now, hopefully, I will be able to, move also the slides. Like Mirela mentioned, there are 4 sessions dedicated to hydrogen production, storage, and distributions. 3 of them are for today, and 1 tomorrow afternoon, moderated by myself and my colleagues Dionysis and Enrique Giron. Let's start by looking at this map of hydrogen production routes. On the left, it's the splitting of the water molecule through direct solar or electrolysis. And in the middle and to the right, it's the extraction of hydrogen from bio or fossil-based hydrocarbons through reforming or gasification. Today, hydrogen is produced from fossil fuels. However, our support, indicated by the orange circles that you see, has gone to only renewable hydrogen production. So 68 projects, more than 200 million euro, 18% of FCH JU support going to this area. The majority of this support going to electrolyzers. So let's start looking at electrolyzers. On the left, you can see the almost consistently increasing support of the FCH JU to electrolyzer projects, different colors indicating different types of electrolyzers. To the right is the cumulative support, 135 million euro, provided mostly to PEM electrolyzers, then to solid oxide, high temperature electrolyzers, then alkaline, some projects with more than one type, and then anion exchange membrane and proton ceramic electrolyzers. This is a slide of our largest low-temperature electrolysis demonstration projects. In green, it's the ones with PEM electrolyzers, and blue, the ones with alkaline. They are sorted according to the capacity of the electrolyzer, indicated in the arrow in the middle. Interesting to observe that in the last 8 years, we've gone from a capacity of 150 kilowatt in the Don Quixote project to 20 megawatt in the Jewels project. So 100 times increase, while at the same time, FCH JU support was reduced by 50 times per kilowatt or per megawatt installed. I would like also to flag the 6 megawatt H2Future project and the 10 megawatt Refine project. Both will be presented today. They have allowed close interaction with the steel industry and the refining industry, and these industries have lobbied for hydrogen, helping it move to the center of European energy policy, and also eventually to the European Green Deal. You can see at the bottom right the 100 megawatt electrolyzer project. There is a call currently open that is managed by DG Ener. These large demonstration projects have forced electrolyzer OEMs to really up their game to be able to address various new challenges for installing and operating in industrial courtyards. At the same time, industry familiarized with these novel electrolyzers. Same thing for permitting authorities. And they are updating the various tools, risk analysis, etc. And we've observed this iterative loop that has been very beneficial for establishing a solid trust basis on which the EU hydrogen strategy was built. Also very important, the support to the European value chain. I love this picture that I'm copying from the Refine project on the right, showing the different components being developed or acquired for the 10 megawatt PEM electrolyzer. These originate from 5 different EU countries. We have in Europe a vibrant research community supporting electrolyzer OEMs that has achieved all the different MOB targets, safeguarding Europe's leading position. Bottom left, you can see the energy consumption at stack level for alkaline and PEM electrolyzers, the green bars being the averages of the prototype electrolyzers developed in our research and demonstration projects, the blue bars being the averages of commercial electrolyzers, usually those installed in HRSs in our transport projects. You can see how energy consumption is decreasing and also how much closer to state-of-the-art the commercial PEM electrolyzers are. Top right, you can see the average current density of PEM electrolyzers approaching 3 amps per square centimeter. And we have projects like Neptune and Pretzel, both to be presented today, that have achieved 6 or even 8 amps per square centimeter. At the bottom, Project Colygrid developed and tested on electrolyzers profiles for the dynamic testing of electrolyzers, and these are feeding into a new ISO standard. They have also been incorporated into the JRC document shown on your screens on standardized testing protocols for electrolyzers at cell, stack, and system level. Right, moving on now to high temperature electrolyzers, a similar trend. Over the last 5 years, we have observed a more than 10 times increase in capacity, all the way to 2.4 megawatt, and a reduction of FCH JU support by 5 times. We have also observed that in the context of those projects, some strategic partnerships have formed of the industrial partner hosting the electrolyzer at their premises. That was a very interesting side effect of these projects. Similarly, in terms of research, European researchers have supported meeting the targets on electricity consumption, durability, still some work to be done on availability. At the top left, you can see that solid oxide electrolyzers have been even tested on dynamic operation, very impressive. Project Reflex, presenting again today, is a reversible unit that has achieved 1.25 amps per square centimeter. And at the bottom, Project Gamer, developing proton ceramic electrolyzer tubular cells for a 10 kilowatt electrolyzer. Now, this slide is a kind of a reality check. We claim that Europe is a leader in electrolysis. We're using here the JRC-developed TIM tool that counts globally number of publications, patents, conferences around the world. So for 11 years, we show for alkaline, PEM, and solid oxide electrolyzers these occurrences. You can see for alkaline, EU is a leader, closely followed by China. Roughly a quarter of all publications come from the EU. For the case of PEM, EU clearly a leader over USA and then China, with almost half the occurrences coming from the EU. And for solid oxide, still EU in the lead with a third of the occurrences. So it's really very good news. Moving on, still splitting the water molecule, but using concentrated solar technologies. Over the years, we have supported the hydrosol, let's say, family, eventually, of projects that are based on redox thermochemical cycles. The most recently completed project of those, hydrosol plant, identified a number of issues on stability, cyclability, and heat recovery that the recent project Hydrosol Beyond is trying to address, and we'll be hearing from the Hydrosol Beyond coordinator today. The target is 10% efficiency at lab and 5% in the field with a 750 kilowatt solar thermal platform. Very important there to develop a high temperature heat exchanger. Then, in terms of photoelectrochemical devices, you can see here over the years how projects Artifiction, Tech Demo, and today's PEXIS have improved efficiency and have been increasing the size of those panels. We'll be hearing again from the coordinator of PEXIS on the challenges faced and on the targets met in these 10 square meter panels developed by Project PEXIS. Moving on now to extraction of hydrogen from biomass. On the left, you can see some singular projects from 2012. Project Unify, a biomass gasifier, large scale, 500 kilograms of hydrogen per day at less than €5 per kilogram. And at the bottom, Project High Time, a laboratory scale where wet biomass was used to produce hydrogen through dark fermentation. But recent emphasis has been shown on the right. It's the reforming of CO2 containing biogas. So Project Bionico has recently been completed and will be presented today. Has developed a compact it's a device, a reactor, which is both a reformer and a purifier. And Project Biorbur Plus is an oxidative steam reformer for the production of 99.9 purity hydrogen. In the future, there will be mixtures of hydrogen and methane. There will be underground storage, hydrogen as byproduct, and we need efficient separation and purification of this hydrogen. And projects iGrid and Memphis are doing just this, have achieved already their targets in terms of hydrogen recovery rate and low energy penalty, lower than 5 kilowatt hours per kilogram of hydrogen purified. iGrid is based on thin palladium membranes. Memphis is a PEM electrochemical separation device that at the same time compresses hydrogen to 200 bar. The last slide I have is on storage and distribution of hydrogen. Top left, we have supported research work on underground storage, Project High Under, that estimated the geological potential for storing hydrogen in Europe and the additional cost. Today, Project High Stock below on liquid organic hydrogen carriers is going to be presenting its achievements. Already developed a 1-ton hydrogen trailer at a very good cost of €85 per kilogram, much below the targeted cost. To the right, you can see support we provided in the past and today to metal hydride storage, tanks, Project Eden, and today we'll hear from Project High Care. The gravimetric efficiency is still a challenge, but not so much a concern for stationary applications. The concern here is the integration of renewables, hydrogen production, storage, and eventually release and use. So, what are the main takeaways from this presentation? Our research and demonstration projects have met the 2020 targets on CapEx, energy consumption, degradation, and there are more ambitious targets and also improvements in manufacturing coming up in the next multi-annual work program to keep and secure EU leadership in electrolysis. The large electrolysis demonstration projects have proved that electrolyzers are a reliable enabler for sectoral integration and helped bring renewable hydrogen to the center of EU energy policy. We have supported alternative routes for renewable hydrogen production and moved them from lab to field. However, further improvements are required for market readiness. Lastly, in terms of hydrogen storage, we've supported R&D from metal hydride tanks to conventional tanks for transport applications, to be covered in another presentation, and to the scale of salt caverns. And hydrogen storage is going to be playing a major role in the future partnership. With this, I would like to thank you for your attention. I hope to meet you in person next year, and it's back to you, Mirella.
Thank you very much, Nikos. Thank you very much for the interesting presentation. Really, like I said, many achievements in our project over the last year. I would like also to mention that I'm happy to see questions coming into the chat. So please, again, I encourage you to put any questions and we will try to take them at the end of all the 4 presentations. Without taking more time with introduction, I would like to pass now the floor to my colleague, Lionel Boyot, Project Officer on the transport side, who will guide you through the portfolio analysis of transport applications. Lionel, floor is yours.
Thank you very much, Mirella. In the next 10 minutes, in fact, I will give you a flavor about hydrogen and fuel cell for transport application. But I strongly encourage you to attend the 4 parallel sessions that will be moderated by myself, colleagues Pietro Caloprisco, Claudiu Pavel, and Enrique Giron, who grandly contributed to this presentation as well. The structure is the following. First, I'll start about hydrogen infrastructure, then moving on towards a different transport mode, and closing with research in transport. The FCH is well known for the fact that it has been deploying more than 100 HRSs all over Europe, but that's just the visible part, the top of the iceberg. There are a lot more behind the seawater line, in the sense that we helped the basic building blocks or technological block, if you want, on HRS. For example, looking at the integration of electrolyzer for grid balancing services. We are now getting ready and adapting the HRS for the wave of hydrogen trucks that will come, therefore looking at fast refueling protocols. We have adapted heavily, intensively use HRS. For example, in case of Paris, London, how is the infrastructure responding when 50 or 100 taxis are put into operation? And lastly, for the regular citizen, owner and driver of hydrogen cars, how to plan, thanks to the European HRS availability system, your itinerary so that there will be HRSs along your way that will be capable to deliver you hydrogen. On the basic building blocks, compression. In fact, the compressor is often known as being the weakest point on the HRS. Therefore, we are looking, for example, on innovative hybrid compression techniques where metal hydride will compress the hydrogen up until 430 bar. And then conventional mechanical compressor will do the top up to 700 or 900 bar. This is done in Project Cosmic. The compression concept is being tested, and later on it will be scaled up in an HRS capable to deliver 1 ton of hydrogen per day with a reduction of 20% of the energy consumption. If I now move, let's say, into the result from the trial, looking at the diagram on the right-hand side, HRSs, or hydrogen refueling infrastructure for the buses, in the period 2000 up until 2010, there were 2 bus projects, Qt and High Fleet Qt. The HRS infrastructure has been built only for the sake of these projects. You see a limited number of refuel and a great variability of the availability of this system. Then, in the period 2010-2020, projects Chic, High Velocity, High Transit, and Tree Motion have been intensively used their infrastructure, more refuel, and a better availability of the station. Regarding hydrogen refueling infrastructure for cars, the dispenser and the compressor still represent roughly 80% of the downtime caused. I move towards the different transport mode, starting with cars. We have deployed 50% out of the 1,800 cars planned in our project, mostly in fleet. In fact, 86% of them are through fleet. We'll accommodate the Toyota Mirai from spring, summer of next year. And if you are not convinced about the fleet business model, look at the graph on the bottom. Back in 2017, so 3 years ago, only 0.6 million of kilometers have been driven by the vehicles. We have been putting, of course, more vehicles, but the fleet is roughly representing 25% in number of cars, but more than the half in the total number of kilometers. So 0.6 million 3 years ago, today we are 23 million. That's 40 times more. I move to buses. The same. We are moving fast. Back in 2019, there were 50 fuel cell buses on the road. It took 8 years to go to the 50 buses. This year, at the end of the year, we'll double that number, 115. And for next year, we'll even triple that number to 350 fuel cell buses. Looking in this historical analysis, looking at the fuel cell bus consumption, kilogram of hydrogen per 100 kilometer before the new project Drive and Drive 2. In the period 2000 to 2010, in Qt and high fleet Qt, the buses were consuming something like 23 kilograms of hydrogen per 100 kilometer. Then, period 2010 to 2020, Chic, High Velocity, High Transit, and Tree Motion have deployed projects that were consuming half of that value, 12 kilogram of hydrogen per 100 kilometers. The target of Drive and Drive 2 is 7 to 9 kilograms. I move now to heavy-duty trucks. It's again the full landscape where we looked at the basis, how to increase the durability of stack up to the level of several tens of thousands of hours of functioning, how to scale up the HRS, moving from a usual 200 kilograms of hydrogen per day to 4 times, 5 times more, up until the tons of hydrogen per day. We have two demo projects, Revive 15 garbage truck, H2-haul 15 long-haul trucks, and today will be launched the business study on hydrogen trucks. Maritime started small, becoming big and fast. Back in 2017, 2018, compressed hydrogen in PEM fuel cell of size of 200 kilowatts up until 1 megawatt. 2019, we've been looking at ammonia as a fuel used in a solid oxide fuel cell. And from 1st of January next year, we'll start a project of a 3 megawatt PEM fuel cell running on liquid hydrogen. In fact, there is a huge diversity of vessels. You have cargo, you have container vessels, passenger ferries, and so on. So there is a need for different fuels and different fuel cells. In order to decarbonize port, we have the project H2 Port, looking at heavy machinery, so the reach stacker, yard tractor, that are moving containers within the harbor premises, how to decarbonize them thanks to hydrogen. Next, on aeronautics, same trends. Starting small with an auxiliary power unit, mostly to power the secondary electrical system or emergency operation, up to the aircraft propulsion. Still an aircraft of modest size, but that's an achievement. The study that we launched together with the other joint undertaking, Clean Sky, has revealed that hydrogen is a compelling option, bringing on economical terms a huge environmental benefit, and the first demonstrator could be seen by 2028. This has been later confirmed by the announcement of Airbus. Trains, the study that we did with Shift to Rail, looking at the different business cases, has revealed that hydrogen trains is competitive against electrified line, is competitive against battery electric trains and is even sometimes competitive against diesel trains. So with these conclusions, we published a call this year, and we have a successful proposals that will start on 1st of January next year, FCH 2 Rail, which will develop the bi-mode multiple unit that will be homologated in 3 different countries. Now I move into research. The basis of all the hydrogen transport mode is the PEM fuel cell. So the cohort of projects that you see there is targeting the heart of it, platinum loading, how to improve the performance, reduce the cost, and improve the stability of the PEM fuel cell. On manufacturing now, objectives are clear: how to increase the yield, how to reduce the cost, and how to improve the quality. This has been the focus of 3 projects, Inline, Fit for Amanda, and Degeman, where there is a shift from manual assembly line, if you want, towards semi-automated or fully automated line. And in project TAIA, then for the hydrogen tanks, the combination of new material, new design, and new manufacturing techniques help to halve the cost of the hydrogen onboard tanks. I am now reaching the conclusion of my presentation. Heavy duty is an absolute key word in here, and the FCH JU is prepared for the deployment of heavy duty long haul trucks. We are investigating different hydrogen carrier, studying liquid hydrogen, preparing the infrastructure and the technology building blocks. Then manufacturing is there to help to bring the volumes needed, moving from tens or hundreds of fuel cell systems per year, or even thousand, to the tens of thousands of systems needed for the sector. Lastly, research is still needed in order to improve the stability and the performance of the low platinum catalyst, and even further, the platinum-free catalyst. Thank you very much.
Thank you very much, Lionel. Really my pleasure to see also the achievements from the transport sector, from the transport application, from our transport projects. Again, a pleasure to see so many questions coming into the chat. Encourage you to put more. I cannot promise we will take them all, depending on the time. And with that, again, not taking too much time with introduction, I would like to pass the floor to my colleague Antonio Aguilo, project officer also in the joint undertaking, and he will guide you through the application of hydrogen in stationary fuel cells. Antonio, floor is yours.
Thank you very much, Mirela. Thank you for the introduction. My name is Antonio Aguilo, and I will present to you the portfolio of our activities on stationary applications of fuel cell, gas to power and heat. Next slide, please. Okay. So tomorrow we will have 2 dedicated sessions to present these activities, where a number of projects will take the floor. They will be moderated by myself in the morning, demonstration projects, and then later on, second half of the morning, with my colleague Dionysis Simis, who has actually helped me to put together this presentation. It has been a 12-year journey. I mean, we have had the objective to bring fuel cells for heat and power production to market readiness by 2020. In particular, our activities have been designed around increasing efficiencies, durability of fuel cells for heat and power production, while reducing the costs. And we have done it because they are the highest conversion efficiencies that you can get, mainly I'm thinking here about power, and because they are clean and silent. And they offer unique propositions if we think about conventional technologies, like could be the case of combustion engines. They are also fuel flexible. That means they can run on a wide range of input fuels, and that positions them in a very advantageous position as we move to an energy system with a larger share of renewable gases. Our early research actions look at understanding degradation, lifetime fundamentals. We were looking at research at component improvement level. Already back there, we were looking at material research, diagnosis issues to identify fuel cell faults at an early stage. And all these research activities were followed with proof of concept projects for a number of applications. We went into early field trials, large-scale demonstrations, covering all portfolio of applications, as you can see in the slides, all the way from residential, commercial buildings, as well as industrial and backup and remote applications. And I think proof of the advancements that we have achieved is that in the last year, our research activity has already focused on the next generation of products, on developing this next generation of products. So the next slides will provide you an overview of where we are today and what we have achieved. Looking at the domestic sector, heat and power domestic production with fuel cells, also for small businesses. Since we presented last year in PRD 2019, we have seen an increase in the market share of 60%. We are now confident to say that we have experience in Europe with 18,000 units. And how we have got here? Early research focused on achieving a track record of performance. Then we moved into providing confidence to the European players and that they could build enough volumes to allow them with confidence to shift to more automated and efficient manufacturing processes. In parallel, some market activation programs at national level, especially in Germany, help to increase the market volumes. And you can see here in the map where the dominating market is Germany. Certainly, thanks to the European support, we have opened up other markets, and Belgium units are now in the order of thousands. If we look at what we have done in terms of research, now our activity has always been to support concrete research and development improvements in synergy with deployment activities. Two main reasons: one, to maximize the impacts, but to achieve those impacts in the shortest possible period. This has allowed, looking at the domestic sector applications, European players to redesign their units, allowing them to be ready for mass manufacturing, to improve performance of components and systems, resulting in increasing manufacturing capacity of key European players, but also on cost reductions of key components like stacks and heat exchangers. Also, help them to redesign units so that they are easy to service, easy to maintain, achieving 40% reductions in some cases on those costs. You can see here some of the achievements in our projects. For instance, significant reductions, outstanding reductions, I would say, on the degradation rate. So today we have large operational hours in our projects. We can say with confidence that we have products continue performing as expected, technology neutral approach, next generation of units already being deployed, and new business models being adopted. Targets for 2020 on the domestic application sector with fuel cells achieved, very large power efficiencies, availability levels compared to conventional solutions, high stack durabilities all the way up to 80,000, and capex targets below 10,000 euros. As you can see on the graph here on the right of the screen, cost reduction goals are being met. We just need a little bit more of volume so that we can get to the values of capex that we believe will be cost competitive without the need of any support. Very important looking ahead, making these units ready for 100% hydrogen. We have already worked in this direction, getting units which are 30% hydrogen tolerance. Now, looking at commercial building and the service sectors, early demonstrations have ended. We have more than 10,000 running hours for a project using biogas for a wastewater treatment plant, above 50% power efficiencies, recover waste heat from the fuel cell to feed the process of anaerobic digestion itself, but we need longer operational experience. We need that. The project has been very useful to showcase that the technology works to potential replicators, but we need more operational hours of this type of units to unlock the market potential that we have in this segment. And this is why we are now preparing the next generation of units that will be demonstrated in some of our demonstration projects, as you can see in here. That will build a track record of performance that we hope will gather further investments to this sector, allowing us well to shift to mass manufacturing, hence getting the cost reductions that are needed. Just as an example of one of the next generation units that we've been working on, the projects have been working on, outstanding results, stack electrical efficiencies of 74%, a lot of work again on manufacturing, getting less components in those systems, getting to points where we believe that by mass production or at mass production, we can get the stack cost at 1,100 euros per kilowatt. Now, some of these units are now being deployed as well outside of our projects, and this is very welcome. Like this is the case of the Innosoft unit that was developed in the Innosoft project that will be presented tomorrow in a smart grid in Finland. Looking ahead even further, if we want, we have the possibility to use solid oxide cell-based technology to, let's say, offer a possibility to the network, to the power grid that will have a large share of renewable energy, of variable renewable energy. One of the concepts that we first were looking at was tree generation with solid oxide fuel cells, generation of hydrogen, heat, and power. We brought this further, and same technology can operate in reversible mode, hence able to listen and to actuate on the market signals in terms of electricity prices. Electricity costs are low. We can generate hydrogen cheaply with the power, with the electrolyzer mode. Electricity costs are high. We can generate that hydrogen, heat and power using a hydrogen-rich fuel. Targets of €5 per kilogram of hydrogen. We are looking at what could be the upscale strategy for this type of solutions. Here we're looking at really tens of megawatts, 50 megawatt plan, 100 megawatt plan. We have a very nice project that will be presented tomorrow in detail, which is the waste to grids in the session Hydrogen Future. At industrial applications, we have a number of applications abroad, projects driven by high renewable power prices. Two main flagship projects that have produced significant results. One of them installed a 2 megawatt PEM fuel cell in China. And very important achievements. However, we still need to get the cost further down. We are working on the next generation of systems, looking at 1,500 euros per kilowatt at mass production. But as you can see, the results obtained so far have already opened up new applications for these systems, looking at maritime, looking at district heating applications, cogeneration, prime power solutions. As we move to the last part of my presentation, we can see in here that we have the possibility to also provide the power needs of remote communities, of backup power, critical infrastructure, as well as portable generation. And we can do that as well through the generation of 100% renewable hydrogen. We have a number of flagship projects here. The remote project is looking at developing, actually for demos, of these power-to-power solutions that will help to decarbonize remote communities in Europe. Flagship project also looking at the use of hydrogen gensets for portable generation in temporary events. Two of these gensets have already been built, and we hope that the current pandemic situation will allow to demonstrate them next year because they are ready to be demonstrated. Remote power as well for applications in critical infrastructure, critical oil and gas infrastructure, telecom towers using solid oxide fuel cell technology. And to conclude, I would like to say that we are mainstreaming now fuel cell technology for domestic solutions. We are moving the market from 100 to tens of thousands. We have the next generation of products already being deployed in real installations. And very important, not only in this segment, but in others, we are developing a very strong, and we have actually developed a very strong solid oxide fuel cell supply chain. And not only that, technology is offered by consolidated heating suppliers as part of their standard heating and power, micropower solution portfolio. Finally, the applications are diverse. We've talked about applications in the commercial building sector, where we will have the demos starting very soon. As well, in the industrial segment, we need further cost reduction, as mentioned, and we hope to see those next generation of units deployed in real environments, both abroad and in Europe, and very important to unlock niche markets like the ones that we've referred to. 100% renewable solutions for remote communities, backup power solutions, genset generations. All of these projects that will be presented tomorrow in the morning session as part of the parallel sessions. Thank you. Thank you very much.
Thank you very much, Antonio. Really, my pleasure again that we were able to show today the many achievements in the stationary application of fuel cells. Many achievements, like I said, just in the last year. So this I also wanted to underline every single time. And now it's again my pleasure to pass the floor to our last speaker from this morning, Alberto Garcia, project officer also in the joint undertaking, overseeing most of the cross-cutting issues. and he will also show to us the achievements in that area of our projects and activities. Alberto, floor is yours.
Yes, thank you, Mirela. Thank you so much for the introduction, and welcome everyone to this last presentation in which we are going to present an overview of the different support activities that we have for the mass market commercialization of these technologies and the market uptake. First of all, I would like to invite everyone to the two parallel sessions that we will be holding tomorrow on education and training activities, but also on hydrogen in the future, in which we are going to present some of the support activities we have with the regions, the guarantees of origins, among others. Secondly, I would like to remark that the mass market commercialization of these technologies presents a number of systemic challenges of horizontal nature that also needs to be addressed to effectively kickstart a hydrogen ecosystem in the next decade in Europe. We are addressing all these horizontal challenges within the cross-cutting issue activity area, and through projects we have been supporting projects in 6 different areas on regulation codes and standards, on education and training, on safety aspects, also concerning social awareness and public acceptance, sustainability and building databases. But as the technologies are approaching to the market, we are complementing all the activities that we are undertaking within the projects with many other activities, such as the activities that are performed by the Regulation Codes and Standards, the Strategic Coordination Group, the set of activities that we have thanks to the cooperation with the Joint Research Center of the European Commission. We have set up a European Hydrogen Safety Panel. We have different initiatives concerning the regions. We have an observatory. We are providing funding and support and financing support services. We are publishing studies. Some of these activities have already been presented by Mirela in the previous session, so I will try to cover the remaining ones. So let's start. On the first area, on regulation codes and standards, we are supporting the development of suitable frameworks and regulatory frameworks for the market uptake, because the lack of harmonized regulation codes and standards is still one of the major barriers for the commercialization of these technologies. We are supporting projects on dealing or performing pre-normative research activities. We are supporting projects like high-law projects, identifying legal and administrative barriers, but also sharing the best practice and recommendation on how to overcome these barriers to have an effective rollout of these technologies. And we have supported the Certified project, which is a pioneer project in order to establish a guarantees of origin scheme so that we have a reliable system about the information about the origin of the hydrogen. The majority of the activities have been focused on pre-normative research, and we believe this is an essential step for advancing regulation standards, and as a research and innovation program is where we can make the most impact. Pre-normative research encompasses pure research activities, but also desk research activities. And what it does is to bring new knowledge, hydrogen-specific and scientifically sound knowledge to update and further develop standards, regulations and codes. We have been supporting pre-normative research on a variety of different topics, from stack testing to passing through materials, pressure vessels, hydrogen quality, metering, refueling stations, just to name but a few. All these projects, all together, they are supporting the development of a suitable regulatory framework along the entire hydrogen chain, from production, passing through storage and distribution, but also on consumption or end uses. And they are also targeting standards at international and in European level. Just to give you an example, out of 5 projects running last year, 80%, 4 projects were addressing international standards at ISO and IEC level, and 1 project was addressing a specific standard at the European level at Senelec level. We have so far, currently we have seven projects, running or performing innovative research. We have 2 projects addressing safety aspects. We have Presley project addressing many safety aspects related with the safe use of liquid hydrogen. We have High Tunnel CS project performing innovative research for the safe use of hydrogen vehicles in tunnels and other underground areas like underground parkings. We have Hydrate project, which is the follow-up of High Cora project dealing with hydrogen quality. And apart from all the activities performing on hydrogen quality and quality assurance, they are establishing 3 laboratories in Europe capable to measure all the hydrogen quality against all the set of requirements imposed on the standards. We have 2 projects focused on stack testing, IT Fast and AD Astra. They are developing accelerated stress testing protocols for PEM and solid oxide fuel cells. And also we have 2 projects dealing with hydrogen and natural gas mixtures. In particular, Higgs projects is bringing new knowledge on the effects of hydrogen injection in the natural gas grid. And Taiga projects is bringing new knowledge on the effects of this type of mixtures on the performance and the behavior of the domestic and commercial gas appliances, end user appliances. Apart from the activities undertaken within the projects, we also have a regulation codes and standards strategy coordination group. This is an industry-led working group within the program steering or coordinating the RCS needs of strategic importance for Europe. The group is composed of Hydrogen Europe and Hydrogen Europe research members with the support of the Joint Research Center of the European Commission and the Program Office. And they are steering the activities within the joint undertaking concerning regulation codes and standards. They are identifying their RCS needs to what is developed, what is needed to be developed in Europe. They are also tailoring the different annual work plans to best address those needs. They are making proposals for standardizations toward the annual Union work plan on standardization of the European Commission. They are contributing to ensure that all the results of all these PNR projects are really taken over into the regulation codes and standards development. And they are somehow also trying to enhance the European participation in the RCS fora. Related with this, but with a wider scope, we also have a set of activities thanks to this cooperation with the Joint Research Center. They are helping us throughout the entire program. They are supporting us on RCS matters. They are helping us on safety aspects. They are helping us with the program monitoring and assessment. And I will not talk much now because in the next presentation, in the next session, Evelyn Weiner from the Joint Research Center will present an overview of all the activity that JRC is performing to support the market uptake. Moving on, next, education and training. We are promoting education and training programs because we need a well-educated society for the mass market market commercialization of these technologies. But also we need to prepare a well-educated workforce for this growing industry. We are supporting projects developing educational and training programs tailored for different target groups, from technical professionals, regulators, and public safety officials, first responders, technicians. We are developing a platform for connecting all this knowledge. We are also supporting the development of our European network of universities. And all these education and training programs, they address different levels of education and types of education. They include different formats and also different features. Right now, we have 4 projects running dealing with education and training. One of the FCH Go projects is focused on primary and secondary education. They are developing what they call a ready-to-teach toolkit so that every school could use this toolkit to teach about hydrogen and fuel cell technology in primary and secondary. We have Teach High project focused on university level. They are developing a blended master course on hydrogen and fuel cell technologies. We also have a project, NetTools projects, dealing with distance learning with a component on e-education, but also a strong component on e-laboratory, developing a nice, a comprehensive set of tools for performing assessment of fuel cells and hydrogen technologies, but also safety assessments. And in 2020, we have launched a follow-up of High Response project. The name is High Responder, which is developing a training program to train the trainer of first and second responders. And just to give you an idea, since we are keeping a record since 2016, we have been able to train more than 3,000 people in 11 countries and in 7 different languages. If we continue, yes, safety is paramount. We need to have a safe deployment of these technologies in the years to come. And we are addressing safety from multiple perspectives. We are addressing safety through innovative research projects, through education and training, but also we are supporting projects on addressing key safety-related aspects. We are supporting projects on hydrogen sensors. We are supporting projects on CFD or safety analysis, and we are also supporting projects to establish expert groups. And in that sense, 3 years ago, we have set up an European Hydrogen Safety Panel, which is a group of experts which are helping us to ensure that hydrogen safety is adequately managed within the projects, but also at project level, at program level, and they are also contributing to promote and disseminate a high-level safety culture within the program and beyond. The group is composed of 14 experts in 2020, and they are providing services at project level, at program level, concerning data collection, and also on public outreach. At the project level, they have published last year a reference guidance document on safety planning for projects. So all projects, they have this reference document about how to plan safety within the projects. They are starting to assess key elements related with safety within the entire portfolio of projects. They are organizing a workshop with a set of projects involving the similar technology. At the program level, they are about to finish the multi-annual work plan, in which they are going to set out somehow the framework for the activities of the panel in the years to come within the program, but also at international level with international stakeholders. Concerning data collection, last year they released a report on the lessons learned and the findings coming out from the hydrogen incidents and accidents database. And on public research, they are about to finish a communication strategy which involves a revamped website and a first set of frequently asked questions related with safety aspects. Moving on social research and public awareness, we're trying to gain a deeper knowledge on the social and economic factors around these technologies, and the best reference I can give you today is the Still Hyacinth project, in which they performed the biggest exercise ever on social research around these technologies in Europe in order to understand the acceptance, the perceptions and impressions of stakeholders, but also the general public. They did a survey involving 7,000 participants in 7 European countries. They did also a survey on key stakeholders from the private and the public sectors. They did interview with the stakeholders as well, and they put all this together, all this information in 2 public reports. So if you are interested to know what the general public thinks, or what key stakeholders working on hydrogen fuel cells technologies thinks about these technologies, please have a look at the 2 public reports. They are publicly accessible and accessible free of charge. Moving on, I'm running out of time. We also have a set of activities dealing with sustainability in order to ensure that the technologies are environmentally friendly. We have been supporting projects dealing with life cycle assessment on recycling and dismantling technologies and the guarantees of origin, as I mentioned. With last year, with the Joint Research Center, we have reviewed how projects are applying life cycle assessment tools, and also we have a workshop with key experts in the field to assess how this is being done. And thanks to this, in the next year, we are launching a new project in which we are going to provide updated guidelines on life cycle sustainability assessment. We are going to launch a project in order to validate and to develop the recycling technologies for these technologies, and also to provide guidelines for the eco-design on fuel cells and electrolyzers. And last but not least, on databases, we are supporting the development of advanced databases to concentrate on the information in one place, but also so that everybody can find the information easily and seamlessly. We are supporting databases on legal and administrative processes, on education and training, and also on safety aspects. We have also our own database, Trust Database for technology monitoring, and last year we launched the Observatory, which is meant to become the one-stop shop for a lot of information about the technology, publications, patents, financial support, and over the program review days, we are going to launch a new module on education and training. So, in conclusions, pre-normative research, safety, education, sustainability, all these are cross-cutting aspects which are essential for mass market commercialization. Cross-cutting projects and other support activities are really contributing to have a safe and frictionless deployment of these technologies in Europe, and altogether they form a comprehensive portfolio of activities strengthening the whole sector and supporting the market uptake. That's all from my side. Thank you so much for your attention. Mirela, back to you.
Thank you very much. Thank you very much, Alberto, for your presentation too. And again, as you have seen, many achievements also on the cross-cutting type of issues, on education, on training, on pre-normative research, input to standards, ultimately. It is my pleasure now to really introduce our last speaker from this morning session. And she is a very old colleague of ours. I have to say, I remember with pleasure when we started together in the joint undertaking. But then she moved to the Joint Research Center, and it's even more greater pleasure for me to work with her from that position, where she is supporting us with all her colleagues in the Joint Research Center with this review every single year. So my pleasure to introduce today Evelyn Weidner, Scientific Officer in the Joint Research Center. Evelyn, floor is yours.
Yes, good morning. Thank you for the very kind introduction. So it's also a pleasure from my side to be here and to have the opportunity to give a short overview of our activities under the framework contract. So let me figure out that I can advance the slide. It works. Okay, so there is a contract between the FCH JU and the JRC, which is covering activities that are then planned on an annual basis. These activities are agreed between the JRC and the Program Office, Hydrogen Europe and Hydrogen Europe Research. In line with the JRC's mission, these support activities are in the area, as already mentioned by Alberto, on RCS strategy, harmonization of testing protocols, safety, and on technology monitoring and assessment or knowledge management. So in this presentation, I will give a short overview of our activities under the contract this year and also provide a quick outlook on what our plans are for next year. Next slide. So a large share of our activities under the contract are related to knowledge management. And on this aspect, we are, of course, in very close contact also with the knowledge management at the Program Office. We are monitoring the evolution of selected key performance indicators from the start of the joint undertaking under FP7 in order to track progress of the program. And there are several ways we are doing this. So, for example, on an annual basis for the program review, this has already been mentioned, and I will say a bit more on the next slide, but also we're doing this for specific technologies. So this assessment then shows how successful the program has been in advancing the state of the art of these technologies. And the purpose of this exercise is then also to reveal any potential R&I gaps that then can be covered in the future. So these reports are called the historical analyses, and they have been done for now for stationary fuel cells and electrolyzers. And this is covering over 100 projects in total. The assessment is based on data submitted in trust and also on project deliverables. This analysis is then also complemented by data on patenting. But as some of the data are submitted in trust and also quite a few of the project deliverables are confidential, we cannot make the full report public, but we are working on publishable versions which should be ready in the coming months. So again, on the topic of knowledge management. Since 2016, JRC is performing the annual review of the program to see the impact of projects and the progression of the program towards its targets. And this review is carried out by a team of experts at the JRC who are assessing the project portfolio against the key objectives of the program. And yeah, as Mirela mentioned this morning, the 2019 program review, the public version, has just been published. So this year, the JRC has also been involved in the target setting process for the next framework program. So in order to support this process, the JRC has proposed a methodology. Oh, my slides have disappeared. There they are. So a set of guidelines, and the emphasis of these guidelines is documentation of the process and to ensure a coherent, systematic approach with high quality and traceable input. So this methodology is then used in this ongoing process. In 2018, JRC has begun to look more closely at all the LCA deliverables that had been submitted so far by projects. And it did turn out that different methodologies were used. And following the same methodology is important, otherwise the LCA output will not be comparable. So this issue and how to best deal with it was then discussed further in an expert workshop in 2019. And the experts recommended that clearer guidelines are needed, and they also said that more effort should be put into ensuring availability of primary data sources. The outcomes of the workshop also helped to clarify what activities are needed to improve the situation, and this also enabled us to give some input into the annual work plan 2020 call topic on LCA. And also given the relevance of LCA for technology monitoring and assessment, JRC is planning to put more resources into this topic. And this will then also help us to better support the increased focus on sustainability of the Clean Hydrogen Partnership. On another topic, it's advancing. On media monitoring, this is also something JRC is supporting at various levels. So there is the FCH media monitoring system, which is regularly maintained. There is help desk support. JRC is working also on categorization, monitoring, and improvement. There is a weekly monitoring of the results in various categories and a monthly newsletter preparation together with the program office. And also has been already mentioned this morning, tools for innovation monitoring. So this tool allows to measure and represent the evolution of the technology. So aspects that can be measured are publications, participation in projects, and patents. So for the FCH JU, it can be used, for example, to visualize collaborations and also to track output of beneficiaries. So this year, again, new technology spaces have been created, and there has been much effort on data cleaning. So maybe you can see above Asian characters, these pose quite a challenge. So the results of the FCH JU adapted TIM datasets have already been included in a number of publications, for example, the historical analysis, and also in the presentations produced by the program office and the JRC. And this tool is available for all stakeholders. So JRC is also supporting RCS at strategy level on terminology and harmonization of testing protocols. So for the testing protocols on for low temperature electrolyzer, already shown this morning by Nikas, a report summarizing the outcomes of the expert working group has just been circulated for stakeholder comments. This report is somewhat delayed due to current situation, but also because an extensive revision was performed to ensure high quality of the document. The scope is from cell to system level, and it incorporates results of the project quality bits. On RCS strategy, JRC has contributed to the overall effort, which has been already been explained in more detail just earlier. And another aspect on RCS, on the harmonization of testing, JRC has developed our hardware to minimize the effect of the testing device on the results. So this design has been shared and has been tested, and currently there are some efforts ongoing to iron out some difficulties that arose due to manufacturing. So this design can be made available to the community, so please contact us if you're interested. And on the next slide, so on hydrogen safety, JRC is operating the two safety databases, Helen, which is a confidential repository for events that might occur during the FCH JU project, and HYA 2.0, which is a public database. And together with the European Hydrogen Safety Panel, JRC has contributed to the improvement in event reporting. So JRC is supporting improving the quality of the descriptions, and also in terms of quantity, just adding more events. Yeah, so this brings us to a more general outlook of the activities that are planned for next year. So the main lines will largely stay the same as in the previous year. JRC will continue to support the target setting process for the next framework program, and will also deliver another historical analysis, this time for onboard storage. Another annual program review is planned, and EMM and TIM will also continue to be developed further. A new aspect is an increase in focus on assessment of sustainability of hydrogen technologies, and on RCS, depending on the decision of the working group, harmonization of testing protocols for high temperature electrolysis will be supported by the JRC. And on terminology, the terminology report is due to be finalized this year or early next year. And JRC will also continue to support RCS at strategic level. That already brings me to the end, and now back to you, Mirella.
Thank you very much. Thank you very much, Evelyn, for your nice introduction and your nice presentation too. I know we are running out of time, and we have received multiple questions in the chat, which I continue to encourage you to do. And because of that, I will just pick few of them just to answer myself quickly to you. And for the technical ones, I will also encourage you to follow the parallel technical sessions where you can have a bit more time to pose these questions. So quickly, you have asked multiple of you about the studies that we are producing, which are the links. You can always go on our website, and in the studies headline tab, you can find all the studies that we have produced. Of course, the track study, again, the results will be presented tonight. So please stay in and follow us, because tonight the results of the track study will be there for the aviation and for the national energy and climate plans opportunities. These are always on our website. Another question was if these presentations will be available. Of course, this presentation will be available later, most probably as of next week. Again, follow us, register, subscribe to our website, to our news, and then you will know when the presentations are online, for example, or when any study is published. And finally, I will pick just the third question as relates to our next work program. As you may know, European Commission, together with our private partners, are currently discussing about next clean hydrogen partnership in the next Horizon Europe. And again, I will invite you to stay tuning in for tomorrow for the closing session, when you will hear more. And my expectation, and here I'm talking as in my personal nature, my expectation is that the next program, the next work program, should be available somewhere end of next year. So with that, I hope I answered to some of the questions. Again, for the technical one, please go follow the parallel sessions, and there you may have more time to put questions and to get the answer. And I would like again to thank all the speakers, to thank all my team. I'm really proud about the whole team, and you will see them throughout the whole week, but in particular today and tomorrow, all the project officers, the knowledge management team who's behind helping with all the numbers, with all the fact-based information, but not the communication team. You cannot imagine the work that requires such a virtual event, and they are here together with us day and night. So really, thank you very much to the whole team, and let's have a wonderful week. Thank you very much.
Ladies, gentlemen, good morning. Welcome to the session on hydrogen cars, hydrogen buses, and hydrogen infrastructure. The session will last 1 hour and 20 minutes. There will be presentations done by 4 projects, 2 of them on cars and 2 on hydrogen buses. You will be able to ask any question you feel at the end of the entire set of 4 presentations. These projects have been chosen because they are, in fact, the flagship project in terms of hydrogen for transport application within the FCH. And without any further comments, I kindly invite for project Jive 2, Ms. Madeleine Ojakovo from Element Energy and Mr. Jens Konrad from RVK, Transport Operator in the region of Cologne. The floor is yours. Thank you.
Thanks very much, Lionel. I think good morning, everybody. First of all, my name is Madeleine Ojakovo. I am the coordinator of the Jive Fuel Cell Bus initiatives. As Lionel said, these are the flagship projects for the fuel cell bus deployment in Europe. So to tell you a little bit of background about the Jive projects. They're a pair of sister projects made up of Jive and Jive 2. And the main goal of the project is to commercialise the market for fuel cell buses in Europe. So the projects started in 2017 and 2018 for Jive 2. And the goal is to take the technology from the tens in scale to the hundreds by the early 2020s. Jive is made up of over 50 partners and has a total budget of 217 million between the 2 projects. And this includes 57 million in FCH JU funding. In terms of a summary of the project, Jive is a truly pan-European initiative. There are 19 countries involved in the projects overall, either as deployment sites or as observer regions. As I said before, Jive aims to stimulate the fuel cell bus market. So to do this, we will deploy 291 buses and accompanying infrastructure across the 18 sites in the project, which are across 7 countries and involving over 20 European public transport authorities and operators. So not only is this the biggest collaborative initiative attempted to date in terms of procurement for fuel cell buses, it's also critical as it allows new cities and regions to trial hydrogen technologies, and it can act as a starting point for cities to increase the rollout of other vehicle types, including trucks, vans and cars, by ensuring that the buses form the start of the regular demand use for the hydrogen infrastructure in the local area. So, in terms of project progress, we are now 4 years into the initiative. The majority of the buses have been ordered. There's 230 currently on order, and 47 are now in daily operation as part of regular bus services across Europe. We're expecting to have every single vehicle ordered and 100 on the roads by Christmas. So it is clear that the Jive projects are directly responsible for stimulating the fuel cell bus market. We now have 14 European manufacturers offering fuel cell bus products, either urban city buses, articulated buses, and double-deckers, with further diversification of models expected in the next 2 years for applications such as coaches. The projects have also outperformed in terms of the economics. The graph on the right shows how the capital cost for the fuel cell buses has come down significantly within Jive. We've been able to outperform expectations that we had at the start of the project, getting prices for the capital cost of the vehicles below the project target of 650,000 euros per bus, and even below the FCH JU multi-annual work plan target for 2023 of 500,000 euros per bus. So this is, of course, extremely encouraging for the future of fuel cell buses. But of course, there's still work to do to compete with battery vehicles in terms of the cost. Although fuel cell buses are, of course, able to outperform their battery counterparts in terms of range and in terms of flexibility. We're expecting to see the cost come down through other projects and initiatives to scale up buses to the hundreds per operator and the thousands of buses across Europe. So, of course, we're still early on in the project phase, and we're seeing some strong operation and strong performance coming from the buses that are already in operation. But I'm going to hand over to Jens Conrad from the Cologne region, who can tell you more about the buses in action. Thanks, Jens.
Well, thanks a lot. I hope you can see my slides. As mentioned, I work for RVK. We are one of the biggest partner in the JIVE project. Just to give you a short idea who we are and what we're doing, as mentioned before, we are a regional public transport operator, and I think that's quite important to notice when we speak about fuel cell buses, especially about the advantages that we see, especially in regional public transport. As you can see here on the right-hand side is a graph of our area in which we operate, and especially you can notice that we are talking about a very large area in which we're operating. So early on, probably some 10 years ago, RBK decided to reduce emissions, to ideally avoid emissions in public transport. We did this technology open, but as you can see, we always have to keep in mind that we are operating in a large area, and that we do have to keep in mind that our buses travel at least 250 to 300 kilometers per day, and that we need the flexibility that Madeline just pointed out. So even though we did this technology open early on for us, it was clear that the only chance or the only technology fitting for us is fuel cell bus technology if we want to replace diesel buses like for like. So it was our idea to replace really one diesel bus with one alternative bus solution, and that is, in our case, definitely fuel cell buses. As you can see here, we started early on in 2011 already with deployment of the first buses. Back then, the situation was way different than it was described by Matt, and just there was hardly anybody on the market, hardly any big OEM offering these buses. But thanks to the projects funded by FCH JU in particularly, we now have a way better market situation. We now have actually not the situation that back then in 2011 we had to deploy prototype buses. By 2014, as you can see, we deployed started another demonstration project. But it was important for us to do the next step, which is a mass deployment of fuel cell buses to deploy the 20, 30 or more buses in our fleet. And the JIVE projects exactly enabled us to do so, because that's exactly the aim as described by Nathan of JIVE. So what we are doing right now in Cologne is we are building up a fleet of 50 fuel cell buses, and we are setting up 2 new refueling stations, all funded by the FCH JU. So right now we have already 35 of these buses in service. The other 15 are ordered. So the 35 buses were deployed procured under the JIVE project. The additional 15 buses JIVE 2, that's why there was a slight delay in there. The first 35, the Europe-wide tender was won by Van Hoel. The 15 additional buses are ordered from Solaris, and the delivery will start probably even end of the year, as you can see on the slide, maybe at the beginning of next year, but we are well on track here. To put it in a nutshell, as mentioned by Madeline, we see huge advantages regarding the fuel cell bus technology, especially from the view of a public transport operator in deploying the buses in the region. It's not just the buses itself, it's hydrogen as a fuel and even as an energy carrier, which is, you can produce it locally, which is important, and we have it environmental friendly. We have the advantages which are very important for us. We have the ranges, we have the flexibility and the refueling time, which do match diesel buses already today. And again, to slightly toot our own horn, by now we have already 37 buses in service, and with that we have the biggest fuel cell bus fleet in Europe so far. Thanks a lot.
Thank you very much, Madeline. Thank you very much, Jens. it was very inspiring to hear all these good achievements from JIVE and JIVE 2. And in fact, we are looking to present to you next year more operational data. What is the consumption of the buses? What is the availability of the HRS as their deployment and operation will go. Now we go for another project, not supported by the FCH, but supported by CEF, Clean Europe Facility. The name of this project is H2 Bus. And if you want, it is the successor of JIVE and JIVE 2. It is the next step. JIVE 2 combines the 300 fuel cell buses, and H2 Bus aim at, depending where you look the number, but for 600 up to 1,000 fuel cell buses. I give the floor to the coordinator of H2 Bus, Mr. Lars Jacobsen from the company Nel. Lars, the floor is yours.
Thank you very much. I can see that you can hear me. So I'm here to present today on H2 Bus Europe. As Lionel stated, I'm Lars Jacobsen. I'm the sales director of the company Everfuel. So Everfuel is basically the company holding the entire H2 Bus project. Just to give you an idea who we actually are, Everfuel is a dedicated green hydrogen company. So we basically handle all the hassle that you've been doing in the projects leading up to H2 Bus. So we take care of the entire hydrogen value chain, make sure that you have hydrogen available. We have a legacy in Nel where we saw and were part of the development in the hardware, so we know that works. That's both on the electrolyzers as well on the HRSs and the stations. So we have a really good idea on that, and what we saw was that in some of the projects that we've seen already, as Jens and Madeline described some of them, it has been quite a challenge to make the HRSs effective and also bring down the price. And price is key to making this work. As Madeline said, there's quite an intense competition with battery electric buses, especially coming from China. So we needed to be very focused in order to do that. Everfuel is a relatively new company, but we've been quite successful, and we're currently listed on the core market in Oslo. So the clicker should work. So what we basically do is we offer an all-inclusive, and that's taking care of installing the station and also taking care of the green hydrogen delivery throughout the period. And the customer only pays per kilogram, so we take care of setting up exactly the one-to-one replacement with diesel, but it's not diesel, it's green hydrogen. With this relatively, as we see it, interesting approach to the market, we were looking to something that could really make the business case work. And what was quite interesting there was the bus segment. As Madeline stated, it's one of the interesting segments because it's a public entity that you're dealing with. Public entities, they tend to pay the bills. It's long-term contracts, and for those of you who don't know, capital investments in hydrogen is quite high. So we need to have some long-term perspective, as well as a lot of hydrogen to depreciate the assets over in order to become competitive. We could see that was something we could need, but we could only handle part of it, and that was the hydrogen, and that was why we wanted to do a joint and a coordinated approach with other partners in order to also move the bus segment. So that was why we did the H2 Bus project and consortium initiative. We ran around Europe and talked to partners who were in the value chain already, and we ended up with the most ambitious in that time in order to make this a competitive scenario. So it is basically consistent of Nel on the electrolyzers, producing the hydrogen on green basis, also producing the station modules that we will implement as a company on the depots. It's Hexagon. Hexagon produces the vessels on the bus as well as vessels for transportation. It's Ballard on the fuel cell. It's RISE as a fuel provider. They are a UK-based company, and that's because we have a branch of H2 Bus in the UK. It's ourselves as a company, and then all these great initiatives led to a OEM partner, being Wrightbus, who were the ones who were most, it's called aggressive on pricing and on the offering. So as Lionel stated, we are not funded by FCH JU, but by the Connecting Europe facilities. That's basically an infrastructure program. So there was a specific call under that for innovation, and we successfully received what was at that time the biggest hydrogen project in Europe. It was a funding of 39.5 million euros. And that goes for both the production, so that's the infrastructure, as well as the infrastructure on the depots, and for the up to 600 buses, as Lionel stated. The ambition was to drive down the price to roughly 350,000 euros for the bus, also with attractive consumption and also service and maintenance. With the scale, we can see that the hydrogen price can also be attractive. As Madeleine said, there's been quite a success in driving down the price. So the economics of scale are familiar to everyone, I think. In the beginning, a hydrogen bus was quite expensive. It cost roughly €1 million, but that was when you did one or two. Then Three Motion was successful in the 850,000 region. Jive and Jive 2, as Netherlands say, now in the region of 600. But what we could see is that if we go coordinated and go for even larger volume, especially with one OEM, so they can produce it more serious production, then the price could come down even more. And our target was the 350. And with the up to 1,000 buses in H2 bus, we could see that that was possible, because you could then see some serious production on the bus. And there was a growing concern also on all the deliveries of the parts, which the ambitious partners had dedicated the attempts to bring down the price. So that is below 400, and it's approaching the 350. And how we're doing this is, we know that the first bus will be more expensive than the last bus. So we talked to the different OEMs and said, these numbers are indicatives. We are aiming to roll out a lot of buses in the same project, and we would like to have the best possible price. Okay? As you know, the first bus is most expensive, the last bus is less expensive. And we then asked to give an average price over the project, and we would then secure the framework with this OEM. So basically, that's the function of the cost. That's the blue line. The orange one is then the average price from the OEM on the offer. And the gray line is then what we have reduced the price to using the funding within the CEF project dedicated to the buses. And what is really interesting is that if you look at the gray line and the blue line, in the end, the blue line is lower than the gray line, which is the offered price. So it will be a sound and sustainable low price, which is what is really key to making this work also in the long term. And what are we doing here? We are looking at scaled and focused rollout. So we're looking at 3 clusters. So it's UK, it's Denmark, and it's Latvia. So it's up to 200 buses in each location. The scale is key to bringing down the price. We can see that it's successful. Currently, we are bidding with the solution in different tenders. So it's not a demonstration project like the previous one. So we have a heads-on competition with battery. But the scale is key to making this work. And if we get this first and interesting long-term contracts going, this will also benefit the other sectors, as Madeleine stated. So it's the unlocking of trucks, it's trains, it's maritime, and it's all a matter of just getting started, because the beauty about hydrogen is that it scales fantastic. So it's the first demand that's key to making it work. So let's make hydrogen happen, and you can contact me with any questions. You know?
Thank you very much. Thank you very much, Lars. Message well received here in Brussels. It's very interesting to see how H2 Bus is indeed pushing the technology towards a more business model with this view of centralized production of the hydrogen. It's excellent. I hope that there will be questions. And as a refresher for the audience, in fact, you can ask questions thanks to Manymeter, that's the platform where you could ask a question on live. Perhaps a comment for the next speakers. Allow yourself a bit more time. The session is planned to last until 12:20. And so you could allow to explain or go into the details. What I forgot to mention as well in the introduction is that for some projects, I have identified two speakers, one coming from the coordination entities and the other being either the operator of the buses or the taxis, to give, let's say, the deep perspective from the end user of the hydrogen vehicles. This is finished for the hydrogen buses. If there are questions, we'll take them at the end. And now we do a shift towards the hydrogen cars. Again, two projects. First one is H2ME, H2ME2. The two speakers are Mr. Peter Speers from Cenex and Mr. Benjamin Jödecke from Hydrogen Mobility in Germany. Peter, the floor is yours.
Thank you, Lionel. Good morning, everybody. As Lionel says, I'm Peter Speers of Cenex, and today myself and my co-worker Benjamin of H2 Mobility will talk to you about the Hydrogen Mobility Europe, or H2ME project. H2ME, as you can see from the slide, is a large and ambitious project involving almost 50 partners in 8 countries. It originated from a 2014 call to support territories where there is a strong political commitment to deploy ambitious and innovative hydrogen transport projects. And this is explained better on the next slide. H2ME is essentially a brand that brands 2 projects, H2ME 1 and 2. They run to the project runs to 2022. And H2ME aims to deploy over 1,400 passenger car and light-duty van fuel cell vehicles and 49 hydrogen refueling stations in 8 countries. It is the FCH JU's largest light-duty vehicle deployment project. As Lionel says, it's a flagship project. It explores several fuel cell vehicle use cases. They include individual passenger cars, so individual cars to individual people, vans in captive fleets, and importantly, high mileage end usage applications such as taxis and police vehicles. So real world applications with real end users. The overall aims of the project, and this is my take on it, are twofold. It is to demonstrate that these vehicles and refueling stations can do the job of conventional equivalents. And it's also to provide an evidence base to help the larger European efforts to commercialize the technology. So I'm hoping you can see an animation on the left-hand corner developing here. And this helps to explain what we've achieved so far, summarize what we've achieved so far. As the animation shows, the project has achieved an impressive evidence base of fuel cell vehicle and hydrogen refueling station performance across 8 countries from 2015 to 2020, where we are now. We've continually rolled out vehicles and hydrogen refueling stations over the time of the project. The graphs on the right summarize this and show that the vehicles have driven over 15 million kilometers in those 6 years, and the hydrogen refueling stations have dispensed over 165 tons of hydrogen. One thing to note in the graphs on the right is the significant growth in distance covered in hydrogen dispensed since late 2017, and this coincided with the deployment of taxis and police vehicles in France, Germany, and the UK. So it seems almost obvious to state it, but the best results here and the best business case, and I think Lars referred to this earlier, you put vehicles where there are users, you'll get usage. It's kind of self-evident, but it's really important to state that. The evidence base accumulated by H2ME is now at least equivalent to the large-scale US Department of Energy deployment programs that have been going on since 2010. And this is despite some delays in deployments, as the slide shows, particularly in vehicles. And obviously, as Lionel will hopefully attest, we're working hard to correct that. of things we could talk about that we've learned and continue to learn from such an accumulation of data. Today, because of time, I know Lionel's given me a bit more time, but I can only work with the time I was given. I'm going to focus on one aspect of what we've learned, and that's about the reliability of hydrogen refueling stations. And this is a key aspect in building confidence in the technology so that we get the rollouts of vehicles and hydrogen refueling stations that we're all looking for. And this aspect of confidence is something that one of my co-workers, Sophie, will touch on in the next presentation in Zephyr. The graph on the left shows that the project hydrogen refueling station reliability improves steadily after initial teething problems as more hydrogen is dispensed by the station, and eventually it reaches a steady state, a flatter point on the curve. But even though there are still issues, they are fewer and they're generally fixed more quickly. And this picture of an initial period of more problems, a middle period of kind of flatness, and then possibly an end period, an end of life period where the reliability of the station decreases again as components work out, is known as the bathtub curve. You get this initial steep curve, a flatter portion, and then say at end of life, that curve will rise again. As a consequence of these learning effects on all the stations, the right-hand graph shows that even as the project has continued to add refueling stations to the portfolio, and even though some stations exhibit relatively poor reliability in any given quarter, since 2018, the average availability of the hydrogen refueling stations in the project has reached a steady state value of around 95 to 96%. So, this final slide that I have shows that even though there are many stations that are exceeding the availability target of 98%, the overall project average remains below that. So what are the remaining issues that are causing this downtime? This slide summarizes some H2ME work in this area. There is a well-known saying from management consultant Peter Drucker that what gets measured gets improved. And I guess that's the whole point of these demonstration and deployment projects. The left-hand pie chart here shows station downtime categories reported according to the highlights framework, which was a framework devised in 2011 to kind of provide an overall reporting framework for all the FCH JU's work. And what we see on that pie chart is that we see a lot of downtime reported according to the 4 categories of the highlights framework. And what we saw as the project proceeded, particularly as I showed in the previous graph, we got more usage in the stations and vehicles. We were seeing increasing amounts of category F failure reports, and category F is a kind of catch-all other. And obviously that wasn't very satisfactory. You kind of, category A is dispensers, category B is compressors. Knowing about this helps us improve the technology. But when people report failures as other, that was kind of problematic because we're not really learning anything from that. So we went back to the hydrogen refueling station providers to discuss this. Eventually, it turns out that many of these category F other failures were actually down to pre-cooling issues associated with 700 bar T40 fueling. And because that's a kind of a facet of modern hydrogen vehicles, they weren't really considered in the highlights framework. So what we did in the graph on the right shows this. We recut the data using an additional category G for cooling or chiller downtime. And this now shows that compressors, dispensers, and chillers are the main sources of hydrogen refueling station downtime. This is much more useful information for the FCH JU, but also for the OEMs, because they can now understand the areas where they should focus their efforts in improving the technology. And it's important to say, I mentioned the large-scale demonstrations in the USA, the National Renewable Energy Laboratories demonstrations funded by the US DOE. They also find the same results. The majority of their station downtime is down to compressors, it's down to dispensers because they're the ones that people deal with. And it's also down this pre-cooling, this chilling, has brought in another failure mode that perhaps wasn't envisaged 10 or 15 years ago. So having provided that evidence base, I'm now going to hand over to my co-worker Benjamin of H2 Mobility, whose stations in Germany form the largest grouping in H2ME. And he's going to talk about how his organization is going about continually improving the technical performance of hydrogen refueling stations and, importantly, the customer experience of using them. So over to you, Benjamin.
Thank you, Peter. I hope everybody can hear me quite well. Yes, I will give you brief outlook on what H Mobility has done in Germany regarding hydrogen infrastructure, but also touching the remaining challenges of especially the infrastructure being ready for light commercial vehicles around 700 bar. And as you have touched already, the issues we were remaining during operation, those of course continue, and also different parts. And one topic I really want to touch today is the back-to-back performance for the applications. But yes, H Mobility, who doesn't know us yet, we are providing, I would say, the backbone of the infrastructure here in Germany, and are to date the biggest operator of hydrogen infrastructure in the world. We are operating 88 stations in Germany current to date, and also now acting as a partner for others to operate hydrogen refueling stations, but as well as also installing new ones as kind of a service partner. That's exactly what I wanted to say. We are getting to almost 100 stations in operation in Germany. Of course, mainly funded by the H2ME, mainly funded by other projects or funding programs within Germany. And we have reached a technical capability, I would say, or capacity of around 40,000 cars that could be served by the infrastructure current to date. And we in Germany have around, to date, 1,700 bar vehicles on the road. And this is all public infrastructure, mainly serving 700 bar. We have, of that 100 stations, around 10 stations can serve 350 bar. But so this is public 700 bar infrastructure that you can see here. So one point I really want to make here is that we need more cars, and our infrastructure can serve more cars in this current stage. But as you can clearly see here, also this is a coverage focus, H Mobility focus. So we try to bring hydrogen refueling stations everywhere into Germany. So you as a customer, especially when you have a passenger vehicle, that you can travel wherever in Germany and can be served with hydrogen. But as Peter said before, of course, the high utilization is where there's a clear customer around one hydrogen station, and he's always refueling there. But of course, this here with H Mobility, we try to kind of bring them both together. On the one side, a coverage focus, but on the other side, we also looked at trying to bring more and more stations into closed city regions. So it's very attractive also for customers to, of course, use their vehicles regional and also achieve redundancy, which is another important thing. One thing we found out that, sorry, this slide is always showing a little difficult, but that we can reach with this 100 stations, we can reach around 6 million drivers in Germany already today with this infrastructure. So it clearly states here we have I would say, more or less a problem of the availability of cars on the 700 bar market, especially also in terms of light duty vehicles. And of course, the price is an issue to get closer to customers that can afford those vehicles. But I want to give an outlook, especially in this light duty vehicle infrastructure. And as you can see on the top, this is the stations we kind of have built in the last years with a focus on coverage. So small stations, I would say low capex, that can dispense up to 200 kilos per day. And they have a back-to-back performance that is limited, as you can see. A light duty vehicle with around 5 kilos of hydrogen, you can do back-to-back refueling, but there is time that the compressor and the high storage pressure tanks need to recover in order to serve those vehicles. And this is especially crucial for fleets that are operating regional and are sometimes coming in very narrow windows where they are refueling. So, we are in close contact with for example, our German Post here in Germany to talk about, using hydrogen in fleets, especially where there's a lot of driving range every day, and they operate in very small refueling windows, and the infrastructure has to serve those applications. That means within 1, 2, 3 hours maximum, a fleet of 20 to 30 cars has to be refueled. And this is, of course, a challenge for the fuel station itself to achieve those back-to-back performance. And we are working quite eagerly to achieve that. But of course, this is what drives up the capex of those stations. But as you can see in this second row here, this is what we have to be able to achieve. So we have to be able to achieve back-to-back refueling of each car, plus also simultaneously refueling, so that you can, fuel up a fleet of 20 to 30 cars in 1 or 2 hours. And that said is to combine this also with the availability of 350 bar refueling. As we can see, the heavy-duty transport sector, or also the medium-duty transport sector, is growing. So a hydrogen refueling station in Germany can be able to achieve all kinds of refueling standards, and you as a customer don't have to worry about if you're going to get your hydrogen in every car filled at that station. And of course, the bigger stations for then really the trucks that are going long haul. This is all in discussion for, I would say, a later stage, and this is what no of the stations can serve at that moment. And yes, this is the task we as H Mobility have to also look into for the future. And just want to briefly touch the main challenges here. Ongoing with this upgrading the infrastructure for this fleet, but also new stations, and it's mainly it's also a matter of space. At the moment, we are positioned at normal refueling stations, so at a Shell or a Total or an OMV. But we have a small space, but coming with this intensified back-to-back performance and this also dual refueling, we need to look at spatial requirements that we have at refueling stations. Of course, we need to look at where do we store all the hydrogen that we need to serve during a day. So as I said, 200 kilograms a day, that's what the refueling stations can serve at the moment. But we are looking into projects where we are fueling a ton a day, and you also have to store that somewhere. So this just gives you a brief outlook. And also on the left, you can see the map that not all stations that we have currently in operations can serve this. We cannot upgrade them, so we need new positions of those stations, and we have to build new stations in order to achieve that. And one last topic I want to touch is that we are seeing that in order to overcome those challenges, digitalization can help a lot. We have an app that shows you the availability status. It's called H2 Live, and can guide you to those stations. But of course, we are working more in depth to get all the data from different stations over different station providers, and that can be key to combine all those factors. So the customer with the data from the stations, and of course the system the fleet is working on. So in order to get them all together to make it I would say a satisfactory good, this mobility with hydrogen. And we face the challenge of course, this is there's an investment needed, but from the customer perspective, the return on investment is very, very low at this moment. So we are facing here that we need also support in this terms of digitalization in order to overcome all those key challenges we are facing with the hydrogen infrastructure in the future. So this is from my side, and happy to every question later on.
Thank you, Benjamin. Thank you, Peter. It was very nice to have both presentations, one focusing mostly on the infrastructure, the other one on the vehicle. Just to come back and said by Peter is saying a lot of important things, but this one in particular, he said, what get measured, get improved. We need data. We need to collect the data from the cars and the infrastructure to analyze this data. So then later, this could bring benefits in terms of where to locate an HRS in the best place so that the taxi fleet, for example, will not lose time for the refueling of the vehicle. When it is the best time to do the maintenance of my hydrogen refueling station, how can I improve the consumption of hydrogen within the cars, electrical consumption within the HRS, and so on and so forth. Data is absolutely key. Plus, ultimately, the goal is to bring more people to the hydrogen sector. And this will only be possible thanks to transparent data analysis. We go now for the last project called Zephyr. 2 speakers. First is Sophie Ayons from Element Energy, who will present an overview of the project, and then Mathieu Gardy from the taxi company Hype in Paris. Sophie, the floor is yours.
Thank you very much, Lionel. I guess firstly, to start off, good morning, good afternoon, and good evening to everyone who is joining this meeting today. We're very excited to be here and to be able to present the Zephyr project. As Lionel said, my name is Sophie Aynon, and I'm from Element Energy, a low-carbon energy consultancy, alongside my colleague Madeline, who you would have heard from earlier in this session. Element Energy coordinates the Zephyr project, or the Zero Emission Fleet Vehicles for European Rollout project. And today we are here to present the progress the project has made in the recent years, some of the emerging results from the analysis, and then I'll pass over to my co-presenter, Mathieu Gardy from Hype, who will present some of the kind of wider impacts of the project going forward. Slide isn't changing. So what the project aims to do is answer to a call launched by the FCH JU in 2017. And the call in 2017 aimed to build upon some of the key business cases identified in previous and ongoing demonstration projects, such as High5 and the Hydrogen Mobility Europe initiatives, which you heard about earlier. So the call aimed to both combine a large-scale demonstration of fuel cell electric vehicles and hydrogen refueling stations with a demonstration of a bankable and sustainable business case for fuel cell electric vehicles. The project launched in September 2017 with the funding support of €5 million from the Fuel Cell Hydrogen Joint Undertaking and over €13 million of investment from the 11 consortium partners outlined on the right of the slide, stretching across both the public and the private sector. So to date, we are over 60% of the way through this 5-year time scale that the project has to deploy vehicles and evidence their operation. And we are starting to make very good progress. We are seeing that the fuel cell vehicles are very suitable for these high mileage fleet applications. And we're also seeing a very positive emerging business case, which I will go on to later on in this presentation. So in order to achieve the business case, Zephyr aims to deploy 180 fuel cell electric vehicles into operation in applications such as taxis, private hire, and emergency services, where the operational advantages of the fuel cell electric vehicles, for example, their long ranges and their quick refueling times, where in applications where these operational advantages are both required to enable the business case, but also can be maximised. And this has led to the deployment of vehicles in 3 cities, so in London, Paris, and soon to be in Brussels, where the value of the zero emission vehicles can also be monetised. For example, through the avoidance of congestion charge zones or increasing air quality restrictions, preventing vehicles operating in the city centre. The project will use existing hydrogen refueling station networks that are in place in the cities today, and it will upgrade some of the stations to ensure the back-to-back performance that is required, as noted by the previous presentation. So the project also aims to, by using these stations, to increase the utilisation of the stations and thus increase the business case for the hydrogen refueling station operators going forward, providing them a steady and secure demand for hydrogen throughout the period of the project and beyond. So in terms of where we are today, the project is progressing well. We've deployed 117 out of the 180 vehicles in London and in Paris, and 60 more are due in Brussels, but there has been some delays due to regulatory complexity encountered in the city. And of the vehicles that have been deployed, they are being used as a direct replacement for petrol diesel vehicles, and they're operating well. They've amassed over 4.2 million kilometres since April 2018, which is the equivalent on average, depending on the fleet, of between 150 to 175 kilometres per day. So really demonstrating that the vehicles are up to the test of the high mileages. In terms of the hydrogen refuelling stations, over 115,000 kilograms of hydrogen has been dispensed by the stations in the project, and 3 out of 4 upgrades have been completed, including upgrades to the technical performance to allow higher back-to-back performance, and then also upgrades to the customer experience of the station, for example, implementing availability apps. And then in terms of the performance of the vehicles, we can evidence that through data given in the project. So we can see that the fuel cell electric vehicles are performing incredibly well, with over 99% availability, and this has exceeded driver and operator expectations. A key value proposition of the vehicles, again noted by operators, has been the long ranges and the quick refueling times, which are novel to this zero-emission technology. And as you can see from the graph on the left, this is a graph illustrating the results from a survey provided to all drivers and operators within the Zephyr project. And when asked about their experience of fuel cell electric vehicles, as you can see in the green columns, there has been an overwhelmingly positive experience of fuel cell electric vehicles, with over 95% of drivers rating their experience to be positive or very positive. However, you can see in the graph that the experience of hydrogen refueling stations has been somewhat more mixed, and there are calls from the drivers and the operators to increase the number of stations in cities, especially in large cities where navigating between the east and the west is particularly difficult and time-consuming. And there's also been calls to improve the reliability of the stations in order to really further the commercialisation case for vehicles in taxi and private hire applications. And then another aspect of ensuring this further commercialisation is obviously the business case. We need a strong business case for the fleet operators to be convinced to uptake fuel cell electric vehicles. And on this graph shown on this slide, it shows the TCO, or the total cost of ownership, of a variety of vehicles across the market at the moment, including a fuel cell electric vehicle current, which is today's current fuel cell electric vehicle without subsidy, and then a Zephyr fuel cell electric vehicle, which includes the generous subsidy from the fuel cell hydrogen joint undertaking. As you can see from that graph, the FCH JU funding is vital in bringing the cost premium of a fuel cell electric vehicle down in comparison to a petrol diesel hybrid. So the funding has brought the premium down from about 80% to 40% today. And although prices still remain high and above parity, the operational advantages of fuel cell electric vehicles can lead to incredibly positive externalities for operators. For example, in London, the avoidance of the charge, so the £15 per day charge. And the other point to note is on this slide, the battery electric case here is a best case scenario. It assumes a slow charging and after a shift. And for many fleet operators, you must take into account that not all drivers would have off-street parking, and there may be often needs for rapid recharging in order to meet the range requirements of the business case. So, although there is a positive business case already arising for taxis and private hire fleets, the future is very bright for fuel cell electric vehicles, with prices expected to decrease over time with scale, and incumbent options such as the hybrid and the petrol hybrid electric vehicle to increase as sale restrictions are enforced, taxes increase, and cities become increasingly strict on air quality regulations. By 2025, commitments from OEMs indicate that parity is achievable with petrol hybrids such as the Toyota Prius today, and should scale be achieved. As a result, the scale of a hydrogen refueling station can expect to reach nearly €7.50 per kilogram for hydrogen dispensed. And when you assume this, you will get the FCEV 2025 case that is displayed on the graph on this slide. So when you assume this case for 2025, you can see dramatic cost reductions of nearly 50% in comparison today, with both requiring no subsidy from the FCH JU. This is also expected to bring fuel cell electric vehicles in competition with modern battery electric vehicles. So overall, we're in a very good position in terms of price by 2025, and that's just based on the cost reductions expected in the technology. We can also expect policy to move alongside with us and create an even more positive business case, which is not taken into account in that graph. So that is all from me today. I will now pass over to my colleague Matteo Gardi, who will provide an insight into the business case for his operations.
Hello. So, sorry, can you hear me? Okay, so thank you, Sophie, and good morning, everybody. I'm Matteo Gardis, the CEO of Hype. The launch of Hype in 2015 was clearly a bet. We had been looking for a few years before for a solution to help the taxis to switch quickly and massively to zero emission, and therefore to be able to eliminate noise and exhaust gas of this fleet from the city. Battery electric vehicle had proven to be not practical enough for this activity in a situation like Paris, notably because of the psychological anxiety regarding range and autonomy, and also because of the constraints in terms of charging, which are real hurdles for massive adoption for this activity, because in this activity, most of the operators are in fact independent driver, and you cannot ask them, they cannot afford to have additional constraints or to have additional risk in their activity. So H2 seemed to be a perfect solution on the paper because it presented all the advantages of the electric vehicles and none of those constraints. But at the same time, the sector of H2 mobility was extremely young. The costs were extremely high, the volume very low. And so to try to win this bet, we needed first strong support from industrial partners and also strong public support. And clearly the FCH JU programs were really vital for us. And second, with those supports, we needed to make things move, to accelerate things and try to increase volume to reach as soon as possible some form of critical mass in our activity. So the Zephyr project in that context was a perfect springboard for Hype because it allowed us to cross a necessary step in what was at this moment the most critical area for us, which is access to a sufficient number of cars. And during the project, it also allowed us to confirm that this solution with H2 mobility was effectively fully relevant and fully positive for the drivers and for the customers. The main challenge that the project raised for us was the necessary acceleration in HRS deployment. And so we created a dedicated company named ICETCO to fully integrate the different components of our strategy. I guess we're on the next slide, but I cannot see the slide, sorry. So ICETCO includes both the fast deployment of HRS network and also the development of mobility-related applications. Sorry. The first market that we addressed is taxi and private hire. And on this market, ICETCO can rely on its first customer, which is the Hype fleet, in order to address the other taxis, the other private hire, through a dedicated package. this package will, we believe, help them to switch quickly to zero emission. And the idea is that for a fixed monthly fee, which is comparable with what they pay today for diesel, there we get all they need for their activity. So it includes the cars, the access to the cars, the fuel cell electric vehicles, including maintenance. It includes the energy with the access to the network of HRS that is deployed by ISETCO. And it also includes, what is key in this activity, the access to the final customer of the taxi through the booking app Hype. And we managed to have this global package at a comparable price as what they pay today in a diesel environment. ISETCO will also progressively address other relevant H2 mobility markets, like buses, like other LDVs, and try to help to make those markets also accelerate and increase the volumes. Where we stand now, so third slide probably, and the scale-up plan in Paris. So in the coming months, we should in Paris reach 600 cars in the Hype fleets, and we will also start to propose the mobility package to the other taxi and the other private hire, with an objective of 10,000 cars, taxi or private hire, to have switched to H2 for the Olympic Games in 2024, which represents 20% roughly of this market in Paris area. In order to support that, we will deploy next year 4 additional HRS. You can see on the slide some pictures of the next one, which will be in the city of Paris, Porte de Saint-Cloud, with a capacity of 1 ton per day, with on-site electrolyzer, and all this on a location which is only 1,000 square meter large. And for the 2024 deployment plan, we plan to deploy additional 16 HRS of 1 ton per day each. We are also preparing our geographical expansion. We will replicate this model in other major polluted cities, notably across Europe, and focusing first, again, systematically in situations where we see that battery electric vehicles do not provide an efficient enough solution for this activity to switch quickly to zero emission. Thank you very much.
Thank you very much, Mathieu. This is the end of the presentation of Zephyr. As you have witnesses, it's one of the main goals of the FCH, in the sense that we have found factual analysis. We know how the taxis are performing, how the HRSs are behaving, and up to the point of creating a new market, not based on the FCH funding alone, but it helped. Now it's time for questions. I see already some of them on the chat function. The first question was about the hydrogen buses. Is it worse to do retrofit of the buses? Will it be more easier in the sense it will accelerate the pickup of the hydrogen technologies by retrofitting old diesel buses? So I throw the question perhaps to Jens, Madeleine, or Lars.
Maybe from the operator perspective, if I may start. I hope. Sorry, I was on mute. You can hear me now, I think. Yeah.
Yes.
If I may start, from the operator perspective, there is a possibility to do the retrofitting, and we have looked into that. And it might speed up a bit the process, but I think in the long run, this should be our aim to do that, because fuel cell buses is new technology. It's a new bus. I think we are better off really going for the new product, for the better product, and therefore, in some cases, it might be useful looking into that. But as mentioned, in the long term, I think the OEMs have very good products on the market. We are very happy with our Van Hool buses, and we are really excited to get the Solaris bus right now. We're testing the Caetano bus. It's in operation by RBK right now. Very, very nice products. We are looking forward to see the right bus on the market. We have excellent products on the market. So I think the retrofitting is maybe not the best solution.
Thank you. A question now for Everfuel, Lars. Who is the bus provider that you mentioned in H2 bus. Can you remind us that?
Yes, as Jens just said, there are some. I think Madeline mentioned that there are 14 producers of hydrogen buses in Europe. Some of the ones who have greater experience in rolling out is 4 or 5. And the one who is supplying the buses for H2 bus is Wrightbus of Northern Ireland.
Okay.
That was easy. I would like to also add something to what Jens just said. So if you retrofit or if you buy a new bus, it doesn't matter because our stations, they communicate with the bus anyway. So we can actually refuel everything that meets the standards. So I think that's one of the really, really good things about fuel cell buses, that there's only the same standard for heavy duty on buses. So we can still meet it, although it's a retrofit or if it's a new product.
Thank you. There is now a question regarding the hydrogen infrastructure. So a question perhaps for Benjamin or Peter. Does the upgrade of stations depend on securing demand for heavy-duty vehicles, or the strategy to upgrade stations will advance regardless the demand level?
Yes, so I briefly answered that already in the chat here, but I don't know if that's visible for everybody. I think it will be a mix of both. Of course, for the upgrade of our existing stations, we will focus on a customer approach where customers first need a higher back-to-back performance, a higher throughput of hydrogen per day. And we are doing that, for example, with our partner Faun at the moment. They are offering garbage collection vehicles on a 700 bar basis, and we are looking where first vehicle fleets are going to which municipalities, and of course are upgrading our stations depending on that. On the heavy duty vehicle side, I would say really then long haul vehicles or big fleets in this market. I think the infrastructure has to be built up, and I think we will follow the. This is in very intensive negotiation at the moment. What role H2 Mobility will play among all our shareholders and everybody that wants to enter this market. But I think from our side, we will start with a customer-centric approach. So clearly looking for demand cases first, together with customers, and seeing where they need their vehicles to travel. And then this will be followed by, of course, closing strategic locations in order to allow a mass market rollout. Because as you can see now, we are coming from this approach of having a coverage focus at the beginning, and it's quite challenging at the moment to allow all these costs that we have with this very small vehicle numbers. And I think in the duty vehicle market, you have this very, very big advantage to know where the vehicles will travel. And we will, intensify that with customers in order to place the hydrogen refueling stations at the best positions for their mobility needs.
I guess it's as well a conclusion from Zephyr, from the last word from Mathieu, in the sense that the company HySetCo would deliver or provide hydrogen to a span of hydrogen mobility actors, not only taxi companies. Speaking of taxis, we have a question on Zephyr. How has the public experienced the taxis in Zephyr? Do they enjoy the experience of being transported in a zero-emission fuel cell vehicle? Question to Sophie, perhaps, and Mathieu for the field feeling.
Yeah, of course. Maybe I can kick us off with a project perspective and then hand over to Mathieu. I think overall, the perceptions have been very positive from the public. Lots of people like to drive in the fuel cell electric vehicles. They feel like they're playing their part in the zero emission transition, and it's a very smooth ride. So that often adds to the experience of the public. We don't have, firm data on the public perceptions, but this comes from driver feedback of the taxis. So overall, there's a good perception, and I guess the safety question is being tackled daily by the drivers, and there is clear evidence across both H2ME and Zephyr that when the vehicles are in accidents, that they are very safe, and that is information that's being disseminated across the project. So I think a very positive view from the project as a whole, and maybe Mathieu can provide a first-hand experience.
Yes, clearly the customer experience is very positive and systematically quite the same. He didn't knew much about hydrogen when he entered into the taxi, because most of the time he entered into the taxi just by chance. He was looking for a taxi and he found this one. And a few minutes later, he's fully convinced that it's a very good solution, notably for taxis. So very efficient and very positive experience. And just to add on the safety, we are driving with hundreds of cars in Paris. So of course, we do have some accidents, and so I can confirm that we did not have any kind of safety issue, even with sometimes big accidents. So that's also something important for the psychological acceptance by the public for this vehicle.
Thank you. I would add something in there. For example, in the other fleet, Green Tomato cars, we even have taxi drivers having their own Twitter accounts and promoting the hydrogen fuel cell vehicles in there. So the drivers are in fact the voice, the spokesperson of the hydrogen technologies in mobility in there. Perhaps we could give the question back to the bus people. For Jens, for example, do you have done some satisfaction survey on how appealing were hydrogen solutions for the bus drivers and for the customers on board the bus?
Yes, sure, we've done that, especially as I pointed out in my presentation, we started in 2011 with a rather F&E project, and it was part of that project. We were surprised by the feedback, especially at the beginning, first fuel cell bus on the road. We were slightly worried if our customers might be concerned about it, but there was no single customer, to my knowledge, even up to date, who refused to enter a fuel cell bus. It's rather the opposite. We have really customers waiting for our fuel cell buses. As you know, we don't have the complete fleet transferred up till now. So there are sometimes really customers at the bus stop waiting and passing by, letting the diesel bus pass by in order to take the fuel cell bus. Same for our drivers. As you know, fuel cell buses, they drive purely electric. So you have all the advantages you have with electric driving. There's hardly any vibration, there's less noise. So our drivers are pretty happy. We haven't looked in our sick leave days and statistics to see if actually our drivers are less sick due to the less vibration. This might sound funny, but it is really the feedback we got from our drivers that they feel more relaxed after an 8-hour shift on a fuel cell bus in comparison to a diesel bus. So we do a lot, not just for the environment, but for the health of our bus drivers and for the happiness of our customers, for sure.
Thank you. We stay on the buses for a moment. Let's now imagine that I'm a city or a transport operator interested in fuel cell buses. How can I approach you? What should be my first step? Is there a website, or where can I find more information about fuel cell buses? Shall I do a trial, already committed toward the fleet, or all these things? Perhaps, Madeleine? What would be your key words for somebody or an entity wishing to jump into hydrogen buses?
Yeah, I think, thanks very much, Leonard. I think the main message that I have is don't go it alone. I mean, we have Jens and we have many operators in Jive who are already trialling fuel cell buses. You can see they're already producing excellent results for cities and for public operators across Europe. So don't go it alone. We have a huge body of expertise and best practices that we're developing in the project, and also in collaboration with H2 Bus Europe and predecessor projects. I think the first place that I would suggest to go, either you can email us. Our details were on the slides, so you can send us an email directly, or via the fuelcellbuses.eu website, which is a body of knowledge that is produced by all of the fuel cell bus projects in this programme and funded by the FCH JU and Connecting Europe facility. And that has a lot of resources. It also has a contact form, so you can contact the team directly and be put in touch with with various operators or us on the coordination side to help support you with your project. But yes, main message is don't go it alone.
Thank you very much. Indeed, the club is vast. We have helped in order to ease, let's say, your jump into the hydrogen mobility. Question now about cars. In fact, in one of the diagrams, you have shown how the price of the buses went down from 1 million, let's say, to 600,000 euro in the case of Jive, and even lower for H2 bus. But if we speak about cars now, we did not see such a big decrease of the cost of the car over time. How can we lower the cost of the hydrogen cars by 2025, 2030, so that it would be more competitive versus more conventional or even battery electric vehicle? Is a question perhaps to Mathieu, being an owner of a large fleet of hydrogen cars?
I think the key solution to decrease the cost is to increase the volume. So we have to convince the car makers, the OEMs, that there is a market, that this market is now and not in 10 years, and that they should move and accelerate and increase the volume. So we have to explain to them, and that's what we are trying to do with HYPE initiative, that there is already a relevant market for those cars with a significant volume, because if you talk about the volume for taxis and private hire vehicles around the world, you have hundreds of thousands of vehicles that are sold every year for this activity. So it's becoming a real market for a car maker. And on these activities, most of the cities are looking for short-term zero emission solutions. So hydrogen is clearly something to bring there. But we have to convince the car makers to accelerate and to increase the volume. And once the volume will increase, the cost will decrease. And the other thing is, in the taxi activity, you have what is interesting is the fact that you not only look at the acquisition price, you really look at the TCO, monthly TCO. So it helps also to start even with a higher price because you can work on the TCO even if the acquisition price is high.
Thank you. And I do think as well that the regulation, the fact that many more cities are now putting zero emission zone where diesel cars will be banned, will act as a boost for a zero emission solution, be it battery electric or fuel cell electric vehicle. So that, in fact, should be a convincing argument towards the hydrogen cars OEM, so that we see more models than the one available today. If we stay on the TCO model that you mentioned, Mathieu and Sophie, there was a big fraction which was the car capital cost, let's say, on the TCO, CAPEX and OPEX. But as well, a big fraction of it was in relation to the fuel, the hydrogen fuel. You take a value of 12 euro per kilogram. How could this price of the hydrogen decrease over time and make the TCO gap of 40% that you have highlighted closer to conventional taxis or battery electric taxis? Perhaps an answer from your side, and as well from the from Everfuel, who is providing hydrogen.
Yeah. Okay. So to me again, the answer is to increase the volume and to increase the usage for each station. That's why we deploy our own network of stations, and we can monitor the level of usage of the station. The second thing is, of course, to increase the size of the station. I was mentioning the fact that our next station will be 1 ton per day distribution station, and on the production side, now we will have 2 electrolyzers of 1 ton per day, but the next production scheme will be probably 10 times larger. Again, in order to capture the scale effect and try to accelerate the decrease in cost production and distribution.
Thank you. On your side, Lars?
Yes, there's some input on pricing there. So what we see, why we see buses is specifically attractive is we know exactly, I think it was you who stated that, Benjamin, where they refuel, how much they refuel, and when they refuel. So we can do the exact needed CapEx investment to serve them, also on dual redundant fueling points, but we know exactly how much they fuel. So we have prices, and that's not to point fingers at the taxis, but that's, let's say, between 5 and 7 euros per kilogram. And that's including the investment, because we can utilize the asset really, really well. And that's the challenge with taxis. You need to overinvest, and you don't know if the taxis will always come. So that's the real challenge here. Why we see this as the one of the keys to unlocking this is that we will set up the distribution and the production, and then we can utilize this in other locations. That's also the meaning of the CEF project. Put up the infrastructure and utilize it for others as well.
Indeed, in the portfolio introduction, for example, I've shown to you that in earlier project, when you had for buses between 2-3 buses per HRS, you have a huge variability of the availability of the station, going down up to 60%. But that was back in the days in 2000 and so on. And more as time goes, the more buses you put per HRS, then you put the resources in order to maintain your hydrogen infrastructure and maintain your fuel cell buses fleet. When you have 3 buses going out of service, that's probably an issue, but not a big deal. But when it's 10 buses that are out of your fleet because the hydrogen refueling station is not working, then you start to be into trouble. Indeed, the fleet, the volumes are a solution for the price and for better performance of the equipment.
Can I add something to that, Leon?
Absolutely.
I tried to raise my hand, but apparently that doesn't work. So as an example, we are doing a high-capacity station for the project in South Holland. And that's a commercial contract with a province, so we will be fined if it doesn't work. So in that, we needed to contemplate exactly what is needed for the operators in order to do the performance that they need. So we have built in the redundancy. We have done everything exactly as they needed from our perspective, and also which is able to scale to facilitate the rest of the buses that they have there. So it's going more commercial, and by that, we need to step up our game. And it's not just 2 buses. For this one, it's 24 as a starting point, and I think the depot is 70-something.
Thank you. We have just 2 minutes before the end of the session, so I'll give the floor back to you individually. Give me one word. What is hydrogen for transport to you? How can we quickly achieve larger scales? The first speaker was Madeleine, so it's falling on you. In one word.
I was going to use scale as my word, but yeah, variety.
Thank you. Jens?
It's already working. We are proving it, so just do it.
Thanks. Lars?
Yeah, scale is key. Scale is beautiful.
Thanks. Peter?
I feel like I ought to try and say something different, but I do genuinely think that scale and that kind of idea of really focusing the technology where it works is really key, I think.
And data, I guess, that you wanted to say. Benjamin?
So I just want to add, it's a key. Hydrogen is the key solution to where the core of our emissions in mobility are created.
Thanks, Sophie.
Policy and regulatory support to facilitate the business case.
And Mathieu?
Accelerate.
Accelerate. That's good for a taxi. I accelerate indeed. Now it's the end of the session. I would like to thank very warmly all the speakers. You had a good overview of hydrogen for transport application, for cars and for the buses. In 10 minutes at 12:30 European Central Time, another session will start about heavy duty for transport application, moderated by my colleague Pietro Caloprisco. See you in 10 minutes. Thank you.
Thanks, everyone.
Thank you.
So what are you waiting for? Meet me on the dance floor. I'm gonna bring you down.
Good morning and welcome to this session dedicated to heavy-duty transport application. My name is Pietro Calaprisco. I'm a project officer of the Fuel Cells and Hydrogen Joint Undertaking, and I will be moderating this session. Earlier on, for those that followed the other session dedicated to transport, you heard about the great achievement from the technical point of view, but also in terms of new business models that are emerging for light-duty vehicles, buses, and even the HRS. Now, we know that by 2050, we have a very ambitious decarbonization agenda at the European level. And specifically for transport, that translates in extremely ambitious targets. We will have to achieve minus 90% in CO2 reduction. That means that with light-duty vehicles and buses alone, we will not get these targets. New transport modes are being put under pressure in order to decarbonize. When I say new, I mean new for our technology, for fuel cells and hydrogen applications. We need to see how our technology can provide a contribution to the decarbonization of those transport modes and become a mainstream solution. So in today's session, we will tackle a bit this question. We will see how fuel cells can help for the marine application, how they can be integrated into the port ecosystems, how they can provide a propulsion for long-haul heavy-duty road transport. And finally, as we were also invited by the opening speech by Mr. Picard this morning, we will also not be scared to dream on how to see how fuel cells can provide a contribution to the aviation sector. And we will hear some of the results of a study that we have recently concluded in this domain on this subject. So for all the speakers, I remind you that you have around 10 minutes to present the achievements for your projects over the last year. And for all those that are following, don't be shy, put your questions through the application Mentimeter. We will collect all of your questions, and at the end, following all the 4 presentations, we will discuss them together with the speakers. Now, without further ado, I would like to give the floor to the first speaker that will present us the project Maranda, and this will be Mr. Jari Ihonen. Mr. Ihonen, the floor is yours.
Thank you very much for me, and it's a pleasure to be here. It seems that my video is frozen from my end. Yes, so I think I need to continue without just with the photo. Sorry for that. So I'm presenting the Maranda project, marine application of a new fuel cell powertrain validated in demanding Arctic applications. It's a 4-year project starting from March 2017, and the planned ending would be February next year, but we are applying 9-month extension so that it would be ending in the end of the November next year. There are 7 partners from 5 European countries, PTT, ABB, and Finnish Environmental Center from Finland, PowerCell Sweden from Sweden, Perse from France, OMB Saleri from Italy, and Swiss Hydrogen from Switzerland. The main project objectives would be to develop an emission-free hydrogen-fueled fuel cell system based on hybrid powertrain for marine applications, and to validate systems, 3 of them, both in test benches and on board on the research vessel Aranda. When it comes to global positioning of the project, it's important to notice that we are using for the first time automotive stacks and systems in the marine applications. And we are validating the systems in Arctic conditions. On the right-hand side, you can see the Aranda vessel after 10-meter extension in typical winter conditions. And on the right below, you can see the project structure. So just briefly, that we have responsibilities here, so that VTT is coordinating the project. The system is developed by Swiss Hydrogen. The stacks are delivered by PowerCell Sweden. Power electronics are delivered by ABB, and OMB Salary is responsible for the hydrogen solution, storage solution. This is the timeline, original timeline, and then with 9-month extension. So we are just about to start the validation phase, and this has been delayed quite much. In some parts a year, and other parts almost 2 years. Concerning the achievements, one of our goals is to develop highly efficient PEM fuel systems with 48% AC efficiency. 2 of these systems have been delivered for VTT for final commissioning, and one system is still in factory acceptance testing in Switzerland, in Swiss Hydrogen location. Below you can see the efficiency of the 2 systems compared to Mirai fuel cell system. What is important to notice is that when we are referring to 48% efficiency, this is full power efficiency. And for example, for Mirai, the efficiency at full power is much lower, while the peak efficiency is very high. And this is typical for the light-duty vehicles, that the efficiency is a light-duty fuel cell systems for light-duty vehicles, that the system efficiency is optimized for low partial load, because the system mostly operates in that range. On the right-hand side, you can see one of the systems in test facilities. Then you can see here the efficiency curves for the
Ladies and gentlemen, we had a small technical issues. This is to be expected, of course, during these times, but no worries about that. I would suggest that while we are trying to resolve these technical issues, maybe we can already try to recuperate and move on with the next speakers, with the next project. Oh, I see the slides coming back. So maybe I'll wait just for a couple of seconds to get confirmation whether we can still remain with the project Miranda, or whether it would be better if we move on with the next project. No, okay, I see that the H2O project slides already appeared on screen, so this seems to be the answer to my question. So no worries about that. We will still have the opportunity then at the end of the session to resume with the discussion about the project Miranda. We move now on with the next set of speakers, because for this presentation we will have 3 presenters that will tell us a little bit more about the heavy-duty application, the road heavy-duty application. And so I would like to welcome for this presentation Mike Dolman from Element Energy. He is the coordinator of the project H2O, and he will do this presentation together with Ivan Calaon and Ruud Boveman, I apologize for the pronunciation, that are respectively from the 2 OEMs that are involved in the project. Now, I hope that you are all here online with me, and Mike, I will give you the floor to start the presentation of H2O.
Thank you very much indeed. I hope you can hear me okay. So as I said, I'm Mike Dolman from Element Energy, and we're coordinating H2O, which is, I guess, the FCH JU's flagship fuel cell truck project. As Pietro mentioned, I'm delighted to be joined today by representatives of VDL and Iveco, who are supplying the vehicles in H2O. So 3 presenters in 10 minutes. I'm not going to speak for very long. I'm going to give a very brief overview of the project before handing over to Ruud and Ivan, who will tell you more about their activities and their plans within the project. So we developed H2 Hall. Hopefully this will work. Yeah, there you go. We developed H2 Hall back in late 2017 or early 2018 in response to the FCH JU's 2018 call, as you can see here. And I think at that time there were very few truck projects or truck offerings from suppliers, and clearly we're starting to see that change, which is very positive news, and I'm sure that will come up further in some of the discussions later on today, for example. So the overall objectives of the project are to develop long-haul heavy-duty vehicles that meet the requirements of customers in a range of different operating environments, and it's both rigid trucks and articulated vehicles that will be deployed within the project across 4 different sites. Of course, it's not just about the vehicles, it's also about the refueling infrastructure, so that's also being developed and implemented and tested within the project. We have objectives to achieve a very high amount of real-world operations, so at least 2 million kilometres of day-to-day driving to prove the viability of the technology. And of course, we'll be monitoring and evaluating the performance of the vehicles and the infrastructure in the project. And within parallel to these, if you like, deployment activities, we're looking at preparing the European market really for further rollout of the technology through the 2020s. So as you can see here, we're approaching the end of the second year of this 5-year project, and we've got 15 different partners collaborating to achieve these overall objectives. So without further ado, I'll hand over, if I may, to Ruud, who's going to tell us a bit more about VDL's activities.
Yes, thank you. Can I get the next slide? There it comes. I'm Ruud Boom from VDL. Now, VDL has already a very long history on zero emission, let's say more than 20 years. The last 7 years, we are very much involved in electric buses. At this moment, we have the biggest market share in Europe on electric buses. And you see all our products in one line, which are battery trucks, battery buses, and the 2 hydrogen vehicles. The white truck is a hydrogen vehicle, and also the red bus truck is a hydrogen vehicle, and also a hydrogen vehicle. Our philosophy of VDL is that we want to use also hydrogen, but hydrogen is only part of the strategy. And especially, you can see in the next sheet, is that we see hydrogen for the long haul and the heavy duty. So we see hydrogen in the long haul heavy duty trucks. We see that in coach and regional buses, let's say ships, big generator sets, and other generator sets VDL is aiming at for its hydrogen. And we have at this moment our strategy is that we want to have a modular system. So everything we do with hydrogen has to be for all kinds of, for the bus business, but also for generator sets or ships and so on. At the end, we want to have also hydrogen will be only be a success when we get also the TCO down. And the TCO down has to do with the price per kilowatt for the system or the price per kilo for the hydrogen. And what you can see also, one of our things is that we are only working on heavy duty and not on cars or something else. Other people can do that better. Now, we have at this moment for the future 4 different kind of products: bus, coach, truck, and also generator sets which can also be used in harbors or on ships. And all those we want to supply to our customers. And especially the first 3 will be done by VDL Bus and Coach. The last one is with VDL Energy Systems, a different company, but it is still part of the whole group. Now, as you see, H2 Whole fits exactly in our strategy, so that's why we are also inside H2 Whole. At this moment, we have 2 running trucks on hydrogen, a big one, 44 tons, and a smaller rigid one. And they are working under the H2 Share and on the Interreg projects. At this moment, we learn a lot from those vehicles and try to get everything we learn from those vehicles also in the H2O project. The H2 status at this moment is that we started to build up the first vehicles. You can see on the right corner that we, with those vehicles, getting the first fuel cells end of this year to make our first prototype next year of our first vehicle. And we hope to deliver all the vehicles to Colruyt, our customer in Belgium, let's say somewhere in the beginning of 2022. We have some development challenges. One big development challenge is, of course, the volume. To get everything inside the tractor within the current legislations is very challenging, especially when you see how much volume you need extra for storing hydrogen. Thank you. Now I give the word to Iveco.
Good morning, everyone. My name is Ivan Calaon, responsible for hydrogen product at Iveco. So the vehicle that you can see here presented is the one that will be operated during the H2O project. This is a vehicle with a gross combination weight of 40 tons, taking already advantage of the zero-emission vehicle weight bonus, powered by a two-stack fuel cell of 100 kilowatts, plus two modules of battery for 80 kilowatt-hour each. The idea is to have an ISO diesel performance vehicle presented and operating to all, coupled with an e-axle, an electrified axle of around 480 continuous power. This powertrain is fitted by 5 tanks of hydrogen positioned behind the cab and the chassis, so that it's possible to have up to 65 kilograms of hydrogen, converting into a range of 650 kilometers. This configuration that you see here, it's a 6x2 configuration, which is not usual for the long-haul operation. But again, as BDL Ruud was saying before, we have to overcome several challenges in terms of vehicle architecture, so that to make sure that we have a proper payload, a proper length, and the correct architecture for ISO diesel operation, we decided to go and test this vehicle configuration. Clearly, this is going to be what we will operate during our field operation during the H2O, together with different vehicle configuration. The idea of the field test is very relevant for Iveco, as it's a way to test a complete ecosystem, so that we can address the need for the penetration of hydrogen solution market. In this specific case, we do appreciate the fact that we are able to test and verify different situations in the ecosystem. In France, we will operate multiple missions with different vehicle configuration on a general configuration which is stressing the range, because we will have one basic position for the HRS in Marseille, and we need to cover a stretch from Marseille to Nice with different vehicle, rigid, and with different missions. In Germany, otherwise, we have different challenges, because we have a very specific route, very well defined, with no change, with 2 HRS stations at both sides, at both ends. That means that we are not going to stress the range, but in that situation, we are rather going to stress the efficiency of the operation of the customer side, being involved in the automotive logistic operation, which are quite demanding. And last but not least, we have Switzerland. Forgive, there is a mistake in this slide, because actually in Switzerland we will operate at 350 bar and rigid plus layer configuration. But what is relevant is that we are going to have a different test configuration, because there we do not have fixed routes, but we rather have to cover a geographical area, and possibly doing that we will have also a network of hydrogen stations for refuel. So, with this field test operation in the H2O, we do believe that we could be able to have a very interesting view on customer operations, on the hydrogen fuel station interfaces with the vehicle and for the customer operation, and clearly understand which are the best options for the vehicle to become an enabler in this picture. last but not least, how we see the time of this deployment. We are closing now the design for the vehicle that you see there, which will be operated in the H2O. In this situation, we will have, so starting from June, a running vehicle which will be tested and validated for the operation at the customer side. And we decided to divide the operation in two batches, one mid of 2022 and one mid of 2023, with the idea of give different maturity level of the technology, mainly driven by the maturity of the fuel cell system, which is under a serious industrialization path. So we consider the H2O project absolutely fully integrated in our full development path for production, and we are really eager and happy to be part of it. Thank you.
Thank you very much for this very interesting presentation. Indeed, the heavy duty is one of the sectors where there is a lot of interest right now, especially also in view of the recent regulation that is demanding the OEMs to increase the efficiency of the vehicles and also to introduce the zero-emission vehicles options by 2025 and 2030. Now, we will have the opportunity to come back also with some additional questions to the speakers of this project at the end of this session. But now we move on, we change again topic, and we go into ports. There we will have Mr. Arhent that will tell us a little bit more about what are the achievements and what is the overall setting of the project H2 Ports. Mr. Arhent, the floor is yours.
Hello, good morning. Thank you for inviting me and give the project the opportunity of presenting the state in this forum. Let me check. Can the slides be seen? I can send them. I don't know at which one am I. Okay, I will keep on going. H2 Port aims at testing the hydrogen technology at ports in the port of Valencia. And that can be translated in several impacts, in which some of them are related to the technology and the H2 Port aims and testing fuel cell at the port for validate the technology and reach a level of production readiness, and finally identify the market potential. And some of these expected impacts are related with cross-cutting issues, such as the definition of a safety strategy, some of impact related to acceptance and knowledge, to the identification of future adopters, and finally the rollout. Okay, now I can see. And why hydrogen and why ports? Hydrogen and ports have a lot of synergy between them. Hydrogen is the solution for some of the application in ports to become zero emissions, and also ports give the hydrogen sector the opportunity to start and even deploy some cases. And you can see in these figures some examples. A port has some captive fleets and also some frequent visitors, such as trucks or trains. And that's an ideal scenario for starting things. You also have some ports are industrial ports, and in those you will have the presence of huge hydrogen consumers. And all of that together to the potential of hydrogen that ports have to produce renewable energy makes ports an ideal scenario for hydrogen production, as you can see in some of the projects that are appearing these days. And Some other related issues. Ports will be the gate for a future hydrogen market and also are next to cities. So those are also those two characteristics that are very interesting for the deployment of the use of hydrogen in ports. In particular, H2 Ports aims at testing and being the first ports that introduces in Europe in their operative two equipments powered by the fuel cell and hydrogen. The two equipments will be a rich stacker to be tested in MSC terminal, which is a container terminal, as you can see in the middle of the screen, and the yard terminal tractor to be tested in a Roro terminal, which is a four-wheel tractor. And since both of them are located in different terminals, there will be a mobile refueling solution that will visit daily each of the terminals. One key factor for the success of the project are the partners, and we think we have a really strong consortium. We, as Fundación Valencia Portas, are coordinators and also have the support of Port Authority of Valencia as the public administration. Also, the presence of two outstanding research institutions such as Centro Nacional del Hidrógeno and Atena, and also outstanding industrial partners, Heister Gel, Ballard, the fuel cell provider, and Denagas. And finally, and very important, to have in the consortium the interest of end users that will guarantee not only the success but also the future deployment of the technology. This is the project structure, very quick. 6 work packages, 2 of them of support, 1 of them of cross-cutting issues, and the other 3 related to the pilot itself. Some details about the refueling solution. This is going to be carried out by Centro Nacional del Hidrógeno, and we'll also have the presence of the end users, Grimaldi and MSCTV, Fundación Valencia Port, also the Port Authority of Valencia. The concept includes 2 parts, one static part that will receive the hydrogen, and you can see the buffer tank and the compressor. And the hydrogen received from an external supplier is pressurized in the static part and stored in the mobile part, which stores the hydrogen in 2 levels of pressure, 300 and 150 for energy saving reasons, and will visit daily each of the terminals. This hydrogen refueling station will be able to deliver 60 kilograms per day, which is enough for the 2 users of the project. Then we have the rich stacker, which is going to be developed for Heister Gel, with also MSCTV is participating, the Port Authority, Fundación Valencia Port, and Centro Nacional del Hidrógeno. Very important, the dialogue between the OEM and the final user to identify and to select and to define the characteristics of the rich stacker that will ease the usage of these options or the final user, which is in the end the stevedore. The objectives of the design are not only to reduce the CO2 emitted, but also to achieve lower TCO and improve productivity. You can see some figures about the design. The design is almost finalized, and also the rich stacker is expected to be finalized at mid-2021. And the second of the machineries is a terminal tractor being developed by Atena, with also the presence of Grimaldi, Centro Nacional del Hidrógeno, and Fundación Valencia Port. This is going to be a retrofit from a thermal, from a diesel version. A Terberg diesel version, in which the Terberg support is in the project from the Italian distributor Malport. And you can see in the figure it will have enough storage for a whole day, batteries, and a fuel cell provided by Ballard. And this is ending the concept and starting the detailed design, and it's also expected to be finalized in the second half of 2021. The project started in 2019. We have suffered some delays due to the COVID situations, which has delayed almost every work package and every pilot. The current planning for the project is to have the hydrogen refueling station at the beginning of 2021. And as you can have been able to see, the Centro Nacional del Hidrógeno has already some equipment in their facilities. Both pilots are expected to be ready in the second half of 2021, at the end. And since the projects will include 2 years of operations in real conditions, that means that the end of the projects will be at the second half of 2023. So that has been a brief presentation of the project. If you want to know more, you can join our social networks. We have Twitter account, LinkedIn account, and we also have a web page with more detailed descriptions, and you can also subscribe to our newsletter. Thank you very much. That's it.
Thank you very much, Mr. Sanargant, for this very interesting presentation. There are certainly a lot of applications for fuel cells and hydrogen on the ports ecosystem. And again, please remain with us, like with all the other speakers, because then later on we will have the chance also to get some questions from the audience. So we've covered land, we covered the ports, and now we move into the air in line with what of the first speaker of the day. And we will have now Mr. Will Thanner that will tell us a little bit more about the study that was completed earlier this year by the Fuel Cells Hydrogen Joint Undertaking in cooperation with Clean Sky. So there is already here, as you can see, a good cooperation among the joint undertakings to see what are the potential of our technology also into the aviation sector. What are the key hurdles that need to be overcome in the coming years, if not decade? So please, Mr. Will Thanner, the floor is yours. Let us know what are the key messages from the study.
Excellent. Thank you, Pietro. So thank you for the kind introduction, and it's an honor to present a few of the key conclusions from the study. As Pietro said, this was a study together with the Fuel Cell and Hydrogen Joint Undertaking, as well as the Clean Sky 2 Joint Undertaking. And many industrial participants were part of the study, providing data, reviewing, and developing the analysis with us. What we want to show you in the next 10 minutes is the main findings, and then we can also answer some questions if there are any afterwards. Before we go on, maybe a quick look at the team. You have today here on the call myself and Julian Hölzen, but we were a bigger team with my colleagues Martin Linder, Maurice Wadenburg, and Daniel Riefer, who lead our hydrogen and aerospace and aviation industry practices and brought in their respective expertise. Let me go straight to explaining a bit the study that we did. As you know, or as you can imagine, aviation is one of the hardest sectors to decarbonize, and clearly there is a lot of efforts that are going on to improve efficiency and to go into hybridization of propulsion, etc. But to really get hydrogen decarbonized, we need new technologies. We need to switch away either to completely new fuels, so to replace kerosene with sustainable aviation fuels, which can be based on biofuels or on synthetic fuels, which uses hydrogen, or to switch the propulsion system itself. So to go away from the current kerosene turbines to either turbines that we drive by electricity, and then have fuel cells to convert this electricity from hydrogen, or to turbines that combust hydrogen. The focus of the study here was to understand whether this latter option, so the use of hydrogen to propel airplanes of the future, is an option that should be developed further, that should be investigated further, and that should also take place in the European Union. What I want to make clear is that the objective of the study is not to give any predictions, nor to provide any in-depth technical feasibility. That is much more than what could be achieved in such a short time frame. But the purpose was to understand whether it has potential and whether serious research and development should be devoted towards its development. What we did is an analysis on two levels. So one on the aircraft design, what does it mean for the airplane? And on the infrastructure level, on the system level, as you obviously need to switch to a different refueling and fuel infrastructure across a large number of airports. The focus here was on hydrogen propulsion, which means that we included three types of aircraft that react hydrogen in fuel cells and use that resulting electricity to drive a propeller, aircraft that burns hydrogen in turbines, or a combination of both, which we call a hybrid hydrogen aircraft. The bottom line is that what we found is that hydrogen has significant potential to decarbonize aviation alongside other technologies. It's not the only solution, but it is an important part of the solution. And as you can see here on the slide, we came to that conclusion with industry, academia, and researchers. More than 24 companies participated. Everyone from aircraft manufacturers, component suppliers, airlines, airports, and also research institutes. Now, let us take a look at the summary of the key conclusions and take them a little bit more detailed than what I said before. So on technology, we looked at, is hydrogen a feasible option to power this? So if we use the current performance and we assume a certain technological development, is it feasible that we actually develop a hydrogen aircraft? And we found that yes, it is indeed feasible. We could have an entry into service as early as 2035 for short-range segments, and the switch in the infrastructure level into the fuel supply and refueling infrastructure can be handled. We used liquid hydrogen exclusively as pressurized hydrogen provides efficient energy density. That means quite significant infrastructure implications on the ground, but in particular in the early years of the rollout, that is not a major hurdle. The major hurdle appears later when we then start scaling up this to a significant share of the total aircraft fleet and need a lot of energy production to make available sufficient energy to refuel planes. The second aspect, and we will see that in a bit more detail in a minute, is the economics. So how much additional costs would that create if we compare it to a kerosene-powered airplane? And what we found on a short-range flight, we see additional costs of around $20 per passenger. And this is about 20% less if we compare it to synthetic fuels, which we create from green hydrogen and direct air carbon capture. What is also important here is the climate impact. We always think of CO2 when we talk about greenhouse gas, but in fact, aircraft have other effects that are not directly related to CO2 emissions, which also create climate change and impact the development of the greenhouse effect. Therefore, actually, when you compare it in the full impact of flying, flying with hydrogen directly is better for the greenhouse gas effect than flying with synthetic fuels or biofuels, as it avoids a number of effects from soot and other particles that and contrails that negatively affect the environment. So the clear advantage of using pure hydrogen instead of using synthetic fuels is that you get a better climate impact. All of this still needs a lot of development. We have talked about in the study that an entry into service is possible by 2035, but a lot of development is necessary, and we set a milestone to have a first prototype in the late 20s, and more research being necessary following that in order to be able to also go into medium-sized airplanes and not only the short-range aircraft. Let me now switch over to Julian, who will tell us a bit about the economics.
Yes, and just to give you a bit better overview of what we did, bringing together technical concept studies. So that's what we did together with the German Aerospace Center, who looked into different segments with us. And we also evaluated economics of that. So here you can see, as an example, a short-range aircraft, which is actually a hybrid hydrogen aircraft. So with both a combustion and a fuel cell, which is very much in line actually with a zero-E aircraft concept from Airbus, just announced a few weeks ago. And what you can see, and Marcus also highlighted already, that the additional cost in a 2040 timeframe for such an aircraft would be less than $20 per passengers if you fly on liquid hydrogen. And that would be even 5% less expensive compared to a synthetic aircraft or a synthetic fueled aircraft. Just on an future potential scenario. So what we did, we looked into a 2050 timeframe where aviation as a sector would be fully decarbonized. And this is just a scenario. There are, of course, different approaches to that. But we looked here into having liquid hydrogen and synthetic fuels to power the full sector. And what you can see here is that the hydrogen-powered aircraft here in the green shadows, that they would replace the conventional aircraft fleet. So everything up to short range and half of the medium range fleet, which is due to the different entry into service dates. And the rest then would be powered by synthetic aviation fuel. So what you can see in such a scenario is that 40% of the global fleet would be hydrogen powered by 2050. And we would reach the net zero target for CO2 in that case, and would even reduce climate impact by 45%, so 3 gigatons of CO2 equivalent, also including NOx. And just to reach this very ambitious scenario, but this is still a scenario that the industry was d'accord, I would say, we show you here the major research and innovation roadmap that we saw with the 3 major milestones that you can see here on the top. So the first milestone would be to look into 2028, where a first proof of technical feasibility for a commuter aircraft and also on a demonstrator level already for a short-range aircraft would be needed. On the medium-range aircraft, we see this more for the 2035 timeframe, and then on a long timeframe, so until 2050, it would be more going into also revolutionary aircraft designs, but especially to look into large-scale infrastructure to supply aircraft with liquid hydrogen.
Good. And then in the last seconds that we have left, just here the summary of our key messages. The report is publicly available with all the details, but what we are finding is, number one, hydrogen is a compelling option as it has a superior climate impact potential. We have set a milestone, as we said, for 2028. Economics, it is more expensive to fly zero carbon than it is to fly with kerosene, but the economics seem within reach and are actually competitive if we look at other decarbonization options. And lastly, we can achieve zero CO2 emissions and up to 70% reduction of total climate impact, but it does take quite a big effort to develop this, and we think it is worth pursuing this direction. With that, I'll hand it back to the moderator, Pietro.
Thank you very much for this interesting presentation and to give us this outlook on what are the applications for hydrogen and fuel cells in the aviation sector. Now, I've been told that actually we managed to also recover the connection with our first speaker, Jari Ihonen, that will now guide us through the last few slides of his presentation. And Jari, I hope you are again with us. The floor is yours to continue with your explanation.
Thank you for this new opportunity, and I will go these slides quite briefly. Let's see. I cannot change the slides yet. The slide is where we have the system under testing in our industrial site. And the next slide is the pictures for the installation. This has been now paused by 9 months because of the COVID. This is actually the only real impact we have had from the corona. Then briefly about the safety and the acceptance of these containers we are going to install on the Aranda vessel. So we had done a lot of planning and safety assessments, a lot of CAD drawings, planning how to organize the filtering of air, the exhaust placing and everything. And now we are in the real life situation where we are installing the systems and preparing for the final testing. The same applies for the hydrogen containers. So a lot of planning also how to move the bottle bundles inside and in a smooth way when we are changing those. And this is also in the testing phase now, so that you can see that how they look like in the containers. Concerning the science of the project, we have developed a new hydrogen ejector model and validated that with our test bench. You may know that hydrogen recirculation is very crucial both for the efficiency and durability of the fuel cell system, and that's why we have developed this component. On the left hand side, you can see how the ejector looks like, and on the right hand side you see the modular parts of the ejector. So we can change all the pieces of this ejector and then validate our models. You can see our test bench here. This is a test bench where we can use a mixture of gases, both humidified and non-humidified, which are representing the real-life conditions in the fuel cell system. And then here are some examples of our validation runs, and you can find more in the deliverable 3.3, which is available in the website. Concerning the risk, challenges, and lesson learned, I think that by far the most important thing and the demanding thing is the safety at sea. And this has been a real challenge, and we have been using much more resources than planned for solving the problems with the careful planning and testing. Concerning communication activities, our main event was 1.5 years ago. The Maranda was together with the Flagships project in Electric and Hybrid Marine World Expo, and we had one of the fuel cell systems visible there, and that was a big attraction of this show. Concerning the exploitation plan and expected impacts, most of the results will be used in the new products of the companies and research institutes that are participating in the project. Thank you for this opportunity, and I'm sorry for the disconnection.
Thank you very much, Jari. Absolutely no problem. And it was also very interesting for us to have the opportunity to hear the full presentation of the project Maranda. All right, so now we went through all the 4 presentations, and it's the time for the question and answer sessions. So we have gathered some of the questions coming from through the tool Mentimeter that are coming from the audience. So I will read them through, and I will I will ask to the different speakers to please take the floor and provide their answer. So the first one is actually, Jari, since I still have you here, it's for you. And the question is, so how was it possible to increase the efficiency under 100% power output so impressively? Was it mainly achieved due to the optimization of the air supply system? So a rather technical question about the project.
Yes, we have highly efficient air supply system. However, we are also probably having much lower current density compared to Toyota Mirai system.
Mm-hmm. Okay, perfect. And there is also maybe another question still for you, Jari. And these are the data available about the impact of long-term full power operation of the automotive stacks on their durability. So what is the impact on the durability of the stacks? Maybe also linked to the maritime condition.
Actually, this was already completed 2 years ago. So we made PowerCell made stack level testing with the marine duty cycle, and the results were excellent, and they're available in the presentation 2 years ago, which we had on Miranda. And long-term durability testing from the system level, that will be available in the next year.
Okay, perfect. Thank you very much, Jari. Please remain with us. There might be some more questions coming for you. Now we move to the project H2O. Also in this case, we have a question. What is the main vehicle architecture challenge? So you already clearly showed us some of the designs of the CADs on how you intend to integrate the different components. However, if you could a little bit expand on these aspects of the main challenges on the integration, maybe also in the future, in the present, and also looking at the future, where you see the main avenues for further improving the powertrain so that they can accommodate the fuel cells components and the system. Ivan, Ruud, I think this question would be for you.
Now let's start.
Well, basically, storage is the key question. Whatever decision we can take on technology, either liquid, cryo-compress, or 700 bar, which are the most dense, with the higher density ones, we, in any case, have such a volume of to be integrated in the architecture that necessarily we need to have flexibility in length, and that's definitely a key point. Difficult to overcome for the next steps. And on the other side, we also have weight, because whatever solution is going to ask for an increase of weight. 2 tons have already been granted for the zero-emission vehicle approach, which could be enough, but definitely also the balance within the vehicle, the operation with the trailer needs to be taken into account in that. So we need a little bit more flexibility.
Thank you, Ivan. Ruud, would you have also? Would you like to?
I think Ivan already said that this, for example, for 700 bar, I need 8 times more volume than with diesel. So somewhere we have to find that volume, and within the current legislation of 17 meter 30 or 16 meter 50 length of total vehicle, this is very difficult to get all the energy inside the tractor, for example, and that will be a big challenge.
Okay, perfect.
All the other components, I think they are comparable.
Okay, understood. Thank you. And there was maybe a follow-up question, which is about the safety of the hydrogen trucks. Do they present any particular challenge compared to other types of technologies, or you're not seeing particular hurdles to be overcome when it comes to safety specifically?
I think that for safety, it will be as all other vehicles. I see only that in some years there are coming some legislations which ask for that we are not allowed to have high pressure within some area of the vehicle, so that gives an extra challenge. But normally, I think this will be the same way and homologation for the other vehicles. At this moment, there's not much legislation because the number of hydrogen vehicles is very low in comparison to the rest. But I think there has to be, there will be some legislation in the next years.
Okay, perfect. Thank you, Ruud. Ivan, do you have also a comment or?
I confirm. Within the technical challenges which are standard for the vehicles, not that different from the LNG, for instance. So basically, it's based on the security on the tank and on the storage, which is highly regulated. So I don't see it as a major issue.
Okay, perfect. Thank you both for this clarification. Now, you mentioned LNG, and this brings me actually to the next question, which is for the H2 Ports project. And the question is, will there be an easier path for the uptake of hydrogen in the maritime application in the harbor compared to LNG in the past? Or do you foresee also some challenges, be that in terms of technical difficulties or legislation for the uptake of hydrogen. So how do you see the comparison between these two alternative fuels and their future?
Okay, with hydrogen, in the maritime sector, there are two main factors to be taken into account. First of all, the autonomy. In some cases, depending on the use case, the amount of energy that you have to store in the vessel, it's huge. So if you change to another alternative, such as hydrogen or LNG, you can do it. Gives you some constraints in the use cases you can use that energy. And also the development of the refueling infrastructure, which is something in which Europe is investing a lot in the case of LNG. Since the amount of energy to be stored is large, you need like barges or pipelines that bring the fuel, etc. And that's something already solved for conventional fuels. It is being worked for LNG. And in the case of hydrogen, it would highly depend on how the hydrogen will be served. If we are talking about compressed hydrogen, either at 350 or 700 or whatever pressure, in terms of autonomy, it will be realistic in some use cases with like short trips and with frequent coming back to one point in which you can do the refueling. That is not an option that you can foresee for long distance shipping. If you finally adopt another carrier, such as LNG or methanol or ammonia, that case is different and it will depend on the case. If it is synthetic LNG, it would be the same as LNG. If it is going to be methanol, maybe it would be easier to develop a refueling infrastructure. And if it is ammonia, it would be something in the middle. In any case, I personally do not foresee that all fuels will be present in the future. The sector will bet and will go to take a path and will go either with LNG, methanol, or ammonia. And in that way, you could guarantee that a vessel, call it at different ports, will have the supply of bunker fuel available.
Okay, perfect. Thank you very much. But still, looking a little bit in the future, but maybe just focusing a little bit on the ports. You explained us about these very interesting applications, such as the yard tractors and the reach stackers. So the technology is there; it's showing that it can work. But what are now the commercialization plan? What is the long-term view for the sector or for the Port of Valencia? How serious is the sector now committed to really deploying these solutions?
The sector is willing to become greener, and in terms of technology, hydrogen in some applications or some mobile applications such as the reach stacker or the yard tractor, the hydrogen shows some advantages compared to pure battery options. And for example, in the case of the Port Valencia, who has a strategy to become a zero-emissions port in 2030, the presence of hydrogen technologies makes a lot of sense. We are seeing news about the innovations of the use of hydrogen and proposals in ports. So in the case of the Port of Valencia, the first step is testing the technology and showing everyone that everything works fine and the refuelings can be done properly. So the H2 port is the first step, but I personally see a lot of future in the use of hydrogen in ports.
Okay, perfect. Well, that's certainly a vision we share. Now, I would like a little bit to move to the aviation sector. And thank you again, the colleagues from McKinsey, for presenting these interesting results. And Marcus, earlier this morning it was already mentioned that there are now serious actors such as Airbus that they are declaring their commitment to the fuel cells and hydrogen options for the coming decade. Was that something that surprised you in the framework of the study that you have done, or this is something that somehow you were expecting?
I think maybe let me try to answer that first. I think the topic hydrogen for aviation has been looked in previously, but it was actually a longer time ago in the 80s and 90s that it has gotten interest, and it kind of disappeared, I think, from many research priorities for a while. As we were, before we were setting out on this report, we found that a lot of people were quite skeptical about the potential. But we did find more and more information around previous work that we could build on, and with the researchers in this field, we were able to come to these conclusions, which were, I think, different from our initial hypothesis. So our initial hypothesis would have probably been that it will be quite difficult to make this work economically, and that the technical developments would be too difficult or very difficult to achieve. And actually what we found as in the course of the study was that it is actually feasible, and the bigger barriers are there is a technological barrier, but there is also a big infrastructure barrier which has held this back. Now, as you said, there was a lot of momentum and announcements after this study has been released, and I think we don't want to take all the credit for that. I think there was a lot of things going on in parallel, but I think it is surprising how quickly the industry is moving now, and how many announcements we have seen, also serious announcements by governments in the European Union to support this technology and to invest into the developments. So surprising, but I think a positive surprise.
Perfect. Yes, indeed. Thank you. But remaining also about some of the last thing that you mentioned, the support. Now, of course, you presented that there is quite still a difference when we are looking at the TCO between the kerosene options and, well, even when we are looking at other types of drop-in solutions, and even more when we are looking at the fuel cells and hydrogen option. What would be really in the near term, like a market activation type of legislation that could really push these alternative technologies into the market? Would you consider, for example, the ETS with higher carbon prices as a viable solution? Or from the study it emerged that more specific types of legislation would really help to kickstart this, the deployment of this technology?
Yeah. So in the study, we do have a chapter where we talk about the necessary or the what we think would be good a good roadmap to go forward. I think in a short term, a CO2 pricing doesn't really change the picture too much. I think when you look at the development cycles and the necessary technology development here, we are still quite far away from an entry into service. We do need quite a lot of technology development in this area to increase the power density of the fuel cell systems, to improve the liquid fuel handling, to build out the infrastructure, refueling protocols, boiler off. So there's a lot of technical topics that need to be solved. So I think an immediate kind of taxation would not help these activities. In the longer term, there needs to be a clear framework to put a price on carbon or to put other incentives for the operators. Otherwise, the switch to these new aircraft will not happen. So I think maybe in the next few years, the emphasis needs to be rather on developing the technology, proving the technology, putting a prototype out there. I think seeing is believing, making these things safe. That should be probably the emphasis, and then there needs to be, I think, a clear roadmap for the industry that the industry can work with. That the industry knows we have to take this serious. We have to develop this in the 30s. Start introducing these novel airplanes. And I think the last thing that I would say is this study really focused on the use of hydrogen directly in aircraft, either combustion or in fuel cells. we see it really as part of the solution, right? So this is not to take away from the importance of biofuels and synthetic fuels in aviation, which we will need. This sector is very big. It emits a lot of carbon. Right now, we're not flying a lot, but we will probably go back to flying quite a lot. And we need really a mix of solutions to be able to address this transition. So it's not only this. There are other parts of the industry and other levers that need to be pulled, and there other measures may be necessary. So while research is a very important focus in this part here for this technology, synthetic fuels and biofuels might require different regulatory framework to be adopted.
Perfect. Thank you very much, Marcus. I think this was very clear. And for people that want still to see a little bit more the details, of course, the study is also available on our website, so that you will be able to see more details. Now, actually, in the meanwhile, I received a fairly similar question, which is more dedicated to the heavy-duty application, road application. And also in this case, the question was, well, today we have around 6 million of heavy-duty vehicles on our roads. And already by 2030, we are meant to achieve a very drastic change. So we will have to have way more zero-emission vehicles that will need to be on our roads by then. So between now and 2030, what are the key challenges that we need to overcome? Is it the infrastructure, the protocols, the vehicles, the legislation, simply the cost of these vehicles, and how do we get it down? So I would like a little bit for the HUL colleagues to comment on this question, on the future between now and 2030. How do we get there? What are the key challenges? I don't know if, Ivan, you want to get started by giving your perspective as one of the important OEMs that also decided to invest on fuel cells and hydrogen.
Well, definitely there is not a simple answer to this question, okay, because it's a combination of factors that's key. But if I had to choose one key point, is the cost of hydrogen. So TCO parity with the diesel by 2030 is something that can be reached only if we have a cost of hydrogen which is going to match a similar situation in which we are with the diesel vehicle. But definitely, infrastructure is something that needs to happen properly according to the development of the technology. But we had the experience in Iveco with the LNG, and with 10 years time frame, it's something that seems feasible if we have an analog approach. But definitely, it's cost of hydrogen which needs to be lowered to a value which is around €3 per kilogram to make the technology really enter in the scene as an alternative.
Perfect. Thank you, Ivan. Ruud, would you like to add some of your considerations?
No, as Ivan said, there are three, let's say, the two major parts are the kilowatt price for the fuel cell, but that can drop very fast if we have solve the chicken and egg story. But the most important one, and what you see also, is that we have to go to the price of €3 to €4 per kilo for hydrogen. Otherwise, or the diesel must be much more expensive, or you have to have CO2 taxes or something like that. But the big difference of fuel cell driven vehicles and the current vehicles is in the fuel price. That's a big influence on your TCO, especially when you drive more than 100,000 kilometers per year or more.
Yes, understood, of course. That has a great impact. But
yeah, sure, I could add one comment maybe, if I may.
Please go ahead, Mike.
Side. So I think it's a really, as Ivan said, it's not a simple question. We could talk for all day about the challenges of getting to scale, etc. But I mean, I think from my perspective, it's interesting because trying to get projects going at the moment, you see a lot of, almost like the demand is outstripping the supply in terms of the vehicles. So getting a truck project going, it's often difficult to find, vehicles available in the short term. But the realization that in any kind of success scenario for hydrogen, even achieving relatively modest percentage of the stock or the sales by 2030 implies a huge increase in demand for not just the vehicles, but the hydrogen itself. So, not just the cost of hydrogen, but the availability of hydrogen at all in the first place is something I think we need to be planning for, even now with the very early stage, small steps of, tens of vehicles. If we fail to plan for, the hundreds or thousands of vehicles today, you might quickly find that the availability of low carbon or renewable hydrogen becomes a big barrier and challenge to the further growth in the sector. So I think there are a number of initiatives. I know, we're involved in some of them ongoing to plan this, but I think it's going to be crucial for this work to plan the larger scale production at cost points that provide an economic case to do that in parallel with the early demonstration activities.
Great, thank you very much, Mike. I would like to remain still with the H2O project because I received another question. It's a little bit more specific on the project itself. And the question is about the refueling operation, because we don't have like a protocol which is dedicated just yet for the heavy duty operations. So which protocols are you going to use today within the project? What are the key messages or learnings that we can expect also in this regard from the H2O project?
Mm-hmm. So on the vehicle side, we are supporting the 700 bar approach. We are actively working with some partners in the definition of the 700 protocol for high flow refueling operation. For the time being, we have made for H2O vehicles compatibility with all the protocols that we know. So basically, we can operate the vehicle at 350 with the past car light duty technology. The effect is clearly that we have lower operation during the refueling. So we have longer time for refueling, which is okay for a transitional solution and in a field test. But clearly, we are strongly supporting hardware, software, and protocol for the 700 bar as our elective solution for the moment. In some cases, we have full cooperation within H2O. In some other, we try to match and find which is the correct compromise to make it happen. And we expect H2O and this field test activity also to give us indication on how severe some limitation could be in the day-by-day customer activity.
Okay, perfect. Thank you very much, Ivan. I have then still another question. This is for the project Miranda for Jari. So in this case, it's a bit more forward-looking type of questions. And here it says, like, what are the main key challenges that will allow us to develop a propulsion for vessels that will solely be based on fuel cells and hydrogen systems?
I think that's a quite big question, and I think for the let's say anything else than short sea shipping, we would need liquid hydrogen, and the technology development and the regulations concerning liquid hydrogen is by far the most important. I think that's where the development is needed for short sea shipping. If we can combine and for inland waterways, we can cope with the compressed hydrogen. And combining these refueling stations with, for example, heavy-duty truck refueling station, we can get the scale up and we can reduce the cost of hydrogen. And also here, the cost of hydrogen is one of the key issues.
Okay, perfect, understood. So let's say no big surprises also in this case. And then maybe we have time for just one last question. This is more for the project H2 ports, Joseph. So the question is a little bit about the regulatory framework, whether it's fairly clear in the environment in which you're operating, whether it's actually helping you to deploy innovative solutions that can help for the decarbonization and the quality of air, or whether the current legislative framework is actually hindering this type of development. Joseph, are you still with us?
Yes, I am.
Okay, so
I was just trying to find out the unmute button. I think about the regulatory framework, there are. I don't think it makes it harder to test and to deploy hydrogen technologies, especially in the case in industrial environments such as a port, in which you can have some things easier than in other environments, for example. However, the regulatory framework should, in some cases and in some aspects, should adapt and consider the use of hydrogen as a fuel that in some cases is not considered. And those not consideration make some things harder. Some projects are harder to be accomplished. But I think there is the commitment from the public authorities to solve that in the short term. So there is still work to be done, but it's doable and can be solved in the short term. So it will not be at this point the barrier for the deployment of hydrogen.
Perfect. Thank you very much. That's great to hear, indeed. So, ladies and gentlemen, unfortunately, we came to the end also of this session. I remind you that also all the presentations will be available on our website, where you can also find many more information about the projects that we have been developing for these last years. Just once more reminders, this afternoon at 3:30, we will have a conference, the presentation of the study on heavy-duty application that we have been conducting together with Roland Berger over the few past months. And today we will hear some of the key messages that we will be presented. So I really invite you to also join us for that event. And don't forget that after a short break of 10 minutes, we will still have 2 parallel sessions. So the program review days continues. Thank you very much for being with us, for your questions, and also very big thanks to all the speakers that were here with us today. Thank you.
Hello, good afternoon, everyone, and welcome to this session, which deals primarily with low TRL research projects for the development of fuel cells technology for transport applications. My name is Claudio Pavel. I am a project officer at FCH JU, and I will be the moderator of this session. What we are expecting now to hear today. In this session, we are going to see a summary of the results of 5 research projects covering primarily 3 main topics: about the development of materials and components such as membrane, catalyst, MEA for the next generation of fuel cells technology. We are going to expect as well to see some improvements on the performance, durability, and production cost through a better integration of these components, new design, new architectures, as well as new manufacturing processes. The last but not least, we are going hopefully to see some good results regarding the reducing of the use of critical raw materials, in particular the platinum and other PGM. Today we are going to have 4 speakers with us, and allow me to present them. It is about Deborah Jones, the Director of Research at the Institute Charles Gerard Montpellier, who will present us Gaia and Crescendo projects. Then we have as well Pierre-André Jacques, which is a project manager at the Innovation Laboratory for New Energy Technologies and Nanomaterials Lytton of the CEA in Renewable, presenting the Pegasus project. Then we have as well with us Mr. Joel Pochet, project manager at the same organization as Pierre-André, who will present the Dolphin project. And finally, we are going to have as well Federico Zenit, a senior research scientist at SINTEF in Norway, presenting the Gyre Leap project. In terms of house rules, just a few points to remind you. Kindly, please try to stay as much as possible within your time slot. And regarding the Q&A session, we're going to have about 30 minutes at the end of the session. And with this regard, I'm going to encourage the audience to drop the questions in the Mentimeter platform. So let's get started with the first 2 projects, Gaia, which relates to the next generation membrane electrode assemblies for automotive fuel cells, and Crescendo, which looks at the development of non-PGM catalyst for PEM fuel cells. Deborah, the floor is yours.
Thank you very much, Claudio. So good afternoon, everybody, or good morning or good evening, depending on where you are in the world. I'm very happy to give this presentation of Gaia. I don't actually see my slides on the screen. I don't know if that's supposed to happen. So the Gaia project is on indeed next generation automotive membrane electrode assemblies for proton exchange membrane fuel cells. Gaia responded to the call for proposals in 2018 on the call topic next generation automotive MEA development. The project started in January of 2019, runs through to December 2021. The total project budget is 4.5 million euros. And we're currently at 60% of the project implementation time. The project Gaia then gathers 10 partners. 6 of those are industrial partners, BMW, Johnson Matthey, 3M Dynion, Freudenberg, and Elmarco, the SME Protexo, and 4 university research organization partners, TU Berlin, TU Munich, ZSW, and ourselves at CNRS. I am Deborah Jones, and I work at CNRS in Montpellier. Moving on to the Gaia objectives. The objectives are to achieve membrane electrode assemblies with an exceptionally high current density, a power density that's beyond the state of the art, high temperature operation, and also satisfy a very ambitious cost target. More specifically, the power density target is 1.8 watts per square centimeter at 0.6 volts when tested in a short stack. Expectation of 6,000 hours of operation, operating temperature up to 105 degrees, and an MEA cost of €6 per kilowatt. So starting from a voltage loss analysis approach, which guided the targets in terms of the materials of the membrane electrode assembly and their interfaces, the approach in Gaia is to develop essentially all of the materials of the MEA, including the catalyst supports, the electrocatalysts, the ionomers, reinforcements, and membranes themselves, gas diffusion and microporous layers, all having improved activity, performance, and durability. Also to develop new deposition methods for catalyst-coated membranes and validate iterations of these CCMs. Finally, to associate the most promising of these components in order to achieve the final project targets in terms of the power density and in terms of the durability. We'll also analyze any gap that remains between the cost of the Gaia MEA and the project target in terms of the cost and technical targets in order to see what improvements are still required with regard to technical capabilities or indeed cost reduction. So we selected four, in fact, project progress indicators to illustrate the progress that's been made in Gaia. And the first of these is the catalyst mass activity in a membrane electrode assembly. Here, the starting point was a mass activity in an MEA of 0.6 amps per milligram of platinum. And the present status of the project is shown down there in the topple plot on the right, where with platinum nickel compositions, we're currently achieving a mass activity in the MEA of 0.89 amps per milligram of platinum. And that's actually significantly higher than the project target that was 0.7. On the left-hand side, we're showing some catalysts that are in an earlier stage of development. These are measurements made in the RDE, sorry. Here, the targets are to achieve an electrochemical surface area greater than 40 meter squared per gram of platinum, and a mass activity that's higher than that of the reference catalysts of the project from Johnson Matthey, shown there in blue. So in the top right-hand quadrant are 5 catalysts that have been prepared that actually exceed both of those targets indicated by the red dotted line, and will be carried through into the next stage of the project by being upscaled and integrated into membrane electrodes. The second indicator that we're showing here is that of membrane durability in an MEA. And here the criterion is an accelerated stress test that combines open circuit voltage hold and relative humidity cycling between dry and wet states at 90 degrees C temperature. The status of the project is shown in the figure, which represents the number of these AST cycles against the OCV response to a 50 kPa anode overpressure. So the start point of the project is indicated by the black line, which is an expanded PTFE reinforced membrane, which withstood around about 18,000 of those AST cycles. And the present status is indicated in green, which is an electrospun nanofiber reinforced membrane in an MEA, where in fact there was no failure, and this MEA achieved more or less 100,000 cycles without failure, a very significant result. Moving on from the components to the MEA performance itself, at the beginning of the project, we defined 7 operation points that associate low, mid, and high power with low, mid, and high temperature. These give 7 operating points, and at the present stage, the MEAs are currently achieving 5 of those. That's shown down in the bottom left-hand side of the slide, where this histogram shows 2 generations of MEAs, the first generation in gray and a second generation shown in green. And the y-axis is the percent of the target voltage at the different operating points that's been achieved. What we can see is that, first of all, that the second generation shown in green then achieved an operating point that it was not possible to achieve with the first generation, and also that the voltage achieved with the second generation MEAs was in every case higher than achieved with the first generation. Also importantly, shown on the right-hand side, is that the second generation of membrane electrode assemblies gave a significantly higher cell performance at the high temperature operating point 105 degrees than did the first generation. Moving on to the final indicator with regard to project progress, and this is one that illustrates progress with regard to manufacturing. This is an alternative coating method for catalyst-coated membranes, where the project start point was a conventional decal transfer, roll-to-roll decal transfer, and the alternative coating method is the catalyst layer deposited by a direct-to-membrane transfer method. So as can be seen by this humidity sweep at 1.2 amps per square centimeter, there's actually an advantage for this DTM method over the complete range of conditions from cool to wet to hot to dry. And although there was no specific target with respect to this alternative coating method, it's possible to see from this figure here that between 70 and 80 degrees, for example, that there's an improvement of between 20 and 25 millivolts at that temperature. Moving on now to communication and dissemination. Gaia has communicated through a project brochure, through 2 newsletters, and also an outreach and educational activity with a video that's been prepared on catalyst preparation and characterization by RDE and integration of the catalysts into MEAs with the associated testing and diagnostics. And this video is available on our project website and also through YouTube. With regard to the dissemination, just as we were ramping up in Gaia to present all of these new developments in conferences, of course, this was rather hit by COVID this year. Nevertheless, during the course of last year, there were 4 presentations that were made at 2 different international conferences, and a number of conference presentations are planned for next year. Gaia has published 1 review paper. This was a review paper published by TUB, and once again, several more publications are in the pipeline coming from Gaia. This slide gives 3 of the risks, challenges, and lessons learned up until month 20, as we are at the moment on the project. And the first of those concerns the thermostable polymer that's being used for nanofiber reinforcement, which at the beginning of the project was shown to give defects at scale, a rather slow electrospinning throughput, which meant that the cost was actually incompatible with the target. So we addressed this by reformulating the thermostable polymer, which means that there's been an improvement in the quality, significant improvement as well, or increase in the electrospinning throughput, and now the costs have correspondingly come down. Another challenge that can become a risk is that the benefits that we can see separately with novel MEA components are not always additive when we put these different MEA components together, which means that ideally we would have more short stack iterations than we initially planned, given the many new materials developments of Gaia. The action that we've taken is to increase the number of full-size single-cell tests rather than the short stack testing, although of course this is also challenging given the current on-site restrictions that there are. I mentioned in an earlier slide that we haven't yet reached high temperature, high power operating points, but we're confident that in the upcoming MEA generations that will be incorporating thinner membranes, higher mass activity catalysts, an optimized catalyst layer structure, and further improved MPL and GDL, that we'll be able to achieve also those operating points. The exploitation plan of Gaia comprises several different aspects that are given here. They include a product commercialization with increased product portfolios for various of the components that are indicated there, also increased sales, a use of introduction of Gaia components in next generation MEA products, Improved manufacturing technology that means that there's improved quality, increased performance and durability. And of course, further research and development to continue the development, the scale up and the qualification of the various materials, the components, along with the characterization, testing and diagnostics, and as well as the methodology standardization. So altogether, Gaia is on a very positive trajectory. The expected impact is high, both in the target area for the project of light-duty vehicles, but also looking further ahead to heavy-duty vehicle applications. So starting from the bottom left-hand side of the slide, the bottom corner of the arrow, then we've mentioned the ionomer, the improvement in the reinforcement, giving novel membrane architectures that led to the exceptional membrane durability. This exceptional membrane durability is also seen in an almost 3,000-hour drive cycle with only a 6 microvolt per hour loss. I mentioned also the high mass activity catalysts on novel carbons that meant that we managed to achieve the mass activity target for the project by 30%. The breakthrough alternative deposition methods mean that the CCMs that can be produced will have fewer deposition-related defects and lower interface resistances. And finally, the novel MPL and GDLs that have been specifically tailored for high temperature and high current density operation have been instrumental in achieving the 105-degree operation and the intermediate power density target of 1.5 volts per square centimeter. So where we stand at the present time is going to be then the implementation, building of several further short stack iterations that will integrate the Gaia new materials and achieve the targets in terms of the durability, the power density, and this higher temperature of operation. The cost analysis will be starting next month, and that will also guide us as to where we stand with respect to the costs and the cost target, and also what further effort is needed with regard to technical improvements or indeed further cost reduction. Moving on now to the second project, Crescendo. This project sits rather upstream, I would say, from what we've just been talking about in Gaia, with its very high current density and power density targets. Project Crescendo concerns the replacement of critical raw materials, and in particular platinum, in PEM fuel cells, and by the development of non-PGM catalysts. So Crescendo responded to a call for proposals in 2017 to the call topic towards the next generation of PEMFC non-PGM catalysts. The project started in 2018 and runs until June of next year, has a total project budget of 2.7 million, and it's at 80% of its project implementation. It gathers 8 partners with 2 industry partners, Johnson Matthey and BMW, 5 partners from universities and research organizations, Imperial College London, TU Berlin, University of Padua, CA and CNRS. And the objectives of Crescendo are to achieve what might look like much more modest targets which are more modest targets compared with what we've just seen for Gaia, but they're nevertheless extremely challenging for PGM-free catalysts. So the targets for the final MEA are to achieve 0.42 watts per square centimeter at 0.7 volts on hydrogen air, 1,000 hours of operation with less than 30% power degradation at 1.5 amps per square centimeter in a drive cycle. So these are really the 3 areas that are very challenging in the development of PGM-free catalysts, concerning their activity, their stability over time and on operation, and high current density operation. So our approach here was obviously to work on the materials, on the cathode catalysts themselves, and also catalyst stabilization approaches. But it was also very important in the project to develop, let's say, a more learning or knowledge-based approach to this by the development at the same time of specific diagnostic methods for the determination of active site density and catalytic turnover frequency, as allow a more rational approach to the cathode catalyst development. At the same time, it was instrumental, extremely important to redesign the cathode catalyst layer construction for a construction that's specifically adapted and suitable for non-PGM catalysts. And the project also works on the development of PGM-free anode catalysts, including bio-inspired anode catalysts, having improved tolerance to carbon monoxide and to sulfur. Moving on then to some of the progress indicators. Here is the hydrogen air fuel cell performance. Down on the bottom left-hand side, the red polarization curve in that figure is given by a commercial non-PGM catalyst from Pacorito powder, fabricated into a CCM at IWI. And we can see from that polarization curve that at 600 milliamps per square centimeter, in fact, the cell voltage is somewhat less than 50% of the target cell voltage of the core and of the project. Where Crescendo stands at the present time is on the green polarization curve there, where we haven't quite reached the target. There's clearly a mass transport issue that must be solved by optimization of the cathode catalyst layer. But we're confident that given the improvement that we've seen with earlier catalysts coming from the optimization of the catalyst layer, that it will be possible to improve the mass transport properties there and achieve the final target of 0.42 watts per square centimeter. And second project progress indicator then, this time on the catalyst stabilization, where we were at the beginning of the project, was using a stabilization approach that we had developed in the earlier Catapult project, stabilization using very low quantities of platinum. During the course of Crescendo, then, the status is that we have been able to develop co-catalysts, PGM-free co-catalysts, that greatly reduce the side production of hydrogen peroxide during the OR and vastly improve the stability during the fuel cell operation. And finally, on the dissemination and communication activities of Crescendo, it's been extremely active in conference presentations, over 30 conference presentations during the course of the project. 7 publications at the present time, including one that's important for the consortium in that it established reactivity descriptors for PGM-free FENC catalysts. Crescendo organized, along with another project, CREATE, that's funded under the materials program, an international conference about a year ago, specifically dedicated to the development and the use of catalysts free of critical raw materials for fuel cells and electrolyzers. And the project has communicated through a project brochure and through 2 newsletters, and there's other information that's available on the project website. So with that, I think I'm probably out of time, so I'd like to thank you very much and hand back to Claudio.
Thank you very much, Deborah. Very interesting. I'm very glad to see that your project are going so well and addressing at least 2 crucial techno-economic objectives of the FCH JU. That one on the increasing the efficiency of fuel cells, and from the other side, reducing a lot of efforts to reduce the critical raw materials used in fuel cells applications. But let's go on. So now we have Pierre-André with the Pegasus projects, which looks at the development of PEM fuel cells based on platinum group metal-free structured cathodes and removal of other CRA materials. Pierre-André, please.
Connect my microphone. Yes. Could you hear me? Yes, it's okay like that. Okay. Go. So thank you very much, Claudio, for introducing the project. So I'm Pierre-André Jacques from the CA in France, Renewable, and I'm going to present you some highlights the Pegasus project. Okay. Are the slides? I don't know why, but Robin, could you please let me the clicking availability to change the slide? Okay.
I cannot confirm from my side. I hope somebody from the technical side.
Okay, I'm active. Okay, I'm active now. Okay. Okay, so let me just introduce you the project. So it's a project which has started less than 2 years ago, and it will finish in June this year. The budget of the project is 2.8 million euros, and there is a consortium of 8 partners in the project. There is CA in France, DLR in Germany, TUM in Germany, CSEC in Spain, Arminus in France, EAUS in Germany, IRD in Denmark, and Toyota in Belgium. And the objective of the project is to develop new PGM-free material to remove platinum at the cathode side of the MEA. In that project, we only address PEM fuel cells. So we are qualifying our material for acidic application only. And also we are focused on cathode only because there is 4 times much higher loading of catalyst at the cathode side of the MEA. So if we want to reduce the dependency of platinum of fuel cell to platinum, we need to remove platinum from the cathode side. And we can play with 3 main levers to design active layer and integrating a PGM-free catalyst. First, on the catalyst activity, we need to increase the PGM-free catalyst activity. We also need to increase the active state density to have the best catalyst. And then we also have to deal with the nanostructure of the catalyst in order to increase the accessibility of the active state of that catalyst. And the third lever is the cathode structures. And indeed, we also need to improve the structure of the cathode layers to have a better catalyst accessibility to the different reactants of the fuel cell. I mean, proton, oxygen, and also we need to enhance the water removal of these materials. Then, in that project, we also need to be able, of course, to manufacture the catalyst at the gram scale, and we also need to be able to produce the MEA with process which is compatible with industry requirements. Okay, and so this project is based on 3 main work packages. The first one is the catalyst development, the second one is the MEA development, and the third one is high-level characterizations and modeling. The other one deals with the LCA, life cycle assessment, the technical assessment, and also the communication and the management of the project. So to develop our catalyst, we've got a strategy based of 4 different catalyst structures. The first one is modifications of carbon nanotubes. Second one is modification of graphene sheets. The third one is polymerization of carbon matrix on existing carbon supports. And the last one is synthesis of doped carbon aerogel to be able to have materials with desired properties. So our results are this one. We synthesized, we developed our different catalysts, and we benchmarked those catalysts versus the Pajarito Powders Company catalyst, which is a commercial PGM-free reference catalyst. We can see on the screen that one of our materials presents mass activity which is 2 times higher than the commercial reference catalyst. Another catalyst has the same mass activity of Pajarito, and the third one has a lower activity. Also, what is important to say is that the people who are characterizing and quantifying the mass activity of the catalyst are not the same partner who are producing the catalyst. So there is no conflict of interest in quantifying the catalyst activity. And the test by RDE has been made by different partners, different institutes using different electrolytes, and the ranking is always the same. Then, in the second stage, we tested our material into MEA in 5 square centimeters single cells. And we can see that we've got the same ranking. I mean that one of our catalysts show a higher mass activity than the reference catalyst by a factor 3. Another catalyst, the carbon aerogel, presents the same activity as the commercial reference catalyst, and another one is a little bit lower. And if we compare the activity of our catalyst in MEA towards the international state of the Earth, we can see that with a lower loading of PGM-free catalyst, we achieve better results than one of the best state of the art MEA. So it means that we have developed a very good catalyst, and we succeed in integrating that catalyst in MEA. Then we can also have a deeper look in the characterization of that catalyst and trying to understand why this catalyst works better. So we performed X-ray adsorption spectroscopy analysis. We also performed cryogenic CO adsorption experiments, and we were able to show that our best catalysts do not have iron particles into structures and have only iron nitrogen-based active sites. That is very important to say that, because this catalyst has been prepared without acid leaching. So it's really a good added value if we want to prepare this catalyst at an industrial scale. And also what is very important to notice is that higher the quantity of iron nitrogen moiety, higher the performance of our catalysts. Then we also be able to quantify the number of active sites on our catalyst, and we can see that for the best catalyst, or number of active sites is around 3 times higher than the best value reported in literature. So we can see that the materials show very these materials with good structure show good performance, and we know why, because it's got a lot of active sites on its surface. Then we have been developing a new technique also to quantify the performance of our catalyst at the agglomerate scale. In fact, we developed a new method, which is scanning electrochemical microscopy coupled with atomic force adsorption, to be able to quantify the activity of our material at the agglomerate scale level. That allows to benchmark our material versus the state of the art and the material that we've got access thanks to our advisory board members. And then we will couple the intrinsic activity of the catalyst at the agglomerate scale. We will couple that value with active layer models in order to better understand what are the main drawbacks of those MEA. Is that the structure of the active layer, or is that the activity of the catalyst? And at the end, we are also developing a new coating method for PGM-free materials. We tested different processes to integrate material into active layers, and we tested spray coating, we tested bar coating, we tested coating on the GGL, we tested coating on the membrane, and we tested coating on inert supports, followed by transfer steps. And we were able to show that the process has a main impact on the performance of the MEA. And we were also able to show that we can produce CCM-based MEA with PGM-free catalyst at the cathode, with 6 active layers around 50 micrometers, which has not been demonstrated before. So it's also good to see that, because it means that we can produce MEA on industrial process to produce PGM-free based MEA. So to conclude, we can say that in our project we're able to produce catalysts with higher activity than the catalyst reported in literature, and the mass activity is better. The activity in MEA is better than what we could see in other projects. We are able to produce those catalysts at gram scale level, and the number of steps is quite few comparing to what we know from other materials synthesis. We are able to produce CCM, integrating PGM-free catalyst at the cathode. It's also another value, so we can test different membrane, different GTL, and to understand what is the impact of the other subcomponent of the MEA. In the next step of the project, we will integrate a new generation of PGM-free catalyst. We already present higher performance in RRDE technique. We will perform durability evaluation and test, and also we will make the life cycle assessment of our product, and also a technical assessment of our product. So I would like to thank the FCH JU for financing that action. I would like to thank all the partners of the project, for sure. And I also would like to thank the advisory board member, and more specifically our friends from different USDOE projects. Thank you for your attention.
Thank you very much, Pierre-André. Very interesting results. Before moving on, let me remind our audience to drop their question in the Multimeter platform, so at the end we can address together with the speakers as many as we can. Let's move on. So now we have Joël with his project Dolphin, and which is going to talk about the disruptive PEM fuel cell stack with novel materials, processes, architecture, and optimized interfaces. Joël, the floor is yours.
Okay, can you hear me?
Yes, I do.
Okay, well, thank you, Claudio, for the introduction. And thank you also for the opportunity to let me present the Dolphin project. So my name is Joël Pocha. I work at CA as project manager of the Dolphin project. And I try to move to the next slide, but it does not work. Can you move on to the next slide? Because it does not work from my side. Okay. Okay, so thank you. I will let you know, because I try once again. Oh yeah, okay, it seems that it's now working. So, okay, so sorry for that. So the project is an answer to the call 2018 on the topic dealing with game changer fuel cell stack for automotive application. So it started beginning of 2019, and the duration of the project is 4 years. And we are now roughly at 1/3 of the project. So the total budget is around 3.2 million euros, with a funding of a little bit less than 3 million euros. So in the consortium, we do have 7 partners split in 7 countries. So 4 industrial partners, Chemus in France, Switzerland, Belgium, and USA, who is supplying some ionomers and innovative membranes. Symbio, with a French company, as a joint venture between Forcia, Symbio, and Michelin, who aims at developing fuel cells, stacks, and systems for automotive application. And they interact in the project with us to define stacks, recreate some also modeling and manufacturing on some pieces of the stack. The third industry is Excel in Austria, also with a company in France and UK. Excel is a specialist of carbon fibers, carbon substrates, and carbon structures. So their contribution to the project is mainly on the carbon sheets, terminal plate, as you will see. And DMG Murray in Germany, who is a specialist of additive manufacturing and laser milling. And there are also three RTO, Manchester University, who aims at developing some single-layer graphene coating onto the membrane to reduce H2 crossover. ZSW in Germany, who is involved in stack design and request, and different single cell and stack tests, and also in modeling. And CA, so as project manager, and also involved in stack tests, single cell tests, component manufacturing, and modeling aspects. So the global aim of the project is to validate. The global aim of the project is to validate disruptive technologies for a 100 kilowatt lightweight and compact fuel cell stack, compatible with large scale and mass production for automotive application. So you see here a table with different KPIs as defined in the 2024 FCH JU call in terms of kilowatt per liter, kilowatt per kilogram, watt per centimeter square, durability, maximum operating condition, and cost. So we have a column dealing with the state-of-the-art as far as 2017. That was the AutoStacker project, also funded by a European Commission. And within the Dolphin project, we aim at improving each of these KPIs. So clearly, some of them we're quite confident in achieving our targets for some of them, kilowatt per liter and kilowatt per kilogram, for instance, but more challenging ones would be the increase in terms of watt per centimeter square and durability. For instance, here you see on the bottom left, right, a polarization curve in green and blue, the AutoStack performance that leads to 1.13 watt per centimeter square. And in terms of, if we do want to reach these KPIs, we need to increase this polarization curve to the red dashed line, which is the Dolphin one, so it is quite really challenging. So within the project, there are different technical developments. The final one will be a 5 kilowatt demonstrator that should combine the different most promising technical solutions in terms of material and processes. And for that, we will spend some time on the single cell. So to say here, you see a cut of the single cell with the membrane in the center, with the active layers, the gas diffusion layer, and also the flow field, and the sheets, metallic sheets, which are stamped in that case, and the coolant circuit, so on the anode and cathode. We will do work on different aspects of this single cell. First, we aim at reducing the sheets to increase kilowatt per liter and kilowatt per mass by thinning the metallic plates, by also proposing alternatives to metallic, such as carbon-based plates, with the corresponding treatments. We also aim at reducing what we call the channel pitch, the rib channel pitch, which is the dimension between the rib and channel, in order to go much smaller compared to the state-of-the-art, and so again to increase volumic and mass power density. And this we will do that by different technologies that we do follow in parallel, such as printing, molding, stamping, additive manufacturing, laser milling, and stamping. Okay. And then we will also try to reduce the GDR thickness. This is what we call the electrochemical and fluidic core. And on the electrochemical core, mainly where the electrochemistry occurs, we plan to coat MPL onto the active layer and see how far we can get rid of the GDM substrate, also to reduce all the thicknesses in the assembly. We also will propose some 3D textured active layers with improved ionomers, and also to have thinner membranes with a specific single-layer graphene coating to reduce H2 crossover and then to hope to increase durability. And the last topic deals with the terminal plate, for which we are studying alternative solutions with composite material in replacement of the current situation, which is aluminum plates, in order to reduce their weight and their volume. So, some results. The first one deals with increase of performance. So you remember that the current state of the art photocycle was 1.13 watts per centimeter square. We need to reach 2. So we have increased performance, but we have not finished yet, clearly. So the first step for us was to design a specific differential cell with a very small active layer surface in order to mimic local conditions in a real stack. That is, with this, by modifying the operating conditions with this cell, we can mimic inlet or outlet or middle of the stack. And here you see the polarization curve, where showing that we can increase the local power density by reducing the rib channel pitch. So again, the rib channel pitch is the figure below at the bottom with the rib and channel here, and we do want to reduce the dimensions of the rib and dimensions of the channel. In black, in the polarization curve, you see the current state of the art, so roughly 1.2 millimeter of this pitch. And when we reduce these dimensions, we can significantly increase power density. And this is the case whatever the local operating condition is. So we can expect this result to be the same over the full surface of the stack. You see that whatever the situation of the local conditions are, we always increase power density by reducing the rib channel pitch, so the flow field dimensions. Next step will be to find a trade-off between this increase of power density and the increase also of pressure drop, because clearly when you reduce these kind of dimensions, you increase pressure drops, which is a drawback for the stack at stack level. So we need to find a trade-off for this. On this, and then to test this solution over larger scale, single cells. But these tests have been done with machined ribs, rib and channels. So now we are trying to find alternative manufacturing processes to make this rib channel design with a lower cost. For this, we are testing different solutions in parallel. So here you see the additive manufacturing solution. On bottom left, you see the 3D molded carbon-based material solution developed by Excel, and on the bottom center, you see the printing of conductive inks to produce the ribs either onto metallic or carbon sheets. So for this, we have made different developments also by laser milling and also for stamping. So this is something which is ongoing. We need still to increase electrical conductivity. And next step would be to compare all these solutions on single cell and then to make a selection for most promising solutions for larger scale tests. And last technical topic deals with the electrochemical core. So we have also in the project some thinner membranes which should allow working at higher temperatures. We have also made some first tests to coat single layer graphene onto these membranes, and showing this H2 crossover can be drastically reduced when applying this single layer graphene. So we hope this would have a positive influence on the durability. And on the bottom of the table, you see that when we compare aluminum current, the current solution for terminal plate is aluminum. So if we make this terminal plate by using some carbon composite or glass composite material, we can reduce mass and volume. Two slides remaining. The first one deals with exploitation plan and expected impact. So we won't go through all of this, but generally speaking, For the different models, this project will have a very interesting exploitation plan expected impacts, either for increasing knowledge and know-how in terms of processing and manufacturing new materials in order to increase power density and or durability. This is also very interesting for in terms of commercialization of new process or new materials, for instance, such as the carbon-based solutions. We have started and will keep on applying different patents with potential licensing. And this also should allow some new actors in the flow field market to enter this to enlarge their portfolio. Nevertheless, we do have some risks in the project. So here you see the main ones. So for most of them, we have numerous backup solutions or mitigation strategies. The one, as I said, which is the more critical, deals with the 2 watt per centimeter square. This is really a challenging target. So for this, we have defined a go-no-go milestone during the project in order to check how far we are from this target and how far we are also close to the other ones in order to see how we can manage the rest of the project. And we have also added a new risk, which is into pandemic outbreaks, as we have all been impacted on this. On the other risks, as we are pursuing different strategies, different manufacturing processes, etc., we have really in mind that we could find one of them that would suit to be online with the targets of the project. So thank you also to FCH JU for supporting us with this project. So thank you to the partners. And well, I'm ready for answering your questions. Thank you.
Thank you very much, Joel. So please stay with us until the end of the session. Some questions may come actually for everybody. Now let's move on to the last presentation given by Federico Zenit, which will present to us the giant leap, and he will talk about the improving automation of non-polluting transportation with lifetime extension of automotive PEM fuel cells. Federico, please, the floor is yours.
Thank you very much, Claudio, and good morning, good afternoon, and good evening, depending on where you are. Yes, Giant Leap project, let's start. It's actually a more applied project than the ones you have seen until now. It's a project that was concluded last year, so we actually finished with total budget of 3.6 million euros, which about 90% from a few FCH JU contribution. So the partners were Sintef, where I'm from, Norway, as the coordinator and also responsible for control aspects. Université de Franche-Comté in France, responsible for prognostics. University of Split in Croatia, representing FESB, one of the faculties for diagnostics. Then industrial partners, Erin Klinger for stacks and Bosch Engineering for the system, both based around Stuttgart. And then VDL in the Netherlands are responsible for the bus and the trailer. I'll mention the bus, and well, this is the bus. The objective of the project were the development of diagnostics and prognostics for fuel cell systems. I put systems in bold because we're focusing on the whole system, not just the fuel cell itself. I'll come back to this aspect, which is quite important. We're focusing on automotive and specifically on a bus. With these diagnostic and prognostic methods, we would then develop advanced control algorithms and doing something hopefully smarter with this knowledge and increasing the lifetime of the system. And on top of that, we planned a demonstration of a prototype. Now, the prototype you can see here in the figure, it's actually a battery bus, what you are seeing, with a fuel cell range extender trailer in the back. So all the hydrogen tanks, fuel cells, and everything is packed in that trailer behind the bus. The bus itself is a fairly normal battery bus with only one modification, that it can charge during movement. State of the art at the beginning of the project was quite a sad state of affair for hydrogen buses in terms of availability. It was known that both in Europe and in North America, availability was fairly low, about 70%. quite consistently in Europe and North America. And that was mostly because there were problems with the fuel cell system rather than the fuel cell. That's actually something that is going to repeat several times. So the system is the problem, and it's still today. Fuel cells are very reliable. So Claudio mentioned before that this session was for low TRL projects. Actually, we went a bit overboard. We were supposed to go from 3 to 6, but we managed to hit 9. So 3 was experimental proof of concept where we started. We then validated the methods in the laboratory. Here we see some electrochemical impedance spectroscopy by FSB and energy macroscopic representation, which is an approach developed by University of Franche-Comté, applied to our system. Tier 5 is a validation of relevant environment. This specific example is an algorithm for online sampling of low frequency resistance, and I'll come back to what that is. So I have a specific slide for that later. TRL6 was the objective of the project originally, and that was done here. I see this experimental rig at Bosch. The fuel cells are actually the blue items in the back on the top right. The black one in the front is actually just the humidifier. And this is a full-size reproduction of the entire system, so 80 kilowatt system that was tested in Schwieberdingen for quite a long time. Then, of course, there was enthusiasm from the industrial partners. They wanted to go ahead, so they built the actual prototype, the trailer, and install the system and the hydrogen tanks. The big metal part in the middle is the hydrogen tanks. And you can see that this prototype actually has a very important item that is a license plate at the bottom, because this was actually homologated and could actually be test driven around along normal traffic. So there is the, without any passengers, there is the bus driving around in the Netherlands. And well, we got in the end to TRL 9. These buses actually, there are 4 of them, and they are driving today in the Netherlands on line 436 in normal service from Rotterdam. So next year, when we'll be out of the pandemic, you can take a trip to Rotterdam and take a trip on our range extender, on a battery bus with hydrogen range extender. One of the most important parameters we were going to work on was the durability also of the fuel cell stack. We started from an estimated 10,000. We wanted to extend it a bit to 12,000. You might know that there are already fuel cells that have much longer lifetime. There is at least one bus in London known to have passed 30,000. So it does not look very ambitious, but please notice we are looking at car-derived fuel cell stacks, not specifically heavy duty. The idea was to replace the stacks in the middle of the lifetime of the bus, so that you would be able to use stacks from the presumably much larger market for car fuel cells, and thereby save some money in that way. And since we had a range extender that could be easily swapped, this was the natural way to go. In the end, with the prognostic approach developed by UFC, we estimated that these fuel cell stacks can be serviceable up to 15,200 hours, which is beyond what we wanted to achieve, and also beyond the multi-annual work plan of FCH JU. One aspect that is quite interesting is the fuel cell rejuvenation. It's a phenomenon that we noted in a previous project, Sapphire, which was also prognostic diagnostics, but on stationary fuel cells. Back in Sapphire, we only noted that when shutting down the fuel cells in a certain way, they would recover some voltage over time. And this diagram you see is over several months, actually. This time we had a systematic study at FSB in Split, and they were able to identify a good number of factors that make it possible to achieve this rejuvenation. So they're listed here on the right. And there's also a link to the paper they published. It's open access, so you can download it. You can see in the bottom right corner. Another thing identified by FSB was that in electrochemical impedance spectra, there is one specific parameter that is very useful, and there's an intersection of the spectra in with a real axis. You see in that violet ellipse, that point where the spectra cuts with the x-axis. That is actually a very important value because it can tell you what is the level of degradation of the fuel cell. Now, the problem with the EIS is that it's very cumbersome, very expensive, and not something you can normally do online. But since this occurs at low frequency, SINTEF developed a modified relay feedback method that does not require additional equipment, can be implemented online. Was tested at Erin Klinger at the laboratory on their stack, on a full-size stack, and was confirmed to actually work and to reach convergence within seconds with almost no disruption at all to the system. Again, there is a link to our publication. Finally, I'd like to stress the issue of the balance of plant. When you have fuel cell system failures, and you have a lot of them, unfortunately, at least in the old generation of hydrogen buses, it's usually not the stack that fails, it's something else. Almost always, it's the compressor. In fact, we had a number of comments from Bosch. They were really impressed with how resilient the stacks from Erin Klinger were. Sometimes they forgot to switch on the cooling and they still worked. They managed to survive all the testing campaign. No one of the stacks died. And when they do the same thing with internal combustion engines, they always assume some of them will break. So they were very positive about the stacks. The problem, as I said, is almost always with the compressors, humidifiers, and other components that are cheaper, but also less reliable. And sometimes you have these failures cascading on the stack. For example, here you see on the right a compressor axle that broke. And it can happen that lubrication oil, in that case, trickles down to the fuel cell, and then the fuel cell was perfectly fine, but with oil in the airline, then you have to throw away the stack. In this particular case, University of Franche-Comté ran a data analysis on this destructive test we had on this compressor, and found out that what was wrong. In particular, there was a problem with transients that were going through the surge line for a short time and accumulating damage. And Bosch was able to devise a solution so that we didn't have these kind of problems during demonstration. Finally, in terms of the simulation, we had 4 peer-reviewed journal articles published and 4 more in the pipeline, 18 presentation international conferences, 28 public deliverables. Some of these are pretty small and trivial, but some of them are much more interesting. We organized 1 workshop at a major international conference, 1 booth at the Renewable Fair last year, 1 patent was granted to VDL for the trailer connector. A website, giantleap.eu, contains all the public deliverables, so visit it if you want to have a look. We also have a few movies of the prototype in operation. All publications are open access. They're all stored on zenodo.org, so you can search for that. And in particular, I think the most important thing, data. Data is available, especially for the balance of plant components. It was impossible to find data for tests of balance of plant components for automotive fuel cell system. We have it now, and you can use it in your research. It's released on an open source license. And that's it.
Thank you very much, Federico, and very much as well to the other speakers. I think we are going to have about 15 minutes to pick up some questions. Deborah, if you can mute yourself, just to take out this echo. Let's start first with GiantLeap, with Federico, and we have a question from the audience asking how other applications such as heavy duties, where the durability of the fuel cells is a key component, key conditions, could benefit from the findings from your project.
Well, absolutely. In general, whenever you have heavy duty, you need a long lifetime, and this can be applied pretty much immediately on heavy duty. We are actually starting up a new project. Maybe I'm saying too much, but we should be starting in 2 months, exactly on heavy duty, and we're going to take some of the results into this new project.
Thank you so much. There are a couple of questions on non-PGM electrocatalyst, and we know that developing PGM-free cathodes in general is very high desirable to reduce the cost of the PEM fuel cells, but also in the context of the supply risk associated with critical raw materials for Europe. I'm addressing to you, Deborah, maybe, what is your view on, and by which time do you see that integration of non-PGM cells in the commercial products will take place? So, as well, based on your experience in this field, how is possible to overcome the low performance and the low stability of the non-PGM catalyst? So, is it possible that the PGM-free catalyst will meet the platinum one's performance in the next, 10 or 5, 10 years from now? What is your view?
So first of all, in actual fact, of course, there has been some commercialization already of cells and stacks based on PGM-free cathodes. So this was back, I believe, in September of 2017 with a stack produced by Ballard and Nishimbo Holdings. So there is a precedent there for a fuel cell stack based on PGM-free. I think it's important not to look only through, as it were, the lens of automotive, where clearly the requirements are very strict, very demanding. So I think that, there are other applications as well for PGM-free and clearly not only automotive. Yes, so clearly, the durability is a problem, the activity is a problem. I think that we're looking at the, beyond next generation. So I think you said it yourself somewhere, in the timescale 2025, 2030 seems reasonable.
And I know as well, to stay with Deborah, that Gaia project enjoys a strong participation of big industry players such as BMW, Johnson & Matthey in your consortium. I was wondering, in terms of exploitation of the project results, if there is any good candidate in terms of either a material or a component that may reach a commercialization level by one of the partners, which, as you said, it was already happening in the past.
Yeah, I think it's just a little bit early to say. We've only passed the midterm stage. Nevertheless, I think that for several of the components, clearly there are vast improvements in the MPL GDL that will move through into the product portfolio of Freudenberg. The results are extremely exciting. It's almost an indestructible membrane that's been produced by the combination that we have there of the ionomer with the thermostable nanofiber electrospun reinforcement. So that's very exciting to carry through, into a product as a component of future MEAs. And clearly all of the catalyst work as well. So really there are many candidates going right the way through from novel supports, modified supports, catalysts that are prepared at partner Johnson Matthey, but also, the other partners, TUB. I showed some prospective catalysts there from TUB that will be moved through into MEA development. And so, we're very hopeful that there will be some of these developments from the laboratories that will move through into commercial products.
Thank you very much, Deborah. We have another question on reducing platinum from fuel cells, and I think maybe Pierre-André may pick up this one. The background is indeed that in the past years we progressed well in some indicators such as durability of the fuel cells, cost reduction, and the power output as well. But when we are looking at the PGM-free, we somehow are falling behind in terms of eliminating completely these materials from the catalyst. Do you think that are the targets too ambitious, or something needs to be revised in the approach of the scientific community? And here I'm referring what, in your view, we should look at developing, for instance, new synthesis techniques for the catalyst, a new approach for a better control of atoms or the active sites in the catalyst, or optimization of geometric structure of the active sites. How do you see this? Where the problem sits?
Okay, so first I think that the targets are never too challenging, because the targets are driven by the market, and if we want to have a working fuel cell, we need to achieve a certain amount of performances, of mass activity, and so on. So the targets are never too challenging. The targets are the targets. Afterwards, how can we reach high performance with MEA integrating PGM-free catalyst? I think that first we need to really manage the integration. We need to crush the materials. We need to have thin active layers, and so on. That is the first thing. We also need to have process which are compatible with the state-of-the-art component. For example, in Pegasus, we are working with thin membrane. Our membrane is 18 micrometers membrane. Because if you want to introduce PGM-free catalyst, and if you use thick membrane, that makes no sense. You need to use thin membrane and thin GDL and so on. After that, how can we improve the performance of PGM-free catalyst? We have been working with iron, nitrogen-based PGM-free catalyst for maybe 10 years, 15 years, 20 years. I think that the first publication has been wrote at the end of the last centuries. So maybe we need also to have new idea, to think to other active sites, to think to other metals, to think to other things. I don't know. If I know, I will do. But I think that with all the things that we have been doing for 10 years, 20 years, maybe we now know that the iron, nitrogen, carbon has got some limitation. Maybe we could never reach such high active site density to achieve good performance, that we need to revisit the active site. Yes, we need maybe to see what is in the blue oceans, and to think to other active sites.
And I think we can stay again with you, Pierre-André, and to go and to make some progress in this field. I can understand that there are so many challenges in front, and you may need to go not maybe on the standard ways to improve a catalyst, but as well to take into consideration something very new, to discover new breakthroughs as well. Do you see that a better collaboration or an international collaboration could benefit and could improve the research in this aspect? Should, for instance, the EU seek a maximum to maximize the cooperation with other countries such as Japan, US, or South Korea, or rather seek on its own European competitiveness? And I know that Pegasus, for instance, collaborates with international partners, and you actually are foreseeing testing some materials of them. How are these materials? Are they better than those developed by the Pegasus, or did you have the chance to test them?
Okay, so as I said in the presentation, we have the chance to test different materials from different projects, and more specifically from US dairy project, and we achieve a little bit higher performance with Pegasus material. So as I say, we are on the top of the state of the art. Nevertheless, if we want to compare the PGM fuel cell catalyst with platinum-based fuel cell catalyst, there is still a big gap to go over. So if we want to increase the performance of PGM-free catalyst, of course, we need to collaborate with our friends from US, from Japan, and from other countries, because all people develop different synthetical routes. So we might have different structures of active sites, And if we compare the performance of those catalysts, if we compare the number of active sites, if we compare the structure of the active sites, we might have new idea to improve the performance of those kind of materials. So we really need to discuss together to cross-check our materials, because sometimes, well, if you test your own materials, your material is good, but if another one tests your materials, it will not say if it's good or bad. It will say that is the performance, just it. And so we need to collaborate with people from the community, and we also need to maybe to find new characterization tools to better understand the reactivity, the mechanism, and the different steps for the ORR on those catalysts.
Thank you very much. I think we have another question, and just in 2-3 minutes. Joel, what do you think about how can we speed up the uptake of innovation coming from low TRL projects in the commercial products? And how can we make the path between the laboratory and shorter with respect to the commercialization of these products?
This is a really good question. And I think this is one key issue also for commercialization, clearly. Well, in fact, I think that maybe when we do when we are inside the project, we need to have this in mind, but also to take care of the planning we do want. Because if you do want to have a commercialization by the next 2 years or 10 years, it's not the same issue, nor the same strategy, nor the same techniques you want to put in priority. For instance, what we do within the Dolphin project, because we are testing different manufacturing processes or materials in parallel, we have a specific task dealing with cost analysis. And I think it could be a way to make maybe a choice, depending on the planning you do want, in terms of pushing some processes, because it would be a trade-off between the increase of performance, for instance, for a given solution, but also the time industrial people will be ready to set up this online, because all these costs can cost a lot, and some people could be interested in developing this process or not, depending on this. And it will also be a question of market. I think if the market is present, I think that more people will be interested in investing in improving processes or not. This is clear. So I think maybe the best way would be to have the market ready for this. But you say, all this is combined. But if the market is not open, I think that industrial people would not be ready to invest a lot, except with short-term results. If we do want to have more than this, we need to analyze this maybe inside the project to make a kind of cost analysis to make the choice.
Yeah, it makes sense. Thank you very much to all of you, and I think we are really approaching the end of this session. Very interesting results, I would say, out of this project. So some of them will continue, some other already are finished. I would like to come to the close of this session. This doesn't mean that the day is finished here, so I will extend the invitation to the audience just to remind that at 15:30 we are going to have a presentation of the study assessing the market potential of heavy-duty fuel cells and with some concrete case studies. So stay with us. We are going to have a very short break of 10 minutes. And then my colleagues will take over with these study results. Thank you very much once again. Have a good afternoon and stay safe. Goodbye.
around long haul and urban applications. And for long haul, we have now a project which is called H2O, which will put 15 trucks on the road. Their autonomy is required to be around 400 kilometers. We will have two different versions. We will have the tractor version, but also rigid configurations. And they will be really integrated in the daily operations of end users, such as, for example, BMW, Carrefour, or Colruyt. We aim to deploy those trucks next year and also some of them in 2022. The second project we have in demonstrations is the Revive project, which also will put 15 refuse trucks on the road. They have a bit of a different usage pattern. Of course, they have to go every day back to the base. And we are really designing here a standard because we are aiming here to really mass production. The fleet operation and totally, so the 15 trucks will have to demonstrate 120,000 hours of operation. And very good already. The first truck has been deployed already in Breda in the Netherlands. The next slide I would like to explain is about the components, because we don't only demonstrate, but we also work around components and infrastructure. And this year, actually, in the Call 2020, we have 4 topics on that. And the first topic was on the durability lifetime of stacks for heavy-duty trucks. Here we really wanted to understand how these stacks degrade. And we aim here, and that's quite tough, I have to say, for 30,000 hours of durability for the truck sector. And we got a successful project, so that's good. The next topic we had was the standardized size fuel cell module for heavy-duty applications. And here our aim was really bringing together the fuel cell suppliers and the OEMs, really in a big consortium. And we managed to do that. And the key point here is, of course, fostering economies of scale. We want to make plug-and-play systems and also, of course, create competition that will, at the end, reduce the costs. Also here, we got a successful project. The next one is on the infrastructure. There we really had a topic to scale up and demonstrate innovative hydrogen compressor technology for full-scale hydrogen refueling station, because we know that the compressor technology is one of the weak points in HRS, so we need to work on that. And of course here for heavy duty we need to upscale and new technologies for such a kind of compressor technology to put in an HRS, because they have to demonstrate that this hydrogen refueling station will need to be able to refuel at least more than 200 kilograms per day of hydrogen. And the fourth topic was a feasibility on liquid hydrogen onboard storage for heavy-duty vehicles. Unfortunately, we didn't got any successful project. There was interest from the industry. Unfortunately, none of the proposals were successful. But we believe also in the FCH JU that liquid hydrogen is a very important topic. And I'm sure that in the next partnership, we will keep working on liquid hydrogen. Finally, we're working on refueling protocols and business models. And in the refueling protocols, we have the project Pride. And here we develop really refueling protocols for vehicles with compressed hydrogen storage system. So above 250 liters and above 10 kilograms of storage. The idea here is to really identify factors that limiting the refueling rate, because we really need larger flow rates to refuel those heavy-duty trucks. Obviously, any finding, recommendation that we will have during this study or this project, we will share with the relevant sectors and also the standardization committees. But also very important in this here is international cooperation. And already today, we are working together with companies from Japan, companies from the US in this project, because it's crucial to make sure that worldwide we have the same refueling protocol as we have in the cars today. And finally, we also issued a tender to study the business cases for hydrogen fuel cell trucks. Such a study was really necessary to look and understand well where and how hydrogen fuel cell trucks fit among the competing technologies that we have today and really the decarbonization of the heavy-duty sector. This study was executed by Roland Berger and Yvonne Roef, who is actually the partner and the global lead on the hydrogen topics in Roland Berger, will now explain to us the results. Yvonne, the floor is yours. and I'm looking forward to hear all the fantastic results that you have achieved in this study. Thank you.
Thank you very much, Bart, and thank you for the introduction. Yes, we've had a fantastic study, obviously with the objective, as you had just outlined, Bart, and I'm trying to click forward in the presentation. One slide. Sorry. Yeah, I can see it's working now. I'm trying to get a handle on working the presentation, which I can't right now. So apologies. Could somebody click one slide forward? I'll try and fix it as we go along. Now, we've had a fantastic project, as you said, Bart. Thanks a lot for the introduction. And on the objective slide, on slide 1 after the deck, you see that the objective really was, as Bart said, developing business cases, analyzing costs, calculating detailed case studies, and understanding what are potential barriers to the rollout of heavy-duty fuel cell trucks in Europe going forward. And going to the next slide, you see we've done this with a huge coalition and an advisory board of companies of different backgrounds, automotive OEMs or truck OEMs, technology suppliers, the operator side, the logistics side, as well as hydrogen suppliers and infrastructure suppliers. And we've relied on support from them greatly to go through the study and to provide a lot of very, very useful insights. And I'd like to present you the results of this project as we go along. And now you're going to need to give me 2 seconds, apologies, so that I can find the presentation again here on my clicker, because I can actually not see it in WebEx. Otherwise, I don't know where we are. Apologies for that. Right, I have it in a second. Sorry for that. We had a technical test and it worked. Now it's connecting to the client and I can see it now. Perfect. So I'm trying to click back. Right, there's a bit of a lag in it. Perfect. Now I've got it. Thanks for your patience. So we've worked on this study with, as you can see, a whole set of advisory board members that have contributed greatly. So thanks a lot for all the contributors to this study. I think it's a great impact on the market, and we've had some very insightful results, which I'm happy to present to you now. Now let's take a look very briefly at the actual sector. 6.6 million heavy and medium and heavy duty trucks are on the roads in Europe every day. And the market with 300K new sales every year is quite large. In total, this actually contributes to 5% of total CO2 emissions. And within the specific road transport sector of trucks, it's 27% of emissions. And as you can see roughly from the map, there's transportation corridors where these heavy-duty trucks drive, so they have a huge role to play in decarbonizing emissions in Europe. And that's actually what's on the agenda. Within the European Green Deal, as you know, the objective is to reduce 90% of emissions, of transport emissions, until 2050. And there's a lot of directives, a lot of specific directives on EU level that are being supported and set out to develop regulation for decreasing emissions. And there's lots of approaches on different national levels. And we've just depicted a few here, with basically low emission zones being the most important one in all of these countries that we've depicted here. And this obviously creates a huge need for the operative sector and the sector using heavy duty trucks and operating heavy duty trucks to actually move forward and try and think about new technologies. Now, what is this? What are the alternatives and options? And you see right here an overview of alternative powertrain options for heavy duty trucks that exist. In the study, we've looked at them. We've obviously focused on comparing the reduced or zero emission option powertrains, and we've basically benchmarked these technology based on costs, on performance with diesel technology, with the established diesel technology. And what it shows is that fuel cell electric heavy-duty trucks are superior in terms of operational flexibility, because you can refuel them very quickly. You don't need, like in catenary applications, large and very costly infrastructure to run them. And in relation to battery electric vehicles, you have an increased option for payload, simply because the powertrain such is a bit lighter than the powertrain, or especially the battery of battery electric fuel cell trucks. And I'll present the results of the comparison to you going forward. Now, looking at the different technology options, you can see that they're all in a similar technological readiness level in general, with fuel cell electric and battery electric quite close to each other, both having a very sort of full emission reduction potential if you source the electricity or the hydrogen applied from renewable electricity entirely. But the technological readiness level of low carbon fuels is obviously still higher. That of catenary and trolley applications still a bit lower. There are some trials going on as well in Europe. So it's a very interesting alternative, but especially regarding the infrastructure requirements, quite intensive on the requirements for build out. And that's that way also very costly. Let's look at the TCO and the results of the cost comparison that we've done going forward. Now, you can see here on the slide one specific use case. In this study, we have defined 3 use cases of heavy-duty truck applications for which we've done the analysis. And this is the heavy-duty, the use case 1, which is a 4x2 tractor, is basically the use case that presents around 30% of the entire heavy-duty market. That is a long-haul use case for international, national logistics. Then we have one for intermediate haul and one for short haul, which is more on the distribution and regional side. So what you see here are the results for this first use case, the long haul heavy-duty use case. The others are comparable, by the way, just in case you were wondering if you can't see them. And what you see here is a comparison of TCO based on a Eurocent per ton kilometer. So it factors in the payload capacity already. And if you take the results, we've basically, at the bottom you can see, compared the different technological options of diesel e-fuels, and then fuel cells at a refueling intensity or storage intensity of 350 bars, 700 bars, and a liquid option as well. And then compared to the battery electric and the catenary fuel cell vehicles. And the orange line is a bit of an orientation that shows from 2027 in our scenario onwards, you can reach cost competitiveness with diesel. That is assuming that quick production volumes are being ramped up quite swiftly. Although in 2027, we assume we're still in a rather niche scenario of around 5,000 stack production per OEM. And in 2030, we assumed a rather mass scenario. And we've basically compared the different technologies with those assumptions in mind. And what you can see here on a TCO basis, really, if you take the year 2027 for fuel cell electric vehicles at 350 bar, you basically reach, or you're actually in terms of the TCO, slightly lower than that of diesel. You're within comparable range of a 700 bar vehicle. There, the driver for additional costs is mainly increasing hydrogen storage costs as well as a reduced payload. And for the liquid version, it's within the same range. And what you can see here quite clearly is that the comparison on this payload base factor TCO with battery electric vehicles obviously fares much better for fuel cell electric vehicles. On catenary, as I've mentioned, the main cost driver here is really the infrastructure requirements and infrastructure rollout. Hence, the costs are expected to be much higher also in 2030 going forward compared with diesel. Now, let's look at this in terms of a market potential rollout. And what we've done to come up with a market assessment is basically we have defined for these use cases, if you take these assumptions for the TCO, what could the uptake, the market uptake for heavy-duty fuel cell trucks be? We've conducted a set of interviews. We've basically also made transparent our TCO analysis. So this is basically based on the TCO assumptions, the potential that we see. As you can see here on the slide, the total market potential the total heavy-duty truck market potential could be covered by fuel cell, or the fuel cell heavy-duty vehicles could cover up to 17% in 2030. That's the entire market that you get. We've put a bit of an estimation of BEV sales on the light gray version above, where you can clearly see it. We estimate that it's actually a bit of a smaller share. This just shows that the role for heavy-duty fuel cell trucks can actually be quite positive. This is a base case scenario. We have an optimistic scenario where this can actually go up to a 30% market share, but we've decided to show the base case scenario here, simply because it's the straightforward one in that sense. We also have a more downside scenario, but we believe with the technology potential and cost assessment that we've made, it's absolutely fair to look at a base and optimistic scenario. And there's one thing I'd like to mention here that you don't see in terms of market potential. When you only take heavy-duty fuel cell vehicles within the segments where these use cases are based in, actually the share in 2030 is around 50%, simply because we expect that the rest will be covered by BEV and by other reduced emissions technologies. But the share, as mentioned, within that specific segment is actually high. You don't see that because we've depicted the entire heavy-duty truck market here in the EU. So quite an interesting market development. And if you accumulate the blue figures of the role that FCEV could play until 2030, you actually get to around 100,000 trucks on European roads, fuel cell trucks on European roads until 2030, which is, I think, quite a positive outlook for emission reduction potential, but also for the industry. And obviously they play, as such, with this potential, a huge role in decarbonizing the emissions in Europe. We've basically continued on this trajectory with the market uptake rate between the years going forward to 2050, and taking an assumption that basically the gray area, the little gray line on the top of the slide with the white space in between, is basically other segments, not the heavy-duty truck segment in the 3 use cases we looked at. You can see that basically most of it will be catered in our assumption by battery electric vehicles as well as fuel cell vehicles. And that obviously has a huge impact on reducing emissions and reaching the goal of climate neutrality in the EU by 2050, as well as reaching the goal of reducing 90% of transport emissions by 2030. We've also done very practical analysis in the context of this study. So we've defined case studies, 9 case studies in all of Europe, together with the support of heavy-duty truckers in all of Europe, together with the truck operator 6 companies, as you can see here. And we've calculated detailed business cases, detailed use cases for each and one of those, the ones that we've defined. And you can see we've done that for the 3 use cases of trucks, truck applications. We've made sure to have a different or heterogeneous geographical footprint in all of it. So we've included countries from France to Sweden over Spain. So, and basically have analyzed in detail what the costs and what the infrastructure requirements, as well as the actual story for these use cases could be. And bottom line for all the use cases is the following. Obviously, a lot of these operational truck operators are assessing their opportunities for emission reduction. So that's one of the greatest drivers, and we've heard some broad interest in actually operating heavy-duty fuel cell trucks, provided that the tests and the demonstration projects that are currently ongoing actually show very good results. But all of them are looking at either battery electric vehicles or fuel cell heavy-duty trucks. And all of these case studies have basically underlined that it is operationally very positive to deploy heavy-duty fuel cell trucks, and that the case for actually doing that in all of those European countries is absolutely given and positive. You can actually, if you're more interested in details of these use cases, the results will be published in due course with the FCH JU, and you'll be able to read through all of these use cases if you're interested in one specific region, for example, or if you're interested in some of these specific assumptions. And by the way, that holds for the entire presentation or the entire project. The publication with the detailed information will be made available in due course. So bottom line of the story, these use cases show that the application is very well put into use in all of these areas. And what we hear, as mentioned from the operators, is that provided that the demonstration projects that are currently being done in Europe will be looked at intensively in order to understand whether this can actually be a case for ramping up and rolling out fuel cell vehicles in their operations. As you can see, Europe is really at the forefront of fuel cell and heavy-duty truck demonstration projects, with basically 9 projects in North America. In some, I think overall 12 relevant projects we've identified in Europe and 2 in Asia, basically trying to test the technology on the ground now, test it within a real-life situation in an ecosystem where hydrogen production and refueling is available, but also then the use of fuel cell heavy-duty trucks for specific logistics applications is being developed. And you can see most of European countries that are participating in these demonstration projects are more in Western Europe. Obviously, I think the challenge here is to roll out some of the ambitions that Eastern and Central European countries have also in rolling out their emissions. And we understand from discussions that we've had with operators that obviously with the need to decarbonize also there's high interest in deploying some more R&D or demonstration projects also in that region. But overall, very balanced, showing that in Europe, there's a very clear focus on demonstrating the feasibility of this technology as well as its viability on the roads. We're not there yet overall. We've looked at and identified some barriers that still exist for the rollout of heavy-duty fuel cell trucks in Europe. And just to mention upfront, there are some barriers, but none of them have been considered as showstoppers, to be quite honest. They are quite known, I think, to the industry side as well as to the public policy side. And I'd just like to highlight those that we've categorized as being of high importance, that will need to be addressed with a strong focus, and that can also point to developing research projects around it. So the first one is really continue in product development and systems integration, optimizing the systems to optimize the technology going forward further and reaching a further technological readiness level. The second one, or number 7 here, is the standardization of storage technology. And that is very much linked to number 10, the refueling networks, and number 12, the standardization of refueling protocols. Because as you've seen with the TCO slide that I've shown earlier, there are still different storage options around that will point to very different refueling protocols. And I think from a public perspective, it's very difficult to support the rollout of a hydrogen refueling infrastructure if it's not quite clear whether the standard will include 350 bar or 700 bar, which will be more, or whether it could be liquid hydrogen. Currently, there's technological openness. I think that makes a lot of sense from an R&D perspective and from a demonstration perspective. But if you're thinking of financing and de-risking a European or a national hydrogen refueling network, in terms of operating efficiency and commercial viability, it warrants some discussion around standardizing this refueling protocols. Number 17 and 19, i.e. the other two on the high priority list, are basically financing and funding support and long-term planability. Now, financing and funding support obviously points to the fact that a lot of these projects are not yet fully commercially viable in all of European countries, although we're seeing projects ongoing, for example, in Switzerland, that are built very much around a commercially viable case, which is also due to a different levy on internal combustion engine applications there. So with some policy reform, we could move forward to commercially applying these technologies, and I'll talk about the policy angle in a second. But financing and funding support in areas where it's not commercially viable yet, and that's mostly all over Europe, is really, really important in order to propel investment, in order to roll out use case projects or demonstration projects, as I've mentioned, in other areas of Europe as well, in order to test the technology, and in order to make sure that the infrastructure, the refueling infrastructure, is in place. And I've just mentioned as one example, developing a hydrogen refueling network is not commercially viable at this stage yet. So also here support is needed, because in order to create sufficient demand and sufficient uptake willingness of the operation side, that will need to be put in place. Now, luckily, we've seen this year, sort of from a European perspective, 2020 has been a big bang on hydrogen strategy year, greatly with the EU hydrogen strategy and various other countries announcing their plans. And we've seen a lot of financial vehicles and money being basically allocated to support the rollout of the industry, to support the development of the industry and the hydrogen economy in Europe, which is great news. I think what's also really important is that there's been a shift from not only supporting CapEx, but also supporting operational costs, which obviously for the especially operational side, logistics companies, etc., is hugely important, because a lot of the times it's not the CapEx that's the huge hurdle or the barrier, but it's actually the long-term operational costs that can incur a negative EBITDA over some years that obviously is not quite pleasant on the balance sheet. So here I think there's movement into more flexibility, more creative direction in also focusing on operational cost support. And then obviously long-term planability as a last point on high on the priority agenda is really important for investment and for technology development going forward. And here I think the context of the European hydrogen strategy, as well as the announcement that have been made, are hugely important and have provided some clarity for the market. But in terms of technological questions, as I've just mentioned, the standardization of the storage technology as well as refueling protocols, some more cornerstones will need to be found here in the short term in order to create the necessary framework conditions and stable planning. In terms of the medium and low barriers, they are all, I think, viable. They're all quite known. These are all addressable topics. The question is just how fast can one move forward, and how fast can it be addressed with which instruments. We've basically taken this and have thought about what the next step could be to bring this further. So the study as such suggests 4 R&I projects that address some of these barriers, obviously going forward. The first is around optimization of powertrain, of the technology, optimization of the standardized onboarding hydrogen storage systems, as I've mentioned, and the refueling protocol development. So the whole question around 350 versus 700 versus liquid hydrogen should be addressed going forward. The second project area where we suggest something be undertaken is basically to continue developing the fuel cell truck and powertrain prototypes to integrate and standardize the technology and to be able to scale up stacks. And the third one is a cross-border multinational demonstration project. It's one that is more directed at the use side, at the operator side. We hear a lot of interests, not only within this study, but also with other discussions with clients we have, that there's lots of interest in participating in a demonstration project that's actually cross-border. And as mentioned here, not only in Western, but also moving to Central Europe countries. So I think that is an area that can definitely propel the acceptance of the uptake of heavy-duty fuel cell trucks from the operator side. That can propel that further a lot. And the last area is really doing some more work on the technology development for throughput and low footprint of high energy efficiency for HRS for heavy duty vehicles. And I've mentioned that already, the refueling protocols are still very heterogeneous, and the requirements here from the industry are still heterogeneous. And in the end of the day, the faster one can get to a concerted effort, to a plannable decision, as well as a financing vehicle that de-risks investment, the better. Obviously, that can also be public-private partnerships where the government de-risks a larger part for the hydrogen refueling infrastructure. But this is key for uptake as well of the operator side. And the location of these stations, obviously, that's a discussion that will need to be taking place in a project in the Area C here, and the cross-border multinational demonstration projects could be clearly along the core transportation corridors in Europe, the golden banana, the blue banana, and then the east-west connection, obviously. But also when you look at demonstration projects that are currently being announced, that's already being taken into account widely. Last point on the policy side, as mentioned, I've mentioned the Switzerland approach with a policy framework that increases the price or the cost of usage of fossil-based fuels such as diesel or gasoline. Obviously, that is a huge lever to reducing TCO for fuel cell heavy-duty trucks. And there's the Eurovignette reform and directive that's in discussion is, I think, one of the concrete vehicles to actually offer an exemption for the road toll for zero-emission vehicles for longer time periods. That has quite an impact on the TCO for operators. So that, I think, is a huge lever, and we're very much looking forward to the final deliberations and the decisions on that. But as mentioned, other areas, I think infrastructure coverage and infrastructure de-risking is an area that needs to be looked at, because especially from the use side, the argument we need to be sure that we can refuel at certain points, that our drive cycles are still valid across different countries is a valid one, and that should need to be addressed. On national levels, there's various policy angles to look at. You could, for example, exempt levies and fees for the production of green hydrogen. So going back to the entire value chain of hydrogen on the production distribution side as well, not only on the end application and usage side of heavy-duty fuel cell trucks. There are various vehicles that can be used and that are used or that are being announced by national governments to implement cost support measures. For example, as you probably know, Germany has announced within its hydrogen strategy to implement a carbon contract for difference scheme, which especially for the production of green hydrogen would be a large supporter. So I think it's really up to taking the national government strategies and also the EU strategy and supporting in operationalizing the ambitions and the concrete announcements very quickly in order to propel the sector bringing forward. But the framework is absolutely there. So overall, bottom line, the story is that we see huge potential for fuel cell heavy-duty truck vehicles, as mentioned, basically coming from technological, operational, and cost arguments at this point. And it can simply, as it is, play a leading role in decarbonizing transport in Europe. And I've outlined, I think, what the next step would be to propel the sector and to overcome some of the barriers that still exist. But overall, we're very optimistic of this application use. As mentioned, we have conducted this study together with colleagues from the FCH JU. Here are the contacts in case you would like to get in touch in the following and discuss some questions that you have. I've also mentioned that the entire results will be made available in due course, where you can basically have a look at all the detailed assumptions as well as the broader amount of results, and there's much more material, too much to present it in such a short time frame. Thanks a lot for your attention.
Thank you very much, Yvonne, and also Roland Berger, for this really perfect and extensive explanation. And it's really great to see such a huge potential for hydrogen fuel cell trucks. I see on my watch we have still 2 minutes, so if you're okay, because I see that a lot of our audience have asked a lot of questions, as you can imagine with such a study. So I just pick one of two out of them. I'm sure the panel hereafter will take care of some other questions, and maybe they are solved. But anyway, please to the audience, do not hesitate to put more questions also in the Mentimeter. If there's time, we will pick them up. But one of the first questions to you, Yvonne, is the use of multiple automotive fuel cell stacks in replaceable modules a viable technical and or commercial alternative to heavy-duty long-life fuel cell stacks for heavy trucks? Is that a solution, to use the fuel cells from cars, put them in the trucks? That's basically the question.
We've made that assumption for the stacks that we have used. Our main assumption and cost assumptions are based on a 120 kilowatt stack that we have for cost assumptions just extrapolated to a 330 kilowatt stack for the heavy duty truck use case 1 that we applied. So yes, to give you a short answer.
Thank you. Another question was about using hydrogen in internal combustion engine, and you can imagine that many of these questions were there. Just I pick out one, is that for zero greenhouse gas emissions, are hydrogen trucks with internal combustion engines considered as a viable option? There is an increasing interest, and their maintenance would be very similar to diesel trucks. What's your answer on that one?
We have deliberately not included it yet because it was still technological-wise at a very, very early stage. Obviously, there are advantages around it, but I think within this study, as mentioned, we had in the beginning decided to focus on the more obvious comparison alternatives for zero emission, which is battery electric vehicles straight away, and then the various fuel cell stack options and refueling and storage options. So it was simply also a matter of scope why we didn't really look at them.
Okay, so time is up, Yvonne. Thank you very much for your explanation again. And okay, I think now it's time to go to our panel discussion. So, and I'm very proud here to introduce the moderator of the panel. She is the chair of the FCH JU governing board, and also the board member of AFIPAC and Avere in France. Actually, some people in France call her Mrs. Hydrogen. She's a true power lady with many nominations and awards in the field of renewables and transport. She has a solid 20 years experience in the automotive field and holds a master and executive degree in international management. She is also one of the founder of the Automotive Association, which calls WAVE, which stands for Women, Automotive and Vehicles in Europe, whose mission is to attract more women in the automotive industry. And myself, coming from the automotive sector as well, I can only agree that we need more women in automotive. That's clear. Anyway, it's my pleasure and big honor to introduce you this amazing woman, Mrs. Valérie Bouillon-Delport. Valérie, the floor is yours.
Thank you, Bart. Thank you very much for these very kind words. Highly appreciated. But I'm so delighted to moderate this panel with representatives from the whole value chain of hydrogen when it comes to hydrogen trucks. So first, let me introduce our panelists, starting with Martin Daum, so Chief Executive Officer from Daimler Trucks. Then we have also Jon-André Locke, CEO from Nel. We also have an end user, which is very important. So welcome Jean-Christophe Maché, CEO of FM Logistique. We also have from the component side, Christophe Offrère, Chief Technical Officer from Faurecia. And last but not least, Marco Liccardo, who is also a board member of Hydrogen Europe, together with Jan, head of trucks, global product line, CNH Industrial Iveco. So we'll come and we'll have an extensive exchange with these gentlemen. But first of all, I want to explain why we're gathered today. So you understood that we have this study on hydrogen trucks being launched, and Yvonne has already shared with us some of the few key outcomes. So I must admit, I'm looking forward for the full publication expected to be in December. But in the meantime, I think we have no doubt the hydrogen momentum is there. And we all understand that hydrogen has a strategic role to play in order to achieve a Green Deal carbon neutrality targets by 2050. And all the options are to be put on the table. We need to keep this technological neutrality because at the end, it's the usage which will decide which technology fits the usage. So we need to keep the option open, and hydrogen probably in a heavy-duty mobility will play a crucial role. The study publication is really, it's the perfect time because it comes ahead of the release of a sustainable and smart mobility strategy on December 9th, and it will lay the roadmap of the transport sector for years to come. So that's a very good timing. But I must insist, like you did at the beginning, Bart, the projects have already started. And I can name a few. You already named a couple of them. So H2O, which is a program being funded by the FCH JU. You mentioned also Revive, but we have also Hytrucks, a project announced by Air Liquide and Port of Rotterdam in July 2020. Whose objective is to have 1,000 trucks on the road by 2025. And we also have the project mentioned by Yvonne in Switzerland with Hyundai and H2 Energy, which aims to deploy 1,600 heavy-duty vehicles, and 50 will be delivered and have started to be delivered before the end of the year. So we're not waiting for 2030, and that's a very important message I would like you to take. We have already started now, and by 2025, we expect a few thousand trucks ready to be on the road, and not only in Western Europe, but also in Eastern Europe. But to achieve that industrial competitiveness, we need companies. We need the companies to be competitive. So let's ask our panel speakers to share with us some key elements. So, gentlemen, let me remind you the rules because we are under constraint in terms of timing. So I will ask each one of you a question, and you will have 5 minutes to answer. So my first question is for you, Martin Down. You have presented your fuel cell truck 2 months ago, and you announced a partnership with Volvo on the fuel cell with the upcoming joint venture. So what are, in your view, the main technologies to be considered to achieve the Green Deal objectives? More specifically, what do you expect from the European Union, but also from the stakeholders from the supply chain, to accelerate the market uptake of fuel cell trucks in the near future? Martin.
Yeah, thanks for letting me be part of this panel. I think it's absolutely important. I highly appreciate the work of the Hydrogen Europe to prepare the cause for hydrogen. When it comes for a CO2-free European transportation sector, there's and when we talk CO2-free, there are only basically two energy sources. One is battery electric, and the other is hydrogen. And hydrogen is, for me, just one step into battery electric, because here you produce electricity on board of the truck with a faster refueling possibilities. So other than battery electric or hydrogen, there's no other technology available at the moment to get CO2 free without having an infrastructure like catenary trucks or so, which makes no sense. So we need we need hydrogen. The big question is, and Daimler is committed to the fuel cell since 25 years. In my own biography with Daimler, I was involved 1996 in the first attempt when we had a major stake in Ballard Power in Vancouver working on fuel cell. The big question is, why did it never come to an end product? And I would say the challenges why from then to today it never came to an end product are still the same. Because we have a well-functioning fuel cell inside the Daimler Group, so well-functioning that Volvo was eager to join our partnership, paying a significant amount of money for a 50% stake. We took Volvo in because one of the big problems in the past was that we never had enough scale, we never had enough cloud to get the missing elements for fuel cell, for hydrogen infrastructure going. Because we need three items parallel. And if one of the three items is zero, the entire product is zero. It's like a mathematical equation. Now, it doesn't matter how large the two factors are if a third factor is zero in a multiplication. So the one factor is a compelling industry offering. And we have that. And we're building and we're going fast. And we will have several thousands of fuel cell trucks on European roads before this decade is going to end. We built an extremely large fuel cell stack factory. And we already started the planning process, and we'll have a capacity to really equip several 10,000 trucks with fuel cells in the years to come. Annually, by the way. So I have no doubt that this attractive industry portfolio, and I know others, the colleague from Iveco is on the screen, and I know they are working on it. So I have absolutely no doubt that there will be a comprehensive and attractive fuel cell offering in the market. But the other two, and I have to come to the finish because I watch the watch as well. My time is running out and I want to be disciplined. There are two more things. The one is we need an infrastructure, and that is why the first fuel cell never caught on. We don't have an infrastructure. We need that infrastructure. And the infrastructure challenge, in my opinion, is significantly bigger. And if I look at the money involved as necessary investment, it's still huge on the truck side, but it's 10, 50 times more and going into the double-digit billion numbers to get that infrastructure with green hydrogen going. And secondly, we need a cost parity. And I have absolutely no clue how cost parity ultimately will be reached. I read the Roland Berger study, but I think there's a lot of wishful thinking in. It all hinges around of the future price of green hydrogen. Can we get a price that is between 3 and 4 euros per kilogram on green hydrogen, knowing the double-digit billion investment necessary? The fuel cell trucks will be significantly more expensive, and believe me, than today's diesel trucks. And we have done studies, and I put in not the actual numbers, I put in the numbers we target for in the second half of this decade. So in my opinion, the CO2-based toll system in Europe is absolutely necessary to ultimately get a cost parity. And always remember, if one of the items is missing, the entire product is zero. Broad industry portfolio, broad infrastructure, and cost parity. And at the moment, we have 3 zeros in that whole equation.
Thank you, Martin. The timing is perfect and 5 minutes sharp. So now we move to Jan Nokke, CEO of NEL. So Jan, the infrastructure will obviously play a key role in the realization of the scenario described in the study. And today's HRS network is mostly aimed at light delivery vehicle, and it was not conceived with an European perspective in mind. So the number of HRS seems to be not sufficient to support a heavy penetration of heavy duty today. So the question to you is, how do we go from where we are today to achieve an infrastructure network that can sustain an important fleet of trucks by 2030? And what are the intermediary steps you are taking to make this happen? Jan.
Well, thank you very much for having us. Very much appreciate that, and thank you very much for a great presentation, Yvonne, related to Roland Berger's work. I think that there's a lot of value in that. When it comes to the infrastructure, obviously, we are technology suppliers that delivers infrastructure, and so I will try to focus on that. But let me start by mentioning the coalition statement that has been signed a couple of weeks ago, which basically is the coalition statement on the deployment of fuel cell hydrogen heavy-duty trucks in Europe. And this is a statement which has basically been supported by the OEMs, by the technology providers, by infrastructure, by truck operators and owners, etc., etc. And we certainly, all of the parties believe that we can do it. You know, we can deploy 100,000 fuel cell trucks that aligns with the 10T corridors, and we can build 1,500 fueling stations. Now, the protocols are currently under development. We are working together with Toyota, Hyundai, Shell, Nel, and a few others to develop the fueling protocols. So that's under development. That includes the receptacle, the nozzles, and those elements. And for me, it's very important to let's not make the perfect solution the enemy of the good solution. Let's start with what we have. We have a few OEMs that already have equipment ready to go on the road. So let's support those. Let's support the OEMs that have taken the initiatives and has been able to develop the technology and are ready to go at the moment. One of them is Hyundai, currently already deploying trucks in Switzerland, but there are also others here that are ready to do. And then we use the technology that we have. It's not a perfect solution, but it's a good solution. And it can at least support the first few thousand trucks. 350 bar, it can fuel 30 to 40 kilos very quickly, 500 kilo per day. And it's a relatively robust and cheap solution, and it's used in bus depots all over the place. So it's not something new. So we start with that. You will only get 300-400 kilometers out of it. The OEMs want to go to 700 bar. We are already developing that. I'm sure others are also doing that. Bart talked about the support from FCH JU. We are very grateful for their support also into developing that. And soon we will have technology that can fuel 700 bars, almost 100 kilos in each load, 1,000 kilos per day. And it can do it in as close to 10 minutes as possible. And that will give you the same exact properties as with a diesel truck. You will fuel exactly as fast, and it will take you the same range as a diesel truck, and you will eliminate the detour on liquid. You don't have to go that way, and therefore you will be much more free. You don't have to rely on a huge liquid plant from one of the gas companies. You can actually do it based on your own abilities and your own windmill and your own technology. So that's really the way to go. And the bonus here is that each truck fueling site can also fuel cars. So when you build the infrastructure for trucks, you will automatically get an infrastructure for cars. And obviously, the biggest problem with the chicken and egg is what comes first. But here you are talking about fleets. We're talking about truck fleets. So you've sold the chicken and egg because the trucks come at the same time as the fueling station, or very close to. I mean, you don't have to sit and speculate for months and quarters to wait for cars. You basically know when they are coming. So that would be my advice. Get started, support the OEMs that are ready with equipment. Start with fleets, 30 trucks here, 50 trucks there, 100 trucks there, and get started. And then we will launch and upgrade the stations so that they can support more and more trucks and more volumes over time. And when it comes to the cost parity, which was mentioned here, most of that is tied, at least when it comes to the fueling station infrastructure, most of that is actually tied to utilization. If we have high utilization, you're already there, pretty much. Thank you.
Thank you, John. Very enlightening. I think we move now to Jean-Christophe Maché. Jean-Christophe, I see that your camera is not on. So if you could put your... Okay, that's fine. Thank you. So, Jean-Christophe, you're an end user and you are probably technology neutral. You probably just want the best technology that will allow your profitability and at the same time allow you to decarbonize your fleet. So the question to you is, why are you interested in the fuel cell option, and how advanced are you on the use of fuel cell in your own company? And the second part is, after following the preparation of the study, looking mainly into the TCO, do you feel comfortable going ahead with this technology option?
Thank you, Valerie, for investing us for this meeting. It's important for us to think about transformation of the supply chain to have a greenest supply chain. So, FCH for us, it's obvious because it's one of the solution to have a significant impact on the supply chain. As we know, we have our vision is to offer a sustainable supply chain for our customer, and for that we have mainly two levers. First, we have to co-design with our customer and with all the stakeholders the most efficient supply chain, sustainable and greenest. So we have to reduce the CO2 emission. For example, for sure, we have to fulfill the truck and to avoid to have 13% of the truck empty on the roads. So first, we have to co-design the supply chain to be more eco-efficient. And for sure, the second lever for us is to decarbonize our operations in transport and in warehouse. The transport emission are 2/3 of our emission. So it's the biggest priority for us to have a significant impact and to decarbonize transport activities. We want to reduce the emission of CO2 in our warehouse too. And we started already, and you're right to say it's now. And we started already some concrete action with hydrogen. 6 years ago, we started to work with hydrogen battery for wood truck in 2 facilities. We started to manage some distribution with hydrogen trucks in China, and we will start in 21 with 15 vans in Spain, and I will come back later now to speak about a concrete action we started in June this year, and I hope we will deliver a fantastic international project in Orléans named H2 Hub, because we want to use the fact we have our own facility with the capacity to have panel solar on the roof, and we want to produce a green hydrogen on our own facility. We will use this hydrogen for our truck, and what we want till 2023, we want to have finally like a public solution, because it's impossible for nowadays it's impossible to solve and to tackle the concern of this subject alone, and we want to create an ecosystem with a right balance between publics and private company. So we have the project to to deploy an electrolyzer inside our facility with a hydrogen filling station. And we want to offer to the different sites we have around Orléans, 8 kilometers around Orléans, some hydrogen solution. And we want to offer to the different city the solution for the truck, for the car, for the public transport, for the garbage transport, and already some other partners, 3 factories, ask us to use this hydrogen to transform their fleet, fleet inside the warehouse, and the vans, the small trucks they use around their facility. So for us, it's key to take our part, means to carry our responsibility and to develop this solution. And for that, we work with the local authority and as a local partner. Okay, we are a perfect bridge between local action with international support to invest and to develop an economical solution to offer a greenest supply chain.
Thank you, Jean-Christophe. I'm afraid we reached the limit in time. So now we move to Faurecia, to Christophe Aufrère. So, Christophe, Faurecia, we all know, has been very active in the recent year in the area of fuel cell system, encompassing the tanks, but also the fuel cell. And I'm referring here to the joint venture you have with Michelin for the fuel cell system. So, when we say 2030, seems a long way, but 2030 is tomorrow for automotive tier 1 suppliers. So are your system and are the fuel cell system globally ready to provide the components needed for heavy duty application in the short term? So before 2030, and are they prepared to address these increased volume? Christophe.
Okay, so thank you very much. So yes, we are ready. So I don't know if you have another questions, but I'm joking. So maybe to remind you what is our current perimeter. And today, Faurecia is currently engaged in developing a fuel cell stack systems through its JV with Michelin called Symbio, so fuel cell stacks. And on the other hand, hydrogen storage system fully owned by Faurecia. So this is our perimeter, and we represent something like 60 to 65% of the fuel cell system, I would say. So in terms of investment, so we have already invested around 200 million euros in the fuel cell technologies. It will continue. And we have recently unveiled also in October a world-class expertise center in the east of France for hydrogen storage system. It includes last hydraulic and gas pressure testing technologies. In terms of products, so for the fuel cell stack within Symbio and hydrogen storage system within Faurecia, we are developing different product generations with improved technologies, enabling us to be at the best technical level as well as, of course, for cost moving forward. We know that, of course, the technology are not already existing for all, that there will be different generation of technologies. We know that, for example, for bipolar plates, there will be new technologies. We know that for winding technology, for the fuel cell tanks, there will be also new technologies. So this is why we have different generations of fuel cell stack and hydrogen storage system. So we are already in production for fuel cell stacks for light commercial vehicles and more to come. And we have homologated also for our hydrogen tank system, so 350 bars, which is already used today for the trucks, the heavy trucks, and 700 bars as well. And we have started to see a shift also to 700 bars for trucks. So we have a next generation of fuel cell stack for heavy-duty vehicles in normally 2022 with a
level of durability. So coming back to what Roland Berger has said, we are not sure that it is worth to have the same kind of technology for both light vehicles, I would say, and heavy-duty vehicles, because there will be maybe a different kind of optimization in terms of cost and overall performance. And we know that we have to get something like 20 to 30,000 hours for heavy-duty. And for conventional light vehicles, it's more around 6,000. So maybe the technology will not be the same. In terms of business, so Forcia already got the first orders for high-pressure storage system of heavy-duty vehicles with Hyundai, representing 1,600 trucks and 10,000 tanks. And we have strong ambitions, of course, with many other OEMs in the coming years. So this is what we are looking for. In terms of industrial capabilities, I would say, the first industrial capacity for several thousand of tanks and fuel cell stacks per year are already set. So we are already producing, we can produce, we will produce more in 2021. However, we need to scale the industrial process to cut drastically the cost, and we think that we can decrease by 5 to 10 times the cost of our product, combining, of course, product optimization, and we have still to work on the product, and on the other end, the volume effect. In terms of competitiveness, the scaling of the industrial process combined with the optimization of the cost of the infrastructure and the green hydrogen price will demonstrate certainly total cost of ownership competitiveness of hydrogen heavy-duty vehicles compared to diesel. So it will be between 2025 and 2030. So we agree with Roland Berger. So we see that the curve are crossing between both, including also the battery electric vehicles. So, and to, of course, to anticipate that, we need to know what the ecosystem is doing. This is why also we are belonging to the Hydrogen Council as a board member, but also Hydrogen Europe, and to know whether we'll have green hydrogen at the right cost, because it is key for the total cost of ownership in 2025, in 2027, or in 2030. Finally, so you know that we have filed some IPCEI also a project to concretize our willingness to become a leader for the fuel cell technologies. So we have one for fuel cell stack system and another one for hydrogen storage system. And indirectly, we have also a third one related to low-cost carbon fiber that we have put within the IPCEI from the IRT Jules Verne in France. So as you can see, I confirm that we are engaged, ready, and we want to become a leader in subsystem for hydrogen vehicles. And of course, we'll have the different generations all over the next decade to be at the best level in terms of competitiveness.
Thank you, Christophe. And now we started this panel with Daimler Trucks. We will end the panel with another trucks manufacturer. So Marco, you're a member of Iveco, and Iveco is one of the OEMs that is investing a lot on the uptake of a fuel cell solution for trucks. I'm referring there to your involvement in Nikola and in the H2O project. So last question to you. From your perspective, which are the key challenges to overcome and which are the regulatory opportunities that you see in order to ensure the high penetration of fuel cell trucks by 2030? Marco.
Well, Valerie, thank you very much. First of all, I'm very, very glad to be here. Challenges and opportunities, there are many indeed. Before to touch them, let me give an overview of what we are doing as a company. As you said, we are doing several things. We have been very active in last years in order to decarbonize the heavy-duty transport, introducing solutions and technologies to reduce the CO2 emissions year over year. But now we are facing this unprecedented challenge that is gonna change dramatically the future of mobility, where we think that in this hydrogen will play really the leading role. For that reason, we are developing in conjunction with Nikola Motor our heavy-duty battery electric vehicle and our heavy-duty fuel cell truck vehicle to be introduced before 2023, both coexisting but addressing different customer needs, with the hydrogen very much focused on the heavy long haul as a sweet spot solution. Well, while the big drivers in terms of regulations are especially the drivers coming from the European Green Deal, and also we have now clear limits for 2025 and 2030 in terms of CO2 emission. Our estimation is that to reach the target of 2025, there must be needed a certain percentage of heavy-duty trucks already in 2025 zero emission, and therefore electric and hydrogen. In our calculation, this percentage is around 5-10%. And if we consider the limits for 2030, this threshold is going to be above 20% and beyond. So this is a gigantic challenge, actually. And I agree with Jon, the starting phase will not be perfect, but that's okay because it's a starting phase. Will not be perfect in terms of color of the hydrogen, will not be perfect in terms of ultimate storage technology. But as I said, that's okay. We need to expedite the technology introduction because we need to learn fast, not only in terms of technology, but looking at the ecosystem as a whole. While we acknowledge a premium cost to the technology, is a paramount that the institution will support the industry in order to reduce in this early stage the cost of fuel cell heavy-duty truck, support the refueling station infrastructure, and also the renewable hydrogen supply in order to create this sustainable ecosystem. At the same time, it's crucial that the current legislation is going to remove unintended barriers that today we are facing. Worth to mention the current weight and dimension directive that can have a negative impact in the development and the deployment of heavy-duty trucks, hydrogen heavy-duty trucks. In fact, the maximum weight, but especially the length, can have a negative impact on the autonomy of the vehicle, so not fitting 100% of the different customer expectations. In terms of additional regulatory opportunities, we welcome the European Commission commitment to the hydrogen technology, to the hydrogen strategy, providing also a list of financial tools supporting the private sector. 2021 is going to be a very important year for the Alternative Fuel Infrastructure Directive because there is going to be the revision in 2021. It's imperative that hydrogen is going to be considered as a mandatory fuel, considering the maturity of the technology and the volume expected by the sector. Always talking about the infrastructure, we hope more and more an integration between the 10E and 10T regulations. Let me give you a quick example of this, why is important this integration. We as a company, we are studying very closely a project called Mediterranean Scandinavian Corridor that is one of the major 9 corridors in Europe for transport. Now, this corridor is 6,000 kilometer length and is utilized approximately by 80,000 heavy-duty trucks per year. Now, assuming that 50% of these trucks in 2030 will be powered by hydrogen, a driver to drive smoothly from Sicily, southern Italy to Norway, he will need 218 hydrogen stations along the corridor, each one able to dispense 6 tons hydrogen per day in average. That means 330,000 tons of renewable hydrogen in 1 year, with a saving of 4.6 million tons CO2 per year. That is impressive. Now imagine if we're going to apply the same concept to all the other main corridors inside European countries. The saving in terms of CO2 is going to be really, really impressive. Thank you very much.
Thank you, Marco. Thank you to all the panelists. And I think, Bart, you wanted to say a few words?
Yes. Thank you very much, Valerie, for this very interesting discussion. And it's really great to see that the OEMs are really so confident that they can decarbonize the heavy-duty truck sector by using hydrogen and fuel cells. And it's not only the truck OEMs, but also the component OEMs or the tier 1 suppliers, tier 2 suppliers, and also the infrastructure. So great, it's amazing to have this confirmed. But I'm just checking here to my team because I promised you a special guest today, and I'm checking if my team is the special guest has arrived. And not yet. So maybe we can still have a question. Valerie, do you have still a question to one of your panel members? Because the special guest is still logging in. I see that her camera is not on. Okay, I already discovered it's a lady. That's true.
Maybe. Okay, let's take one of the questions concerning the infrastructure. So why are HRS infrastructure need to be independent for light vehicle and heavy duty vehicle as long as they are both 700 bar? Jan, maybe you can answer.
I think that's a good question. I think actually I answered it in the chat. It doesn't have to be. It can be shared. That's the simple answer. You can easily add a light duty dispenser to a heavy duty station, and that's I think one of the benefits of hydrogen compared to some of the other energy carriers. That you can share the infrastructure, you can share the production, and you can share the dispensing between multiple applications.
Okay, thank you very much. And Valerie, I have good news. Our special guest has arrived. So, ladies and gentlemen, it's a big honor for me to introduce the person who was since 12 years member of the European Parliament, for which she was for a while the vice president even of the European Parliament. And she also chaired the ITRE and the ENVI committee. She's Romanian and holds a master's degree in studies and security and a bachelor degree in mathematics. Since December 2019, she is the European Commissioner for Transport. A warm welcome for Mrs. Adina Vălean. Mrs. Adina, it's a great honor to have you here today, and thanks for making the time available in your very, very busy agenda. And before I give you the word, I believe that Valerie, our chair of the Fuel Cells and Hydrogen Joint Undertaking, has some very important announcement to make for you. Valerie, what do you want to say to the Commissioner and the audience at home? Because I think it will be great news. I cannot wait longer. Please tell us.
Okay, thank you, Bart. Mrs. Commissioner, I mean, we are very honored to unveil the coalition statement in your presence today. And it proves the role that hydrogen power trucks can play to decarbonize the transport sector. And this role is recognized by all the players. So let me remind you very quickly a few key milestones that we did in 2020. The first one was in March when we organized together with DG Move and Director General Enrico Lolei the fuel cell truck event, in which we already gathered the commitment from many of the players in the hydrogen ecosystem. Since then, we were hit by the COVID crisis, but the urgency of tackling this climate change has not faded away within the players, rather the opposite. And not only do we have companies being involved in the March statement, they have made progress in their hydrogen commitment, but additional companies have embarked in the hydrogen journey. So today, we are very proud to share with you the coalition statement. What is this coalition statement about? We're committing to favor the deployment of 100,000 trucks by 2030, and then it's the first step towards massive deployment afterwards, and we expect this volume to double each year after 2030. The second commitment that we make through this coalition statement is to spur the deployment of 1,000 hydrogen stations by 2030 to service trucks. With this statement, Mrs. Commissioner Vălean, we would like to stress the importance of having, first, an integrated approach in the regulatory process to bring demand and supply of vehicle, so in terms of CO2 emission standards regulation. But the second thing is that the infrastructure side needed, with a revision of the AFID directive, with a 10E and 10T guidelines review, as well as affordable clean hydrogen supply. So we're particularly delighted to see the number of signatories of this coalition statement. We gathered more than 60 signatures today from OEMs, fuel cell suppliers, hydrogen technology providers, refueling infrastructure and hydrogen providers, truck operator, road freight services users, end users, and related industry associations. So all the players We'll continue to work hard together to have as many hydrogen-powered trucks on the road, not only in 2030, but starting now. Mrs. Commissioner Valian, that's our commitment today. Thank you.
So, Commissioner, the word is yours now.
Thank you very much. Thank you for the warm welcome. And I would add to my short biography, you have mentioned the fact that I'm a friend of hydrogen for a long time, since acting in as a member of the Industry Committee in the European Parliament for as long as I remember. I see it from early stages that this is an opportunity for the future. So I was always supporting your industry in order to grow and contribute to the overall economic competitiveness and also cleaning of our sectors of economy. So thank you again for inviting me to join you today, and I want to applaud your coalition's commitment to deploy 100,000 fuel cell hydrogen trucks and more than 1,000 hydrogen refueling stations by 2030. We need this kind of impulse in parallel to the Alternative Fuel Infrastructure Directive revision, which will be likewise ambitious. The study you presented today is valuable because it makes a compelling case for fuel cell hydrogen lorries or trucks as an up-and-coming zero-emission alternative to diesel-powered versions. But to get these vehicles on the road, we need to work together. We have to combine the policy actions with business decisions from the European manufacturers and bring together significant research and development investment to accelerate deployment. There are a lot of changes and efforts ahead of us. Transport currently represents almost a quarter of Europe's greenhouse gas emissions and is the leading cause of air pollution in cities. What's more, transport CO2 emissions have increased in recent years in stark contrast to those of other sectors. And this cannot go on, and our Green Deal ambition is clear. By 2050, we must cut transport CO2 emissions by 90% compared to 1990 levels. However, our work does not end with CO2. Air pollutants such as nitrogen dioxide, NOx's, and particulate matter contribute to more than 400,000 premature deaths in the EU every year, with 76,000 directly linked to nitrogen dioxide. Transport has to clean up, and switching to low and zero emission alternative fuels are one route to a cleaner future. Our long-term climate strategy maps the different technologies and fuels that will enable the transition. As you will have noticed, there is no single silver bullet for any transport mode, which is why we are looking into a combination of fuel solutions. Hydrogen and fuel cells are sure to having leading roles, and the fact that the EU is a technological leader in this area will help. The development of hydrogen fuel cells applications for region transport modes through the Fuel Cells and Hydrogen Joint Undertaking helps us maintain this leadership. 2020 will perhaps be remembered first and foremost for other things, but it has also been a big year for hydrogen at EU level. The Commission Hydrogen Strategy recognizes the role that hydrogen can play in decarbonizing specific transport modes and the huge investment needed to roll out a hydrogen refueling network. To support investment, the European Clean Hydrogen Alliance is taking shape later this week. Before long, we will see a clear pipeline of viable investment projects to maintain global industrial leadership. Having representatives from the entire hydrogen value chain working together within the alliance will help coordinate investment and policies and public-private sector cooperation. Now, talking about funding, Alongside bringing stakeholders together, the European Commission has been supporting investment in alternative fuels infrastructure, including for hydrogen, for many years. Through the Connecting Europe facility, we have helped put in place 24,000 alternative fuel recharging and refueling points since 2014, as well as vehicles and vessels. The total investment, including private investment leveraged, is close to an impressive 7 billion. And finally, alongside the many challenges that the coronavirus pandemic has thrown our way, it has also created opportunities. The EU Recovery and Resilience Facility will support the EU economy by promoting a transition to sustainable transport, notably through the Member States' recovery and resilience plans. So, ladies and gentlemen, we have already come a long way. The market for hydrogen fuel cells, the market for hydrogen fuel cells buses is starting to get some traction. And the cars, the hydrogen fuel cells cars are now available, offering autonomy up to 800 kilometers. Unfortunately, the range of models is very limited and quite expensive, but I remain optimistic, in part due to the encouraging examples from the European cities deploying large-scale utility fleets like taxis. I think it's a good opportunity to replicate their stories. The next step is to make hydrogen fuel cells a real option for coaches and lorries. Long-distance road haul is challenging to decarbonize, and hydrogen provides a promising way for that. But we need to move quickly from pilot tests and demonstration projects to making the technology available from commercial point of view. As you know, the Commission will come next year with a proposal to revise the Alternative Fuels Infrastructure Directive. If we want to go further than only optional targets for hydrogen, refueling infrastructure by the member states, we must be able to just justify this. In other words, we need to have some commercial traction by then. And if I'm not mistaken, all of the actors needed for this traction are in this meeting. I therefore appeal to you, give us arguments we need to justify such a policy shift. Also here, increasing criticism that hydrogen is not that green after all, that less than 0.1% of global hydrogen production today comes from water electrolysis using renewable electricity. To make hydrogen a credible part of the Green Deal, it will be critical to have a clear pathway towards the production of hydrogen from renewable sources. We need to bring down the cost of producing hydrogen with electrolyzers that use renewable energy. The inefficiencies involved in this conversion process today limit the amount of hydrogen that can ever be produced at competitive prices. And ultimately, I'm sure that increasing CO2 emission prices will lead to optimal use of all decarbonized fuels, including hydrogen, for transport modes where they are most needed and valued. But it is up to all of you to ensure that hydrogen is the fuel of choice. At the same time, the Commission will continue to support all your efforts, not least through the joint fuel cells and hydrogen undertaking. So still challenges ahead of us, but as I said at the beginning, I'm a great friend of hydrogen. I do believe that we need to decarbonize fast. So let's make the best use of what is there in order to make important steps and then consolidate for the future. So I'm here for you, and I really hope that you will be here for us so that together we can push this kind of new policies and incentives to actually gain a real result in decarbonizing and moving towards the fuels of the future. Thank you very much.
Thank you so very much, Mrs. Commissioner, for your inspiring words, as usual, I would say, and also the support that you give to the hydrogen sector. And I will put it in your bio. I will not forget it this time. Thank you so much. So this announcement of 100,000 trucks and more than 1,000 HRSs by 2030 is really great. And it should inspire us all to work even harder to really realize the European hydrogen economy and the European hydrogen strategy that the Commission announced on the 8th of July this year. So, Mr. Commissioner, thank you again and wish you a very nice evening. So, dear audience, the day came to an end, but I will not close without thanking all today's speakers. We saw really fantastic research results, which demonstrates really that hydrogen and fuel cell works and are a reality. Or to say in the words of Mr. Picard this morning, hydrogen is not the future, it is the present. And I fully agree to what he said. So I wish you all a very nice evening, and I'm looking forward to see you all back tomorrow morning at 9:30 sharp. We will start again. Thank you and good evening.